All right, y'all, welcome back. Thank you to the 44 of you who have found us. 68 of you now. We're just going to give folks just another minute to find the stream. I do have a dog with me. I don't know who wants to see my dog while we wait. Let's see. Oh, there he is. Aw. He's like, what are you doing? Okay, so we have a really exciting lineup coming up. We are switching hosts, and we're gonna get a new talk. Oh, people are interested in the dog. His name's Ryder. He's super sweet. We love Ryder, but also don't try to break into my house because he doesn't like that. So, yeah, all right. I think we can oh, I love Ryder too. I think we can keep moving. So let's welcome our next host, Dr. Karen Schell. Hi, Karen. How are you?
Hi, everyone. I'm doing great. How are y'all?
Good. Having a lot of fun on the live stream.
Yeah. Taking a nice little dog break. You might see some cats joining us over here at some point in the next 2 hours or so.
Yeah. Oh, good. Yeah, we love a good pets sighting on the live stream. There he is. All right. Do you want to take it from here, Karen? I think we probably have a critical mass to keep going.
Great. Okay. So, hi, everyone. And thank you for joining us on hour 59 of this weather and climate live stream. Only 41 more hours to go. We have another great hour of weather and climate science for you. Later, we'll be talking to Melody Liu, who's going to be talking about precipitation and circulation. But before we begin, we want to remind you why we're here. Well, you're here because you know how important weather and climate forecasts are to protecting your lives and livelihoods. Luckily, the U.S. has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks. And we made the first computer models of the climate impacts of carbon pollution, so you can know what to expect in the decades to come. To make these forecasts work, it is essential that we have observations. And so the U.S. has developed this whole network of observations of weather and climate, including satellites, planes, balloons, boats, floats. And the resulting forecasting system, all this combined, is really a scientific miracle. And we're so excited that we could share that miracle with you tonight. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. And weather stations have been short-staffed, that we're losing our coverage, which is already degrading the forecast that we have. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. And we're losing a generation of scientists. As you heard Dr. K just talking about, the funding that we provide for students, undergraduate, graduate students, postdocs, early career scientists like the next speaker coming up, that is essential for helping them get the training and education they need to be scientists. But it doesn't have to be this way. If you like what you see here on this stream, then we ask you to please use the link on your screen right now to contact your representatives and tell them to save our forecast, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word about this live stream. Either way, we hope you'll learn something about weather and climate. And please feel free to ask any questions you have about science in the chat. So that being said, our first speaker today is Melody Liu. And before she gets started, I do want to say, remember that the speaker's views are their own, my views are my own, and hopefully you will enjoy her talk here.
Hi, can you hear me all right?
Yes.
Yeah, okay. Thank you, Karen, for the wonderful introductions. And then, so first of all, I would like to thank all the organizers to give us, the early career scientists, a opportunity to share our research with the general public. And I also would like to thank all the people that are following through the days. I have been watching the live stream for the past 2 days, and I saw a lot of positive and sweethearted comments on the chat box, which made me feel very positive and supported. Okay, so before I talk about my research today, first I wanted to introduce a little bit about me. So I did my undergrad in China in Tongji University, where I studied environmental science. Back then, I was not particularly interested in climate. And then I moved to UC Berkeley for a master, still in the environmental science. But at that time, I got super passionate on the fluid dynamics, and I took a lot of classes on it. And in one of the professors, he recommended a climate system class for a different department, and I took it. And I was so amazed by the complex behind the nonlinear systems, such as climate systems. And then I decided to pursue a PhD at Georgia Tech. And during my PhD, I'm mostly using the climate models with different hierarchies from simple to hard, from ideal to more realistic. I study the tropical precipitation, the tropical air, ocean circulations, and how the precipitations influence large-scale circulations around the globe. And then I moved to UCLA for postdoc. That's where I am right now. And now I still using a bunch of climate models, but I also added parts of the theoretical framework. We are trying to look at how the temperature distribution changes from now to the future. And by doing that, we will be able to know what's the best way to better forecast the heat rates or the flood rates in the future. So between my journey from the PhD to postdoc, I also took like one semester where I was a lecturer at Spelman College. Well, it is a HBCU in Atlanta, where I lectured a undergrad students about intro to climate science class, and that's a really fun experience. And then first, I want to say all my research are gratefully supported by the National Science Foundations and also the NASA fundings. And these two agencies not only support my research, but they also provide a lot of opportunities for me to travel, to meet other scientists, and to communicate with my work. So yeah, I wanted to say thank you. Without them, I couldn't do research that I enjoy. Okay, so move on to the talk today. I am going to talk about a work that is part of my PhD thesis, which is led by my PhD mentor. It is called Diverging Hydrological Sensitivity Among Tropical Basins, and how that phenomenon influenced the global climate. So you might think hydrological sensitivity is a kind of unfamiliar terminology, but it actually just basically says how the precipitation changes related to the SST changes, or here sea surface temperature changes. For example, looking at this simple equations, we have the changes of the oceanic precipitation on the left, and that can be decomposed into two parts. The first part is basically saying how much precipitation is going to change if you give 1 degree warming of sea surface temperature. And the second part just says the changes due to the changes in the sea surface temperature. Okay, so in this research, we basically find that in the tropics, in the tropical oceans, the tropical Pacific will be much more sensitive to the SST changes, which means that given the same SST increase, the Pacific is going to produce more precipitation than the other two basins. And then we further demonstrate how this phenomenon is going to have a global impact on the land precipitation and the land surface temperature. Okay, so before I start delving into the hydrological sensitivity, this particular phenomenon, I wanted to say a little bit backgrounds of how the tropical oceans influence the global climate. Many of you probably already familiar with the previous talks by Isa Held and many other fellow scientists, that we know that when you precipitate, and then the latent heat released by the precipitations is going to generate atmospheric waves and to change stuff like Rossby waves and jet streams. And one of the quite classic examples of such a influence is the ancel-tide connection. So basically in the El Nino year, the abundance in the precipitation increase in the Central Pacific is going to shift the jet equatorwards and brings a lot of moisture to the US and bring drier conditions in the eastern US part and warmer conditions in the northern part of the American continent. And this is happening in like a 5 to 7 years time scales. But if we look at a shorter time scale, say like a seasonal time scales, we have something called a boreal summer intraseasonal oscillation. So basically what you can see here is that the heavy convections in the Indo-West tropics, this convection will shift north and south. And during these oscillations, the diabatic heatings will interact with the upper level jet, and it will also release diabatic heating to trigger the Rossby wave propagation. And these interactions will cause the heating treatments that is going to warm the parts, for example, in US, as shown in this schematic. And so now we sort of get an idea of how the tropical oceans influence the global climate. And then we wanted to see how the precipitation over the oceans is going to change in the warming world. So if you folks were earlier today in the ISA Health wonderful talks, that we kind of already knows as the surface temperature increase, we will have more moisture content in the atmosphere. So ideally, globally, we will have increase in the precipitation. However, if you look at the spatial patterns of the precipitation changes, things are not that clear. So for example, here I have given 2 plots. The one plot on the top is the changes in sea surface temperature from across many CMIP6 models under a high CO2 forcing scenarios. And the plot on the bottom is the changes in precipitation correspondingly, so that we can see when you have a higher sea surface temperature increase, it also features a high precipitation increase. And this is long being referred to as the warmer get wetter. So to put it in a more formal language, that basically means when you have increase in SST, you will decrease the gross moist stability in the tropical atmosphere, and that will trigger more acid and precipitation. So to put that into a more grounded analogy, so just imagine you are boiling a pot of water on the stove. Apparently, if you turn a stove bigger, the heating is stronger, and then you get more bubblings, and the convection just happens faster, right? So that's basically more warming and more precipitation. And in the meanwhile, we know that maybe the heating on the stove is not even. So you have some places have more bubblings, some places have less bubblings. Then that's why sort of you can kind of imagine as like the warmer place get wetter. But then I know you guys are smart. You might be wondering if I just use a better pot to boil my water, which have a better conductance so that the water is going to boil faster. And yeah, that's what we sort of thinking here. So, right, so if you look at these equations, the SST changes is just part of the story. And we also wanted to know how fast the precipitation is going to change if you're given the same SST warming. So what I'm showing here is still, again, the precipitation changes in the warming scenarios. But here, each climate models are forced with a uniform increase in sea surface temperature. So in these situations, you don't have the SST spatial unevenness anymore. So what you're seeing here is purely due to the sensitivity to the same SST increase. So by looking at this plot, where we can clearly see that precipitation changes are still very spatially uneven. And we can see that apparently precipitation in the Pacific has a most prominent increase compared to the other 2 tropical basins. Or we can also just refer it to as that the Pacific has the largest hydrological sensitivity. Okay, so we can also kind of quantize the concept a little bit. So we can take the grid on our model, calculate the local precipitation changes and divide it by the SST changes, so basically the local hydrological sensitivity. And then we calculate with respect to each grid box, and we take the area weighted basin mean. That's what is showing here as the color bars. So the green refers to the tropical Pacific, brown the tropical Indian Ocean, and blue the tropical Atlantic. So as we can see, the Pacific clearly has a overall higher sensitivity to the SST changes compared to the other 2 basins. And these changes are robust against the model uncertainties on the spread bar. And here what's interesting is that we also plotted the results from the uniform warming and uniform warming plus the warming in different SST pattern on evenness. And these are shown here as the square and the circle. So clearly we see no matter if it's a square, circle, or bars, that Pacific just has a much larger precipitation increase regardless. And we can say, okay, now we know that Pacific is most convective compared to the other two basins. And similarly, we can also calculate the percentage changes in precipitation against SST. So in this way, we can sort of eliminate the regions with a very high or very low historical precipitation values. But no matter what, no matter how you define the matrix of the hydrological sensitivity, we do see that Pacific is the most convective basin, no matter how, and this property is independent of SST changes. So no warmer get wetter. It's just Pacific just going to get wetter no matter how. Okay, now, so before delving into why this phenomenon happens, we may want to say, okay, this seems interesting, but why do people even care? We live over the land. We don't live in the oceans. And yeah, why do we need to worry about this problems? Why if Pacific just gets more convective, that's it. Okay, so to prove the real world implications here, we did a series of model simulations. Here, I use a hierarchies of models. So I, first of all, take a realistic model called CAM5 in CSM1. Basically is a climate model developed by the National Center of Atmospheric Research, NCAR. So this has realistic convections, land, and then radiations and all sorts of things, only that the active ocean parts is replaced with a prescribed SST. And on the right, I have a very simple stationary wave model, basically just written in the equations in the momentum balance and then the mass conservation, that very simple model. So for both of these models, we perturb them with the diabatic heating that is associated with these interbasin hydrological sensitivity differences. So basically this value. And then we're mostly going to talk about the results from the more realistic models, but we cross-check our results with the simple models to make it sure that's not something that is artificial. So here's how we produce this diabatic heating. So first of all, the plot on the top is the precipitation response in the semi models. So we take the precipitation, we calculate each grid point, calculate the hydrological sensitivity at each grid point. And then we subtracted these values by the basin mean differences in the HS. And then we translate it back to the precipitation. And that's what we see in the plot B. So when all the basins have the same sensitivity to SST, that's how the precipitation change is going to look like. So obviously the Atlantic is going to be less drier because you don't have the drying in the north and south of the equatorial of the Atlantic anymore. But accordingly, the Pacific Oceans will have more drying in the south and north of the equator. Okay, so now, if we take the differences of the A and B, then apparently by definition, that is the precipitation changes due to interbasin hydrological sensitivity differences. And then we compare with the precipitation changes under the uniform sea surface temperature warming. We see they are pretty similar. So basically, again, saying that the tropical Pacific is highly sensitive to SST warming, and this phenomenon has nothing to do with the SST pattern changes. Okay, so next, getting these two precipitation changes, we translate this into the three-dimensional vertical diabatic heating profiles, and then we do two experiments. One experiment that we prescribe the model with the diabatic heating changes that include the sensitivity differences, and another one without the sensitivity differences. And the difference between these two experiments basically just telling you the impact of this phenomenon. And then here we're only going to show the results from the CAM5. Okay, so here are the results. What I'm showing here on the left is the land precipitation changes due to the total precipitation diabatic heating. And one on the right is the impact due to the interbasin hydrological sensitivity differences. So as you can see, we see a significant wetting in the US, in North Africa, South America, and we also see the drying in the Amazon rainforest, New Mexico, India, Australia, and Central African rainforest. just to look at these plots, we notice that all the significant changes happen within the regions that has a densely populated areas or has rainforests, which is a crucial ecosystem. Right, so now, say, just in the future, this phenomenon is probably going to cause the US become wetter. Does that mean more frequent flash flood in the future? And then if we look at the Amazon forest, that's going to be drier. So does that mean possibly more wildfires? And similarly, we can also look at the land surface changes due to this phenomenon. So we can see that due to the hydrological sensitivity differences, that the Indian Bay of Bengal areas is going to be much hotter. So we already know India has a pretty bad heat stress problems, but does that going to amplify the problems when the world gets warmer? And again, we're probably going to see more wildfires in the future. So that's pretty concerning. And next is going to just sort of bridging why do we see these like changes outside of the ocean that due to this like a phenomenon we see in the ocean. So basically that's just a simple mechanism, what we call as a gill type response. So basically when you have a symmetrical heatings around the equators, you're going to get a pair of circulation changes, and these circulation changes will be the opposite in the upper level, which is showing in the plots here. So basically we can see that the Rossby wave trend is propagating in the upper troposphere from the ocean towards the land. And we will also see that the cyclonic response is going to bring moistures towards the inland of America, which is going to make the continental US wetter. And then we can also check the tropical circulation changes. Here I'm plotting the changes in the Walker circulation strength, as well as the climatological value here in the gray contour. So to make it look clear, here I'm marking the historical control Walker circulation positions. And then due to this hydrological sensitivity differences, this Walker circulation is going to shift eastward. And that's going to create descending motions in where we see in those like critical zones in previous slides in the Mexico, Amazon forest, and also the India regions. That's where you see the descending motions happening. So so now we sort of know that how this hydrological sensitivity differences in the ocean going to impact the climate in the land. And then go back to the questions that I said earlier. So why the three different basins respond in a different way to the SST warmings? So here it's a similar plots to the bar plots I showed earlier, but just instead of plotting the bar plots, here we plot a precipitation condition on the relative SST changes into different bins. So as you can see, no matter in the present day or in the future, the Pacific is going to be much more sensitive, much higher precipitation given the same SST values. So again, the Pacific has the largest hydrological sensitivity. And then we can do the similar thing, but condition the precipitation onto the bottom level moist static energy. So what is moist static energy? For people outside of the field, it's basically just a concept that wrapping up the both temperature changes as well as the humidity changes. So now instead of just looking at SST, we look at the combination of SST and corresponding humidity changes. So now if we do similar calculations, we do see the precipitation when it conditioned onto the low-level MSE values, these differences between the basins are pretty much just shrinked. So you don't see this large discrepancies anymore. And so now we kind of like know, okay, so that is because if we wanted to explain the precipitation discrepancies, we can basically just trying to explain why the MSE is different. Okay, then we can further decompose the MSE into different components. But here, first I'm showing the MSE conditioned onto the SST, so which is already expected that the Pacific will have the higher MSE sensitivity to SST, similar to the precipitation values. But what is interesting is that if you plot the air temperature conditioned onto SST, and this value has no discrepancies between different basins, so then we know that these interbasin discrepancies are basically originates from the relative humidity. And then if we perform the similar calculations here, then we do see, okay, Pacific has the largest relative humidity compared to the other basins, and it's more sensitive to the SST changes. And now you may wonder why the relative humidity has the interbasin discrepancies. Okay, now here we can plot the spatial map of the relative humidity in two different experiments. One is with the uniform SST warming, so no SST pattern changes. One is including SST pattern changes. And forget about the equations on the bottom, it just tell you how to calculate this transport term. So, and then the second row is basically the changes in the transport of relative humidity. So we can see that when you have a dry relative humidities in these regions, you basically also have a dry transport of humidities. And then if you look at the geographic distributions, we know that these places are basically where the most deserts are located. So what it's saying is that the dry advections from the land is going to cause these phenomena. Okay, I think my time is almost up. So anyway, by wrapping it up, this phenomenon is essentially basically just amplification of the present day humidity backgrounds. Basically, if you have a wetter place, and then you will become wetter, and if you're already drier, and you are drier. Okay, so that's pretty much all the important messages from this work. Here are brief summaries of my talk. So first of all, we know that tropical Pacific is most sensitive to the SST warmings under a anthropogenic forcing scenarios. And the second one is that such interbasins and hydrological sensitivity differences has a large social and global implications. It largely impact the global and land precipitations, especially where have a lot of populations and where the crucial ecosystems are located at. And further, the basic mechanism underlying this phenomenon is because a thermodynamic amplification of the existing spatial unevenness of the relative humidity. And yeah, that's pretty much what I have. Thank you for listening. I'm ready to take questions.
Okay, great. Thank you so much. That was really interesting, and I loved how you started at the beginning talking about your path. There are some questions on chat asking about that initially.
Cool.
And I really loved how you demonstrated why what's going on in the ocean and like in the tropical ocean is important. There was a lot of debate or a lot of conversation during your talk about diabetic heating. And so I was wondering if you could start by sort of defining how you're using it in this context.
So to say diabatic heating, we first need to say adiabatic heating. So adiabatic just means if you have a closed system that you don't have additional input of heat from outside. So here diabatic heating basically just opposite of that meaning. So in this context, diabatic heating is due to the condensation from precipitation, right? So when you go through the phase changes from the water vapor to the liquid phase, and then you're going to lose heat. And that heat is going to release into the atmosphere, going to basically heating up the atmospheric column. So that's here what I meant by diabatic heating in this particular context. But also I know that you guys are going to say, oh, there are other diabatic heating formats like the radiative diabatic heating and sensible heat. These are all formats of diabatic heating. But in the tropical oceans, the dominant diabatic heatings are the latent heating released by the precipitation. Yeah.
So you talked on this sort of near the end of your talk, but you were a little bit rushed. A question about why the Pacific is more sensitive. So, and there are some ideas thrown out. Size, surface area, impact of land mass. So maybe if you could, review what you were saying at the end there as you were rushed a bit.
Yeah, because I saw the chat on time off. I'm like, okay, I gotta rush through. But yeah, these are actually very good questions. This is basically what we were asked by the reviewers. So the simple answer is that Pacific is more sensitive not because of the size, not because of the surface area, and not because of how much you have the land. However, it is because of the dry advections from the land. So if you can see this plot that I just rushed through, so the top row is the changes in the relative humidity, and the bottom row is the transport of relative humidity. And the equation in bottom is how do you calculate this transport term. But basically you see the Atlantic Oceans, it's more like has a lower relative humidity compared to the Pacific Oceans. And these is basically matches the transport of humidity terms on the second row. So that's basically, and then if you look at the land surrounding by this, but you look like the ocean surrounded by the land, and this land usually has this where you have desert and super dry places. So the wind just blow the very dry air from the land to the ocean, which make the Atlantic has a lower present day relative humidity. And this present day relative humidity is going to carry its impact onto the future scenarios. And that's where the plot didn't really go into details. So on the bar plots on the right, it shows the decomposition of this transport of humidity into the dynamical term and a thermal term. So you see it is the thermal term that carries this interbasin differences. That's what I say, wet get wetter and dry get drier. That. But we did carefully calculated all this, like the components that you asked in the questions, and these are not the reason. Yeah.
Great. Well, I think unfortunately we need to move on. I would love to hear more about this, but thank you so much for joining us. And yeah, really, really interesting stuff.
Thank you.
Okay, so for those of you who have joined in the last half hour or so, we are on hour 59 of the Weather and Climate live stream. So we have about 41 hours more to go. We have some more great talks coming up. But before I get started, I want to remind you of why we're doing this. So you can see right now that number on your screen. You're here because you know how important weather and climate forecasts are to protect your life and livelihoods. And we're so fortunate that the U.S. has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast. We developed the first, we to help you know what you can expect in the coming weeks. And we made the first computer models of the climate impacts of carbon pollution so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites and planes and balloons and boats and floats. And the resulting combination of these all is really more than the sum of their parts. It really is a miracle. And we are so excited that we can share some of this scientific miracle with you. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already impacting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of weather and climate is disappearing. And we're losing a generation of scientists, scientists like you just saw, as students and postdocs and other early career scientists are missing out on the wonderful educational and training opportunities that I had. But it doesn't have to be this way. If you like what you see here, then we ask you to please use the link on your screen, the one right down there right now, and contact your representatives and tell them to save our forecast, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word to join this live stream. Either way, we hope you learned something about weather and climate, and please feel free to ask us any questions about science in the chat. So our next speaker today is McKenzie Larson, who is going to be talking about wind. And so before she gets started, I do want to remind everyone that anything that McKenzie says is her views only, as well as anything I say are my views only. But without that out of the way, let's get started on the science.
Awesome. Thanks so much for having me and all the organizers. I'm really excited to be here. So I'm McKenzie Larson. I'm a PhD candidate at the University of Colorado Boulder in the Department of Atmospheric and Oceanic Sciences. And my research focuses on Colorado Front Range weather, so snowstorms and windstorms. And today I'm going to talk to you about some of these windstorms. All right. Oh no. Okay, so just to kind of orient everyone, since we have people tuning in from all over, I'm going to be talking about the Colorado Front Range today. So this is a topographic map of the state of Colorado, and specifically where you can see my cursor, I'm going to be focusing on the Front Range, which is located near Boulder, where a lot of our atmospheric scientists are, and it's just to the west of Denver. So to start off with, what is a downslope windstorm? So like you can see in my beautifully drawn graphics, I'm not an artist, I'm a scientist. These are some really strong gusty winds that blow down what we call the leeward, or this right side of a mountain range. And it leads to some really strong downslope winds at the surface on this leeward side of a mountain slope. And so why do we care about these windstorms? Well, they can actually be really, really powerful, and that can endanger lives, damage property, it can disrupt travel, and it can also exacerbate fire weather. And one such example that made some recent headlines a few years ago was the 30th of December 2021 Marshall Fire. So this fire started during a really, really strong downslope windstorm along the Colorado Front Range. It was so strong, sadly, there were 2 deaths and there were over 1,000 homes destroyed. So I'm going to kind of walk you through how this fire became so disastrous. So this is in the end of December 2021. If we go back 6 months into more of the spring and summertime, we had a really wet, rainy season. A lot of vegetation was really lush, blooming, everything was really green. But then leading into the fall, we had like almost no rainfall and snowfall, really dry. So suddenly we had all these plants that were, nice and tall, really lush, and they all dried out and basically became kindling for a fire. So we were really susceptible to fire weather. So on the 30th of December, when we had this really strong downslope windstorm that lasted for hours, with up to hurricane force winds, all it takes is one little ignition source to get something as disastrous as the Marshall Fire, which you can see some photos here on the left, and on the right shows the areas where the fire impacted houses or structures that were destroyed in the red, and then other structures that were damaged in the yellow. I can also show you some wind gust observations that were taken that we always have going on, but these are specifically during this windstorm. So you have time on the bottom x-axis, and then our wind gusts in meters per second on that left x-axis. And so we can see the morning time of December 30th, we have some winds really start to ramp up leading up into 10 a.m. And then suddenly we have the Marshall Fire that ignites, as you can see with this big red arrow, and these other 2 arrows denote times where evacuations were occurring. And you can see these are all different observation sites along the Front Range, and in the red is at the National Center for Atmospheric Research, which you've all heard a lot about already here in Boulder, and there was a gust there measured at 112 miles per hour. So really strong winds, you get a fire going in there, there's really not much you can do to stop it. And so this fire is estimated to have cost about $2 billion. So this is a really great graphic from NOAA showing the 2021 $1 billion weather and climate disasters. You can see the Colorado fires are included in this now. And it just shows how impactful these downslope windstorms can be. And then one thing I want to point out about these graphics, these $1 billion disaster website is It's hosted by NOAA's National Centers for Environmental Information, or NCEI, and with recent cuts and evolving priorities, now this website is no longer, and this data set is no longer going to be updated, which is quite a loss to our scientific communication to everyone. So now that I've hopefully convinced you that these windstorms are important, I want to kind of walk you through the dynamics and the processes of how these windstorms occur along the Colorado Front Range. So if we have some Coloradans in the chat, you may or may not know that we actually have two types of downslope windstorms in Colorado. We have Chinook or fen winds, and then Bora winds. So we're going to start with Chinooks. So these are our warm winds. They're often called snow eaters. And so I have a little doodle here of a low pressure system denoted with the L, with an attached cold front in blue and a warm front in red. And so these Chinook warm winds occur before a cold front moves through. So that air is still warm. And we're getting this west to northwest flow, or the way the winds are moving. And we get what's called cross barrier flow. Essentially, the winds kind of intersect perpendicular to those mountains, and then the flow can just descend upon the mountains. So I have a little graphic showing that here. Essentially, what's happening is we have cold air that's essentially trapped or dammed behind a mountain range. And then we have this warm, fast air aloft or above these mountains that can essentially just flow above the mountains. And then as it descends towards the surface, it compressionally warms and continues to accelerate. And then we get some really fast winds located in Boulder. Another way that this can occur is through orographic precipitation. There was a talk last night about this. So this is when we have some moist air that essentially ascends up a mountain range. And once it gets to a high enough point, it gets to its condensation level, that moisture in the air condenses, precipitates out, and you get a dry shadow, which some of you might be familiar with. And essentially, we're getting this warm air that, continues to warm and dry as it descends. And one cool thing with this orographic precipitation along a mountain range is that you can get what's called a fen wall. And it's essentially a wall cloud. So it's when I drive into work and we see these, it's just like a big wall cloud, but it just doesn't reach us because the air gets to the top and now it's all dry and has all precipitated out all the moisture. So these are our warm winds. Now Boras, as I'm sure you can guess, are now going to be our cold winds. So now this low pressure system has moved through more. That cold front has moved through the Colorado region. So it's post-frontal, and now we're mostly looking at northwest winds. And so now that the cold front, that little wedge, has moved through, the cold layer is a lot thicker now. So this kind of cold pool is now extending above mountaintop. But it's capped by this warm air above. That's what we call an inversion layer. So we know that warm air rises and cold air sinks, and essentially you have this really stable layer. So it's forcing this cold air to essentially funnel through at the top of the mountain, and it's going to speed up. This air is going to kind of speed up and then descend towards the surface. They'll be a little warmer than the cold air over here, but still cooler air. And if there's any physics nerds out there, this is Bernoulli's principle in action. So now that we've kind of talked about these two types of winds, I kind of want to show you just what the actual environment around a downslope windstorm looks like when they're actually occurring. So often when we get a downslope windstorm, it establishes what we call a mountain wave or an atmospheric gravity wave. It sounds kind of scary, but it's just we have that cold layer at the bottom and then the warm air above it. So it's stable, so it can't really go anywhere. So it's essentially just kind of bobbling up and down as it goes. And it makes these little gravity waves that you can often see in satellite imagery too. This is an example from one of my graduate classes. Air is a fluid and so is water. And you can see this if we picture the mountains as this little plastic bit in the water. We have air kind of speeding up. It hits these mountains and then you get these little standing waves essentially. And then something that's really cool that you might have seen if you've been in Colorado before, we get these fun lenticular clouds. They look like UFOs. So this is when we have, some moisture in some of these layers of the atmosphere and they get high enough and they form a cloud. And it's really cool. Like in this picture you can see here, you could often see the different layers of the atmosphere too. So we can also see these mountain waves, example during the Marshall Fire. Since we have the smoke from the fire, it's actually going to act like a tracer so we can see what's going on in the lower level of the atmosphere. So you can see these mountain waves at the bottom level of the atmosphere, basically trapping the smoke in. And then kind of another really cool thing that's happening, we're getting these pyrocumulus clouds. So the smoke's actually seeding some cloud formation up at the top as well. Then if we get a little further into a downslope windstorm, it's a little more established. Things are picking up and getting a little more turbulent. The atmospheric flow is going to look more like this. And it looks a little crazy, but I'm going to walk you through what's going on. So again, we have the flow. We still have those lenticular clouds. We can get what's called a wave breaking region. So these downslope windstorms can essentially affect the flow pretty high up into the atmosphere. And if you kind of think about yourself like sitting in the ocean, this is what happens when a wave kind of like collapses back on itself. So that can extend upward into the atmosphere and down towards the surface. We can get kind of these spinning regions of air. And we call these rotors. This is another example from the Marshall Fire, where we have really fast air at the bottom. And then essentially it kind of flips up and it's going to start spinning on its own here. And this is actually called a hydraulic jump, which you might have seen in a river before. So the air or the water, as shown here, speeds up. It hits a certain, what we call a critical point, and then it gets really turbulent underneath. And that's what you see happening here with all this smoke. And so now I kind of want to talk to you more about a recent paper we've been working on that we collaborated on that's actually out, and you can Google it and read it. I definitely encourage you to do it, even if you don't have a scientific background. But I want to talk to you about Boulder's downslope windstorm history and future. So we've known that downslope windstorms have been occurring in Boulder for a really long time, especially in the 80s. There were some really strong windstorms. This is measurements at the NCAR Mesa Lab from 17th of January, 1982. These are what the measurements used to look like before they were digitized. These are the analog measurements. And then on the right, you're seeing a map of the Colorado Front Range, just with specific damage and wind speeds during this event. And what I want to point out is at the NCAR Mesa Lab, there was a 137 mile per hour wind gust recorded. So that's hurricane force winds. There were 20 airplanes destroyed at the Boulder airport. There's a picture of that shown here. Lots of housing damage, power lines down, which, that can be troublesome for fire weather. And so really powerful storms that we know have been going on. So we wanted to look at how have these changed over time. So what we did in our study is we're looking at the daily maximum wind speed where the gusts are over 70 miles per hour. We went all the way back to 1967 into the 2020s. And that's what you're seeing here in the lines, that wind speeds on the y-axis. And then I'm going to kind of break down the different colors. So leading up from 1967 to 1990, we have all these analog measurements. We don't have any digital measurements, sadly, and none of these were digitized, which is really sad. They were all thrown out, but we are so thankful for Kathy Smith at the NOAA Physical Sciences Laboratory, because she has a webpage where she has kept a record of the high wind speeds and gusts throughout Boulder, which you can see in the blue lines, and specifically at NCAR in the pink. So she's kept a track of that, and this study is very thankful that she did that. And then once we get to 1990, NCAR installed some digital anemometers, which are shown in the darker reds. And then one thing you might notice is that there's more lines as you get later in time. We're not saying that downslope windstorms have increased over time. It's just due to, we don't have any more measurements from earlier, so we can't say anything about that. But what I want you to look at is the wind speeds around 100 miles per hour. What we have noticed is that there are not as many peak gusts over 100 miles per hour after the 1990s. So we want to know what's going on there. So in our study, we put on our little detective caps and we want to investigate why is this happening? And we essentially came up with 4 different hypotheses. We said, well, this could be due to different changes in instrument location. We had the analog measurements. Now we're putting them on digital anemometers. We're moving them on a 10-meter mast on top of the roof of NCAR. And sometimes we're putting them on a 2-meter mast. So it could be something due to that. What about changes in building codes? Are we just not seeing as much of the damage that used to happen because we have better building codes in Boulder? So when you build a house in Boulder now, you actually have to have the clamps on your roof as if you're in a place that would normally get hurricanes. So maybe we're just not seeing as much damage. What about increasing roughness length? That's just a really fancy term for friction from tree growth. So all the trees, since people have been moving here, are all getting bigger. So maybe the wind is just experiencing a slowdown from friction before it can actually reach the observation sites. And then what I'm going to talk about in my last few minutes is like, what about climate change? Are these winds changing due to climate change? And that's what I'm looking at as my second project in my PhD. So we're looking at how these characteristics are changing since the 1960s. And so I'm going to introduce what we call reanalysis data. This is from the European Center for Medium Range Weather Forecasting, and essentially takes all of the observational data that we have available, pairs it with model data, and makes it our best guess at what the entire atmosphere looks like at a certain time. And I'm going to look at it specifically in winter months. From there, I'm going to calculate an epoch difference. So I want to look at this recent period where we have the newer anemometers from 1995 to 2021. And from that, I'm going to subtract this earlier period of time, 1967 to 1993, when we have the analog measurements, to see what is the difference in the atmospheric state. And so here, you're looking at that epoch difference in the winter months of wind speed difference at 500 hectopascals. So that's going to be above mountaintop. We're going to think back to those graphics that I showed you at the beginning. And we're seeing a lot of red. So we know that the wind speed above mountaintop is increasing. And if we look a little further to actually at mountaintop, where you can see the higher peaks are kind of shaded out in the gray. If we look at Boulder here in the blue, again, still looking at wind speed, we're now seeing a decrease. So we're having faster winds above the mountain, slower winds below. So we know that kind of layer that the wind is funneling through is actually getting a bit bigger. So the winds are slowing down a little bit right at the surface, or at the top of the mountain, which will then in turn maybe slow down what we have going on at the surface in Boulder. So we call this changes in vertical wind shear. So when wind is changing in magnitude and or direction in the vertical. So that could be changing these windstorms. You can also see this in what we call a cross section. So this is height or pressure levels. The mountains are shown here in the hatching. We're at the Boulder latitude. And so you're kind of looking at it like a cross section. If we cut in the mountain, and we can see again at mountaintop, those wind speeds are decreasing, but above mountaintop, the wind speeds are increasing. So we're having an increase in vertical wind shear, which could be decreasing those gusts. Another thing we can look at, also still a cross section, is just a temperature difference. And what we're seeing is just a ton of red, which, we kind of know from climate change, things are warming, but we can really see that here. And so that's going to, if we think about that cold layer and that warm layer, both of them are getting warmer. That's going to change the stability and just subtle characteristics that are going to change these windstorms. So what about the future? So this is what I'm currently actively researching. Again, I'm using that reanalysis data, but now I'm going to pair it with the Community Earth System Model, Large Ensemble, which is a climate data set developed at NCAR. And we're going to compare that with that AERIFY reanalysis. So you've already seen this figure. It's just a little zoomed out, that wind speed difference above mountaintop. And now I can compare that with an even different epoch difference. So the future, way in the future, 2081 to 2100 minus 1991 to 2010. And so this color bar has actually doubled, and you can even see there's just more red. So these wind speeds above mountaintop are continuing to increase over time when we look at the climate models. So what I'm specifically looking at is how would an observed downslope windstorm, so one we've already seen, how would that actually look in a future climate? And to do that, we're using a weather model simulation, the Weather Research and Forecasting Model that's developed at NCAR. And we're trying to make sure that we can recreate these downslope windstorms. This is the downslope windstorm that occurred before the Marshall Fire on December 15th, 2021. We need to make sure we can accurately reproduce this windstorm, and then I'm going to perturb it with some climate forcings to see how this specific windstorm would look in a changing climate. So these purples are 10-meter wind speeds on the left. Purple is faster, and then the right's a cross section. And so going back to when we talked about those mountain waves and the gravity waves, you can really see it here along the Front Range in this WRF simulation. And then on the right, if we look near where we're at the surface with my cursor, you can really see those winds speeding up towards the surface as they descend the mountain slope. So we're very happy with how these simulations are looking, and we're gonna keep on chugging with this research. And I'm very excited to see how it turns out. So I'm pretty much out of time, but I really just wanted to say how important government funding has been. To me, I would not be where I am today without it. There are so many amazing programs within the government that I worked on, as well as people. When I was an undergrad, I participated in the NOAA Hauling Scholarship Program, which gave me a scholarship that helped me pay for my undergraduate degree. I also completed an internship with the National Weather Service in Boulder, which is what got me into studying downslope windstorms, and I found my true passion for that during that internship. And then from there, I went to NCAR to continue looking at these, and now I have a DOE Computational Science Graduate Fellowship that allowed me to go to Los Alamos National Laboratory and actually do some ocean modeling. And then currently I am at NOAA in Boulder doing the LaPenta internship, working on some model development for our real-time forecasting. So I'm so thankful for all of the funding and the American people and taxpayer dollars, and I wouldn't be here without it. So I'm happy to take any questions, and I have a link to papers if you'd like to read any.
Okay, great, thank you. That was really interesting, and having lived in Boulder, I did have my fence blown over one winter, so definitely familiar with those winds. There are so many great questions in chat. I don't even know where to get started. I guess one of the questions in regard to the question about building codes reducing damage, would it be possible to involve the public in data collection through the use of sensors on their homes to maybe measure gusts?
Yeah, you definitely can. I know there's a lot of weather weenies in Boulder, so a lot of people have instrumentation just in their backyard, like one that you could just buy online, and you can report gusts if they get above a specific threshold to the Weather Service. You can do like spotter training, and they give you a spotter number. It's not just for tornadoes. You can report your snow and rain and especially damage as well. You can also do that like on Twitter too, and tag them, and they will record it.
Oh, that's great. Great. Mm-hmm. I know we have a bunch of people interested in citizen science in the chat here.
Yeah.
Are these winds, can they be used for energy generation? A water dam can be used for energy generation.
Yeah, so I am not a wind energy expert, but we actually have the National Renewable Energy Laboratory is right near Boulder, and they have some wind turbines here. But from my understanding, it's too windy because like the turbines are like too big. It actually can get dangerous. Correct me if I'm wrong, but I think sometimes, yeah, it's a little too much and it gets a little dangerous.
Yeah, that's my impression as well. Let's see, maybe one more question. Someone's asking about Bora and Chinook winds. Do they always occur in conjunction with each other, or is it possible to have one without the other?
Yeah, so from my experience, you can definitely get them. They don't have to occur together. Sometimes if you have a really strong low pressure system and it kind of either forms like within near the Rocky Mountain range, or that cold front moves through just right. I talked about earlier about that cross barrier flow. That's what's really important. Those wind speeds kind of have to hit the mountains just right to kind of cross like this to then funnel downward. So they can occur if that happens before the front passes and after, but it doesn't have to for sure. And sometimes there's more of these weaker low pressure systems or weaker fronts where it's just kind of like, I don't know how to say it, not enough oomph to get one of these windstorms going, if that makes sense.
Yeah, great. Thank you. And there was one more really quick question of who came up with the title of the paper.
Yeah. Earth, Wind, and Fire. That was Jerry Meal. He's been a longtime scientist at NCAR and has done a lot of great climate science research. A lot of papers we all cite. It's been a fun project for him because he's been here a long time. So I bet he's been thinking about that one for a while.
Had it in reserve, I
Yeah.
guess. All right. Well, great. Thank you so much. And yeah, this is really, really interesting. Thanks for sharing with us.
Yeah, thank you. Have a good night.
Okay. Well, I think we are now in hour 6, hour 60, if that is correct. So that means I get to do another announcement here. So welcome to hour 60. We have 40 more hours to go. And we have another great talk coming up by Kara Hartig, who's going to be talking about something super cool. But before she gets started, you're here because you know how important weather and climate forecasting are to protect your lives and livelihoods. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in coming weeks. And we made the first computer models of the climate impacts of carbon pollution so you can know what to expect in the decades to come. To make these forecasts work, we have to have observations from this huge network that includes weather stations, satellites, planes, balloons, boats, and floats. And all of these together it creates this more than just the sum of their parts. It's really a scientific miracle. And we're so excited that we can share this science with you today. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already impacting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. And we're losing a generation of scientists. You just heard from McKenzie, who showed you the last slide, all of the different agencies that have funded her education. And if we don't have that funding for students and postdocs and other early career scientists, they're going to miss out on all of these tremendous training and educational opportunities. But it doesn't have to be this way. If you like what you see here, then we ask you to please use the link on your screen, the one scrolling by right now, to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word to join this live stream. We hope you will learn something about weather and climate, and please feel free to ask any questions about science in the chat. So our next speaker is going to be Kara Hartig, and she is an Arctic scientist going to talk about super cool Arctic clouds. But before she gets started, I want to remind everyone that any views or statements expressed here are our own opinions and not those of anyone else. And with that out of the way, go ahead and take it from here, Kara.
Thanks for the introduction. I'm happy to be here, especially so at such an odd hour of the day and an odd time of the week. This is a really interesting way for me to be spending my Friday night. So my name is Kara Hartig. I'm a postdoctoral researcher at the Cooperative Institute for Research in Environmental Sciences, which is hosted at the University of Colorado Boulder. And I'll be going over one of my favorite topics today, which is supercooled liquid clouds in the Arctic. And hopefully by the end of this talk, you'll understand why I think they're so interesting and also why they're so important to the climate. So the first thing to note is that the Arctic is warming at 2 to 4 times faster than the globe as a whole. This is a phenomenon called Arctic amplification, and it's shown in the figure here. So this is showing the change in temperature from the sort of late 21st century into the 2000s. And one of the first features that might pop out to you is this really dark red splotch at the top near the North Pole and over the Arctic Ocean. And this is called Arctic amplification. Now, it's a feature that's been understood and even predicted for many decades. The very first climate models in the 1970s included this feature. And so it's been an interesting focus of research for a really long time to try to understand what causes Arctic amplification, because it's so ubiquitous across climate models, and it's become so clear in observations as well that we now see it as a really fundamental part of the climate response to warming. So there are many factors that contribute to Arctic amplification, but in the interest in time and also of my own focus on clouds, that is the factor that I will be going over today. We're also going to be seeing some data that I work with over the course of this talk, and I wanted to point out here that all of that data so far is focusing on the winter months because Arctic amplification is strongest in the winter. And it's also kind of easier to summarize results if you try to narrow down the level of complexity a little bit, but almost all of these results carry throughout the year. They're just easiest to see in the winter. So here I wanted to highlight the source of a lot of the data that I use. So all of the data throughout this talk is going to be coming from the North Slope of Alaska. This is a long-term Arctic observatory that has been there since the late 1990s. So there's a map on the left-hand side that shows you where it's located. It's at the far, far northern tip of Alaska near a small town called Utqiagvik, right in the Arctic Circle. And the station is photographed on the right-hand side, and you can see multiple instrument platforms and a researcher technician who's plowing their way through the deep snow that often is located at this site. So a couple of notes about this particular location. The North Slope of Alaska is managed by the US Department of Energy as a part of a series of facilities that are intended to provide long-term observations of the atmosphere, the surface, and other components of the climate. This particular site, as I mentioned before, has been around for over 20 years, and it features many different instruments and different kinds of measurements, as are pictured in the image in the instrument platforms up above. And this is a huge advantage to science because it means that you can start to coordinate across different components of the climate system and also to find ways to validate and check your results to make sure that they make sense. So I might use one instrument to detect clouds, and if I want to make sure that the clouds are actually there, I can validate with another instrument that detects clouds in a different way to make sure that the detection that I have is actually robust. So having some of these sites that have both long data sets where you can start to look for things like trends or focus in on really specific situations, and that have many different types of instruments are really crucial to performing this kind of science. And my understanding is that a lot of the proposed budget cuts would potentially be threatening some of these long-standing observations. The final note that I want to make here is that partly because this site is managed formally, all of the data that becomes available to the public is quality checked and validated by experts. So there are people who are extremely familiar with the instruments that are being used and also with that specific site and its unique challenges, who make sure that all of the data that is going out to scientists like myself is of good quality and has been confirmed to be the sort of best possible version that we can access. So this is a really, really excellent resource for people like me, and it makes it possible to jump into a brand new location and a brand new data set with potentially not a whole lot of background, which I didn't have when I started this project. So one of the first things that I wanted to talk about is that I introduced this with Arctic amplification, which is a surface temperature measurement. But surface temperature itself is influenced by many factors, and in particular is really closely related to how energy is flowing either into or out of the underlying surface, which in the Arctic might be the ocean, it could be sea ice, or it could be the land, as is measured at North Slope of Alaska. So in this plot here, along the vertical axis is the surface temperature, and it's warmer closer to the top and colder at the bottom. Because this is winter, you'll notice that almost all of those temperatures are below 0 Celsius, so it's below freezing all of winter here. And along the x-axis is showing how energy is flowing in and out of that surface. So points further to the left indicate that energy is escaping the surface, it's cooling down, which is the main situation that's happening in the winter, and further to the right means that the surface is actually heating up. And the first thing that we notice here is that if we separate all of these observations in terms of what the clouds overhead are doing, we see that clear sky conditions in gold are almost always associated with colder surface temperatures and an actively cooling surface, whereas cloudy situations shown in blue tend to correspond to the surface heating or at least maintaining its temperature. So the cloud state over a particular location is a really important determinant to whether the underlying surface is in an energy gaining or an energy losing state. So that motivates us to want to look a little bit more closely at what determines some of these cloud properties so that we can ultimately try to understand the surface temperature. I also want to point out that the surface energy balance affects more than just temperature, which is one of the reasons we're looking at that instead of temperature alone. So if you're looking at surface energy balance over sea ice, the amount of energy going into the sea ice is going to influence how quickly it melts and also potentially make it harder for it to grow. Over ice sheets, clouds in particular can have a really large impact on some of these extreme melt events. So for example, the Greenland ice sheet has experienced some extremely strong melt events in the last few years, which in many cases are associated with these overlying low clouds that are providing additional heating, which I will explain as we go on. By the end of this talk, you will understand why clouds can heat the surface. So there are additional components of this where particularly ice sheet melt contribute to sea level rise around the globe, which threatens coastal areas, cities, wetlands. It can also have an influence on biodiversity, particularly in the case of sea ice extent. So certain animals really rely on having a particular sea ice distribution, such as seals and polar bears. And as the sea ice retreats and becomes thinner, the ocean becomes less able to support many of those larger sea creatures. It also can lead to relocations of certain types of fish stock that are trying to chase colder and colder waters as the surface melts, and influences the entire food web of the ocean. And finally, many of the high latitude, meaning close to the North Pole land, is subject to permafrost, which means that that land is frozen solid and has a very high percent of ice in addition to soil. And as the surface heats, that permafrost begins to melt and the land loses a lot of its structural integrity. So this can threaten infrastructure such as roads, buildings, and pipelines in any Arctic region. And it also tends to release both methane and CO2, which accelerate global warming. So understanding the surface energy balance of these Arctic regions has important implications for surface temperature, but also many of these other factors that influence people around the world. So one of the interesting features of the Arctic in particular is that the Arctic surface in winter tends to be either cooling very fast or holding its temperature. And there isn't a whole lot of in between. So the plot that I have on this slide is a histogram, which meaning it's counting how many times a variable is in a particular state. And the variable that we're looking at here is the surface energy balance, which I've spoken of a couple of times. So this is the amount of energy that's flowing into or out of the surface. So points on the left-hand side of this plot indicate that the surface is cooling, and on the right-hand side that the surface is maintaining temperature. So remember, this is winter, so asking for the surface to actually be heating up over time is kind of a big ask when there's no sunlight. So instead, when we talk about warming happening in this season, what we usually mean is that it's failing to cool. And one of the things that we notice about this feature is that instead of having a sort of nice, smooth, symmetrical distribution, there are these two kind of camel humps. And that's a really distinctive feature, not only of this site where the data is taken in North Slope of Alaska, but many, many sites across the Arctic over both land and sea ice and near kind of the edge of these sea ice regions, is that you have these sort of two preferred states of surface energy. And that's why you get these two big humps in the histogram, where the Arctic climate tends to be sitting in either the surface cooling or the maintaining temperature state and doesn't spend a whole lot of time in between the two. Now, this has a couple of really important implications for the Arctic climate. One of them is that the average condition is not necessarily the typical conditions. So the average condition might have a surface energy balance of about -30 on this plot, but you'll notice that it's actually much more common to have lower than -40 or around -10, and it's actually kind of infrequent for the state to be in its average state. This also means that small changes to the occurrence of either of those two states on the far end can really swing the average towards one side or the other. So if the Arctic starts to spend a lot more time in this surface cooling state, then that can really strongly pull the average to one side and can affect the sort of energy balance over the course of the entire season. So this feature means that trying to understand what causes the surface to be in one state or the other could help us to get a really solid understanding of what's going on with the energy budget over the course of the entire season. And the sort of key takeaway, if you don't learn anything else from this talk, is that clouds are what determine which of these surface states the Arctic is in. So here I've taken that same histogram, but now split it in terms of whether or not it corresponds to cloudy conditions or clear sky conditions. And here you start to see a really clear separation where the surface is able to maintain temperature most of the time if there are clouds overhead, whereas it tends to be cooling really quickly if there are no clouds in the gold. So this is motivating us to look a little bit more closely at what it is that clouds are doing that is able to keep the surface at its own temperature instead of cooling in the winter. So how is this accomplished? In order to understand that, we need to learn a little bit more about how clouds themselves work. So I thought I'd start from the very beginning, which is that clouds are suspensions of liquid droplets or ice crystals in air. Now these droplets are tiny, tiny, tiny. They're about the width of a human hair, sometimes even smaller than that for typical liquid cloud droplets. And in order for the cloud to hold itself up in the sky, that happens because these droplets are so small that as they fall, the friction from the air moving against them causes them to fall at less than a centimeter a second. It's so slow that even very small puffs of air are able to hold those liquid droplets aloft. And so in order for the water to fall out of the cloud as rain, you need to collect many, many of these droplets together until you have a much larger raindrop, which is now able to fall fast enough that it can overcome that air friction. And for a raindrop to be large enough to do that in a typical cloud, it needs to collect 15,000 of these small cloud droplets. So many of the processes that influence how these droplets are interacting with each other and merging or growing by vapor deposition are really important for understanding how long-lived clouds are. It's also important to know that clouds actually need two things in order to form. One of them is water, but the other is aerosols. So the water might be a little bit more familiar to you. The air has to be saturated, meaning the humidity has to be very high in order for the water to condense out. If the saturation is not high enough, then the water prefers to be in the vapor state instead of the liquid state, and it will just continue to exist as vapor. So often this means that you need air to be rising or to be cooling in order to reach saturation and start to condense. But the other trickier part that I think is less intuitive is that, especially for clouds, you also need aerosols. Aerosols are tiny particles, usually microscopic, floating around in the atmosphere. They can be composed of a variety of different materials. Some of the naturally occurring aerosols include dusts, pollens, smoke from wildfires, sea spray even, so some of the salts and minerals get thrown into the atmosphere when waves break. There are also anthropogenic aerosols, including some that are formed through chemical reactions in the atmosphere from components that start in the gas phase but react to become solid particles. And the really crucial thing about this is that whereas if you had like a bulk of water, like a lake, it's very easy for the water to exchange in and out of the gas phase and the liquid phase. But if you're talking about a tiny, tiny particle, there's actually an energy barrier to first forming that particle. And so the water needs a little bit of help to start to condense into a liquid droplet. And aerosols come in to provide that help. They provide a surface that the water is able to condense onto and then very quickly grow. So in this little graphic here, I'm showing the starting aerosol particle that forms a thin film of water. And once that water is there, additional vapor is able to condense onto this particle and it can grow. But you really need the aerosols there in the first place to help the water overcome this energy barrier and form into droplets. So if you're missing either of these components, the water or the aerosol, then it's very difficult to form clouds. Now we get into my favorite part of cloud, which is supercooled liquid. These types of clouds occur when the liquid droplets continue to exist even well below freezing. So to understand how this can happen, we might want to think about what could be preventing the liquid from freezing. So the first component is that when liquid freezes, it actually releases heat because it had a lot of energy in the gas stage and it loses some of that energy when it goes into the liquid state. It has to lose even more to solidify into the ice phase. And on a large scale in something like a lake, it's very easy for a large mass of water to move that heat away from the freezing front and dissipate it maybe into the atmosphere, maybe mix it further out down into the water. But if you're talking about a tiny cloud droplet, it becomes very difficult for that droplet to release the heat. So the heat that's released by the freezing of the water actually prevents the rest of the droplet from freezing. The other thing is that ice requires a different type of aerosol than liquid does. Many of the aerosols that exist in the atmosphere can condense out liquid, but because ice has this very specific crystalline structure, you often need some sort of mimicry of that structure on the surface of the aerosol in order to help it overcome that initial barrier to crystallization. And that means that while you might have hundreds or even thousands of these cloud nuclei, the aerosols that form liquid droplets in a given liter of air, it's not uncommon to have one or even less than one of the ice-forming particles in the air. So it's much harder for a cloud to form ice than it is to form liquid. And one of the implications of this is that in these cold regions, you often have liquid clouds existing down to -20 or even -30 degrees Celsius below freezing. So these clouds end up being really important for the climate. And it's very difficult for us to even form some of the basic theory around exactly how these two factors of the heat release during freezing and the specific aerosol presence being there can influence cloud formation. So as I mentioned, clouds can be either liquid or ice, but as it turns out, the liquid clouds are the ones that have a much bigger impact on the surface heating. So I included here some visual examples. You can often tell if a cloud is liquid or ice just by looking at it. Liquid clouds are on the left. They tend to be these puffier, thicker clouds. They're very bright white. They often have these more defined kind of edges. They look kind of like the cartoon cloud that you might see or draw. These clouds have many, many, many cloud liquid droplets that are all very tiny. But because there are so many of them, there are many opportunities for them to interact with the heat that's trying to escape the surface of the Earth. So that heat is traveling up through the atmosphere, and when it interacts with a liquid cloud, there's so many liquid droplets present that a lot of that heat gets absorbed and re-emitted back to the surface, and that helps to heat the surface up. Ice clouds, on the other hand, tend to be very thin and wispy. A lot of sunlight tends to come through them, and this is because there are so few of those ice-forming aerosols that unlike liquid clouds, in ice clouds, you tend to have a small number of much larger particles. And because there are so few of them, it's a lot more likely that heat escaping from the surface is just going to go straight through the cloud without interacting with one of the ice particles. So if you want to have a cloud that's really good at trapping heat near the surface, you really want it to be a liquid cloud. Now, I'll point out here that clouds can also cool the surface, especially liquid clouds, because they shade it from sunlight and reflect that sunlight back into space. But one of the things that's so interesting about supercooled clouds in the Arctic is that because the sunlight is not there at all in the winter, and even in the warmer seasons, the sun angle is very low, this cooling effect from clouds tends to be very small. And so the Arctic is one of the regions where the heating effect from the cloud is able to take over, and you actually see a net heating from cloud presence. Clouds are actually really common, even in Arctic winter, and even liquid clouds, partly because of these challenges of forming ice. So here we're going back to some of the data from the North Slope of Alaska. And if we consider all of the winter days in our entire 20-year data set as this gray bar, then we tend to have cloudy conditions about 70% of the time. The Arctic is actually a very cloudy region. And about 30 to 60% of the time, you tend to also specifically have liquid clouds. Now, some of the range of that, the 30 to 60%, has to do with the different instruments that are available at this site. So depending on exactly what I consider to be a liquid cloud, I might get a slightly different number. And this is actually, I think, one of the huge benefits of using this location is that it helps us to really narrow down on this question of like, what exactly do you mean by we detected liquid here? Is it that you detected with one instrument that there's some liquid somewhere in the atmosphere? Is it that you had an instrument that actually traveled through the atmosphere and can tell you exactly where that liquid is? So it's really helpful to be able to start to understand what leads to some of the uncertainty and exactly what the liquid cloud fraction is. But regardless, even in winter, even in the Arctic, when it's freezing, freezing cold, almost always below freezing, you still have liquid clouds overhead about half the time. And those are going to have big impact on the surface. So now we're going to revisit this idea of the surface energy balance in terms of the importance of liquid clouds. So supercooled liquid clouds are really the ones that are helping to prevent the surface from cooling in winter and contributing to Arctic amplification. So one of the things I didn't mention when I first showed you this plot is that this blue peak of the cloudy conditions is actually mostly from liquid clouds. If you separate the liquid from the ice clouds, most of the ice clouds are what makes up that sort of extra edge of the peak on the colder side of this distribution. And it's really the liquid in the clouds that's responsible for keeping that surface warm. It's also interesting to note, and this is an early result that I have from the research I'm doing right now, that temperature alone is actually not enough to explain whether the cloud turns out to be liquid or ice. So here we have some measurements from about 15 years at North Slope of Alaska of the temperature and humidity at the level of the cloud. So this dashed line is just showing you where the water is saturated. So we expect most of these values to fall along the dashed line. And you'll notice that the temperatures run from about -40 Celsius to 0 Celsius. So this is all below freezing, and this is all observation. So we haven't yet restricted to liquid versus ice clouds. Now, on first thought, we might assume that the closer you are to freezing, so the warmer the temperature is, you might get more liquid, whereas at colder temperatures, you would get less liquid. And that would look like this. Our high liquid water path, which measures how much liquid is in the cloud, would be on the right and upper end of this plot, indicating warmer and wetter conditions, and our very low liquid content in gray would be at the lower left-hand side. But what we actually found was that these liquid contents are almost all stacked right on top of each other. So if you look at this plot along the top, so this is just pushing the whole distribution onto the top here, we see that, yes, you're more likely to get these low liquid clouds at cold temperatures, and you're more likely to get the high liquid clouds at warmer temperatures. But there's also this really interesting region in the middle where you're almost equally likely to get any liquid content in that temperature range. And this is one of the areas that we're really interested in studying more, because what we want to understand is climate change going to increase the occurrence of these liquid clouds? Because that would indicate that they might start to really help to keep the surface a lot warmer and even accelerate Arctic amplification. However, if factors other than temperature are important in determining the liquid in clouds, then we might find that this effect would be less strong than we might expect as the climate gets warmer. So the next thing that we have to do is really get into understanding what are all of the factors that influence the amount of liquid in clouds in the Arctic. So where do we go from here? This leaves us with a number of questions that I'm working on answering right now. One of them is, as I mentioned, which factors other than temperature are helping to determine how much of a cloud is liquid? Another is what types of clouds have the biggest impact on surface temperature over their lifetime? Here I'll point out that this is a project that I had planned to do with an undergraduate who is going to come and work with me as part of an NSF research experience for undergraduates. And this question is currently on hold because that grant was terminated a couple of months ago. So unfortunately, I don't know when I'm going to be able to pursue that question again. But at this point, I would be happy to take any questions that people have, and I encourage you to email me if you'd prefer to do that rather than posting in the chat here. And I hope you enjoyed the talk.
Okay, great. Thank you very much. That was really interesting, and I saw some people commenting on the chat that this was like one of their favorite talks that they've seen. Really getting into it. And you actually answered some questions that people had earlier later on.
Great.
But sort of going back to the beginning when you were talking about the observatory, how big is the team at the observatory?
It depends a lot on the season. So over winter, when it's not as pleasant to be staying in this very remote location and managing these instruments, I believe it's just a handful of people. In the summer, in addition to having more on-site staff, you might also have people who are visiting to work there temporarily. So for example, one option for me potentially would be to try and find an opportunity to go there in person and be able to actually talk to some of the people who maintain these instruments about some of the uncertainties. I would then also be able to compare some of my just like visual observations of what's going on in the sky with what the instrument is telling me the clouds are like. And that can help me to develop an intuition for what types of questions I think are interesting. So I think it varies a lot. I think you probably wouldn't get more than maybe a couple dozen people there in like the summer nicer seasons. And it can go down to just a couple in the winter, which I think really emphasizes how crucial those handful of technicians can be.
Related to that, actually, there was someone who was asking how winter days were identified in your work. Were you identifying by sun angle or something else?
I like that question. It's an interesting one. At the moment, I am just using dates. So all of the data that I have is time-stamped, which means it has the date and the time that it was taken attached to it. So right now, what I'm doing is restricting to what I call an extended winter, which is from the beginning of November to the end of March. I just pull out that chunk from every year. The reason I do extended is because if you look at the seasonal cycle in the poles, what you tend to have is a really long winter and a really long summer with very short spring and fall. And that's because the sun angle changes very rapidly in the spring and fall. And so if you want to, you can push out the winter a little bit further than what I would consider winter where I live, for example, in Colorado. Because it's so much further north. So right now I use dates. I think if we were interested in looking at things like the influence of sun angle on clouds and radiation, then I would probably do an explicit calculation for what angle the sun is at and choose based on that.
Great, thanks. Maybe you have time for one or two more questions. Oh my goodness, there are a whole bunch now. Let's see. Talking about the instrumentation a bit more, the surface temperatures that you have used, is that a specific point or multiple points? And then what sort of sensor is being used?
This is a great question. So there are a number of different ways that surface temperature is measured at this particular location. There is an instrument which is specifically for what are considered kind of basic meteorological variables. I don't know the name or the make of the specific instrument. The data that I am currently using for those variables is what's called a blended product, which means it might be using measurements from multiple different temperature stations, all very close to each other, to do things to like cover periods when one of the instruments was down, maybe had an equipment failure or a power failure, or to sort of validate across the set of them. Maybe one of your instruments is biased because it's more exposed to sunlight, or in the winter it gets covered in a snowdrift, and so then you can't trust it as much. So the products that I use for most of these measurements are these kind of blended products where it uses multiple air measurements. So the one right here is using the surface temperature from 2 meters, which is about 6 feet above the surface. And for those, typically you'll have what's called a meteorological tower where they've attached instruments at various heights to take those kinds of measurements.
Okay, and we're running out of time, but really quickly, so you mentioned near the end talking about, so what's going to happen in the future? And so there was a question about rising temperatures and increased pollution, more humidity, more aerosols, more liquid clouds, more amplification. Do you have a feeling sort of how this is going to go? You mentioned there was some uncertainty here, but do you have a...
I suspect, and we have to be very clear that I'm going into speculation here, that what we're going to see is some of a sort of sloshing of this camel hump distribution, where you start to see fewer of these clear sky days because they're shifting over into this cloudy state. Part of the reason that I think that could also happen is that after liquid clouds, the next factor that strongly influences the surface energy is actually how much water vapor is in the air. So water vapor itself is a pretty strong greenhouse gas. And so even if you're not forming clouds and it's technically clear, if you have a lot of water vapor in the air, it's still going to have a strong warming impact on the surface. And so I think the combination of the possibility that you would see more frequent or even thicker liquid clouds as a result of climate change, which also, as sea ice retreats, is going to introduce additional moisture into the atmosphere that's currently keep staying trapped in the ocean under ice. So you'll have increased temperatures and increased moisture. It's very likely that that will give you more and thicker liquid clouds, but it also means that even your clear sky state could get a little bit warmer. I think the main question is that going to accelerate? Is that going to mean that our Arctic amplification factor gets even larger than it currently is, or is it going to sort of track with the current value? And that I don't think we understand enough to even speculate about yet, but it's one of the things that I'm interested in understanding further. I think that's a major motivation for the work that I do.
Yeah, that sounds really important. Well, thank you a lot, Kara, for joining us. And yeah, unfortunately, couldn't get to all of the questions, but really enjoyed your talk. And yeah, follow up with her if you have more questions.
Yeah, thanks so much for having me. I'll try to answer some of the comments before I leave if I get the chance.
Okay, great. Okay, so we are still, we're in the second half now of hour 60 of the Weather and Climate live stream. So about 40 hours left to go. We have another great talk coming up by Alyssa, who's going to talk about hurricane rainfall. But before we get to that, we want to remind you of why we are all here. So you're here because you know how important weather and climate forecasts are to protecting our lives and livelihoods. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts to help you know what to expect in the coming days. And we made the first computer models of climate impacts of carbon pollution so you can know what to expect in the decades to come. To make this all work, we have to have lots of observations. And so we've developed this extensive network of weather stations and planes and satellites and balloons and boats and floats. And you've heard about a lot of those in the talks these past couple of days. The result of all of this is really more than the sum of the parts. It's really a scientific miracle. And we're so excited that we can share the science with you. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk. And funding for our basic understanding of weather and climate is disappearing. And we're losing a generation of scientists as undergraduate students or graduate students and postdocs, other early career scientists are not able to get the funding they need in order to get the training and education to become scientists and study weather and climate themselves. It doesn't have to be this way. If you like what you see, then we ask you to please use the link on your screen, which should be going by in a second here. Contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word about this live stream. Either way, we hope you learned something about weather and climate, and please feel free to ask us any questions about our science in the chat. And so for the final session of my hosting duties here, we're going to have Alyssa Stansfield, who will be talking about hurricane rainfall and climate change. Oh, sorry, Stansfield, I'm sorry, my handwriting's bad. Before she gets started, I want to just remind everyone that the views that she expresses and that I express are our own and not institutions that we work for. And so with that, go ahead and take it away, Alyssa.
Awesome. Thank you so much, Karen. And I just want to say I noticed your cloud earrings and I really love those. So hi, everyone. Thanks for tuning in. I'm super excited to talk some science with you tonight. So my name's Alyssa. I am in the Department of Atmospheric Sciences at the University of Utah. But again, this talk represents my own opinions, not the opinions of my employer. So I'm going to talk about how hurricane rainfall is impacted by climate change, which is what I have researched during my PhD and postdoc. So I think weather and climate people are really interesting because a lot of us have a story of how we got interested in doing weather and climate science. So I'm going to briefly tell you about mine. So why do I study atmospheric science? I was born and grew up in New Jersey, right near the ocean. And New Jersey experiences a lot of crazy weather, but maybe you guessed from the title of my talk that the reason I study atmospheric science is because of a hurricane. And so Hurricane Sandy hit New Jersey in 2012, and that was my senior year of high school. And so at the time, I was really thinking about what I wanted to major in college. And Hurricane Sandy was a super impactful storm. A lot of flooding that lasted many weeks afterwards. And it was also a really big storm, as you can see from this satellite image. The clouds at one point spread all the way from Florida to the Northeast. What also was unique about Hurricane Sandy was this shows its track here, was this abrupt left turn it took into New Jersey, where unfortunately the impacts killed about 233 people and cost $75 billion in 2012 dollars. At the time, this was the second costliest hurricane to hit the US. However, it has dropped down quite a few tiers in that time. So here's a picture of some flooding from Hurricane Sandy. That was its main impact. And I just have specific, images I can still bring up my mind of places I grew up that were completely flooded. There were like boats left on people's front yards, and people lost homes. And when you see like devastation like that in the place you grew up in, I think it really makes an impact on you. So that's why I went to school to study weather, and ultimately in grad school study hurricanes. So many people don't know that water is actually the most dangerous part of hurricane landfalls, because hurricanes are usually ranked by their wind speed, right? Category 1, Category 2, that's ranked by wind speed. However, 88% of deaths from hurricane landfalls in the US are actually from water hazards. So mostly storm surge and flooding from rainfall. So the most recent example of this was probably Hurricane Helene this past year in 2024. It devastated many areas, including especially Western North Carolina. And that was just because partially it dropped so much rain. So here's a map of the rain from NOAA. And so the maximum rainfall was 30 inches in 4 days. So that is a lot of water coming from the sky. And you can see it dropped, over 10 inches over a very large area. And that's a very rare amount of rain, even for the East Coast or the Eastern US, which does get a lot of rain. So this map shows you the chance of exceeding observed rainfall in an average year. So that like black area right near Asheville there means that in any given year, there's a 1 in 1,000 chance of exceeding that rainfall total that point saw. So just to say, this was an extremely rare climate event, rainfall event that happened, unfortunately. And there's a couple reasons that Hurricane Helene was so impactful and why it caused so much flooding. One was because there were these predecessor rain events that happened before the storm. So Hurricane Helene's circulation actually was pushing all this water in the air towards North Carolina in the days before. So they were already getting a lot of rain leading up to Helene. Another was the impact of the mountains. So this is a very mountainous area. As the air gets pushed up over the mountains, that actually produces more rainfall as the air gets pushed up. And then 3, it was just a lot of rainfall, as I just showed from that map. I think anywhere that gets 30 inches of rainfall in like 4 days is probably going to flood. And so Hurricane Helene, again, unfortunately, very impactful, over 250 deaths, mostly in North Carolina. This was the most deaths in the US from a hurricane since Hurricane Katrina in 2005. It also cost an estimated total of $78.7 billion. And I think costs are still coming in because, unfortunately, a lot of areas are still recovering. And so the goals of hurricane rainfall research, or at least I guess my goals, is to ultimately prevent deaths and injuries from hurricane rainfall. And so we can do that many ways. One, we want to improve the hurricane track intensity, rainfall, and flood forecasts. We want to understand the role of the preceding soil conditions in flooding. As I said, North Carolina got a lot of rainfall before Helene, and that made the soil already be like saturated with water, so it couldn't like take any more water by the time Hurricane Helene moved over the area and was dumping rainfall. And then also this third goal, which is what I focus on the most, is to predict how and why hurricane rainfall is changing due to climate change. And so putting together all of these goals, we can kind of link these to actual societal impacts of trying to get more accurate and earlier warnings and evacuations for hurricane landfalls, and also hopefully improve infrastructure so we're more prepared for the floods of the future. And I'll just note that not only do we need the weather and climate research, but to really translate this to societal improvements, we need all kinds of different professions, engineers, social scientists, emergency managers, and a lot of this kind of funding for bridging these gaps and doing this interdisciplinary work does often come from federal sources. So that's just one way that federal funded money is really important for this type of work. So how do hurricanes actually produce rainfall? Well, so as we know, hurricanes spin. And so in the Northern Hemisphere where we are, in the US, they spin counterclockwise. So if you were to see a satellite image of a hurricane, it would be spinning. But actually for hurricane rainfall, the more important ways hurricanes spin is kind of through this other circulation that happens. So here we have this cross section through a typical hurricane. So you have the eye in the center, and that's that area where there's not a lot of, or no rain, no clouds. You can kind of see right through the hurricane. The eye wall is right next to the eye. That's where the heaviest rain and the strongest wind speeds are. And then there are rain bands outside this center area that can also produce a lot of rain. And so this secondary circulation, or it's often called the in, up, and out circulation, has wind and air being sucked in towards the center of the storm, and then it goes up in the eye wall or in these rain bands, and then it goes out again at the top of the storm, which produces these like very thin clouds you see kind of above the hurricane. And so at the bottom section here, as the air is sucked in towards the hurricane center, it's passing over the ocean. And so water is evaporated from the ocean into the air. Then when that air reaches the rain bands or the eye wall, it gets moved upwards, and that air cools, the water vapor condenses into clouds, and then the clouds produce rain. The presentation before me, Kara did an amazing job explaining how rain actually forms in clouds. So I hope you guys were able to see that because it was a great presentation. So that's kind of the basic understanding of how do hurricanes produce rainfall. It's pretty simple. So how does climate change impact this process? One way is that the ocean is getting warmer. And as the ocean gets warmer, it's actually easier for water to evaporate from the ocean into the atmosphere. As the atmosphere gets warmer, it can actually hold more water vapor in it. And as we know, the water vapor in the air is what turns into clouds and then turns into rain. So more like potential rainfall. So you can kind of think of the atmosphere as like a sponge. This is not an analogy I made up. Many people have used this before. And so the atmosphere is like a sponge. It holds water in it. And when a hurricane comes through, it kind of squeezes the sponge out and makes rainfall. So without climate change, you have this sponge. With climate change, the sponge gets bigger. It can hold more water. The last aspect is that hurricanes are becoming more intense. So this upward motion in the hurricanes becomes stronger. And remember, the upward motion is really what drives that heavy rainfall. So given all these factors, we know that climate change overall is increasing hurricane rainfall. And this is backed up by many, many studies, both observations and models. I just put one figure up here from this paper from 2020 that shows this increasing trend in hurricane rainfall over time. I will note that this study used NASA satellite data. And so this is another way federal funding is really important. We need these sustained satellite observations to understand the climate trends that are going on. And so we really need that sustained funding. And so a research question I focused on during my PhD was, which contributes more to increasing rainfall from hurricanes with climate change? Is it more the increasing moisture in the atmosphere because the atmosphere is getting warmer? Or is it in the increase in the storm intensity and that upward motion? So unfortunately, we don't really have observations with like high enough detail, like inside a hurricane, or really long enough observations to answer this question. And so that's why we like to use climate models, because they allow us to perform experiments on the Earth system and understand fundamental physical processes. We can't really, perform experiments on the entire Earth. It's too big. So we need our climate models. So here's the real Earth. And we can represent the Earth using this realistic climate model simulation that basically represents the atmosphere and the ocean using these physical equations. But then we can also have some fun and create some idealized model simulations. So for my simulations, I got rid of all the land and I made a warm ocean covering the entire planet. And what this does is basically creates a planet that is ideal for hurricanes. And so this is not a planet I don't think any of us would want to live on because it is covered with hurricanes. So all of these little dots here, this is showing a snapshot of time in my simulation. The pole is up here on the top and the equator's down here. And all of these little dots here are actually hurricanes. So they form in the tropics where they usually do on the real Earth. And then they move towards the pole and they actually kind of gather up around here and spin around and die out. And so this is good for me because I have lots of hurricanes to analyze. This is a very simple world. There's not a lot of complicating factors. And also I can increase the ocean temperature in these simulations very easily to see how the hurricanes respond. So kind of like a simple climate change analog. And so here are 3 examples of the hurricanes in the simulation. So this is hurricane rainfall if you're like looking from above, kind of composited over thousands of hurricanes. And so the SST sea surface temperature, so the ocean temperature is about 71 on the left here, and then all the way on the right, I increased it to 89. So really, really warm. And so you can see just based on the more warm colors in these plots, the rainfall in these hurricanes increases a lot as the ocean temperature increases. And so that's what we would expect. But what I was able to do was decompose this rainfall increase into the increase from the higher hurricane intensities. So I didn't show this, but as the ocean temperature warmed, the hurricanes also reached higher intensities. So I decomposed the rainfall increase into the increase from higher intensities, and that's the purpley pink here. About 20% of the increase was from the intensities, but the large majority was the light green, was just the increase from the increase in the atmospheric moisture as the air warmed. And there were a couple other small factors, but again, the large majority was just from that increase in atmospheric moisture with the warmer air. And so why does this matter? So again, we found this over 2/3 of hurricane rainfall increase in my model simulations came from just the increase in atmospheric moisture as the ocean was warmed. And so thinking about the real world, this would mean that as long as Earth continues to warm, hurricane rainfall is going to continue to increase no matter if hurricane intensities increase or not. And so therefore, this kind of implies that the flood risk will also continue to increase. So again, these are model simulations. So I'm still doing work now to understand more about how accurate this is for the real world. But I think this is something to take very seriously and understand that, unfortunately, as the climate continues to warm, hurricane rainfall is going to continue to increase, and we really need to prepare for the floods from that. So finally, I'll wrap up with a little bit about how federal funding has helped my career. So I was funded a lot during my PhD work from the Department of Energy. And then I got a National Science Foundation postdoctoral research fellowship. So that funded all of my postdoc. And I also was a participant in the 2016 undergraduate leadership workshop at the National Center for Atmospheric Research. And so this program brings undergraduates from across the country to NCAR in Colorado for a week. And we get to meet scientists there and see the lab and understand what kind of doing atmospheric research means. I got to see their aircraft, the C-130, and sit inside it, which was really cool. And so that was funded by NSF. And these are the things that I am very afraid are going to go away if NSF funding is severely cut. These are really great ways to get people interested in our field. And they're really impactful experiences for a lot of people. And I really see federal science funding as an investment in the future of the US and the world. I didn't do an REU, a research experiences for undergrads, but these are also funded by NSF, and they are a great way that a lot of people get into not only our field of weather and climate, but all science fields and engineering. And so again, unfortunately, a lot of REU programs across the country got canceled this year because they were their funding was terminated early, or they weren't sure if they were going to get the funding from NSF, so they could not run them. Another great resource that's NSF funded is called the METED website. And so this is totally free, like meteorology lessons. So if you really love learning about meteorology, please go to this website, and you just have to register. It's all free. You can learn so much about atmospheric science and climate and weather. And then finally, my last point is that I am a new professor at the University of Utah. And so in order to pay graduate students to work for me and complete research, I need grant funding. And, you know, these students aren't just going to work for me. They're going to learn to do research, and they're going to go out into the world and produce more research. They're going to work in the private sector, hopefully change the world in many ways, and do a lot more things. So we really need this federal funding to continue so we can continue to keep the science enterprise going in the United States. So that's all I'll say. And I would love to answer some questions if we have any.
Okay, great. Yes, we have a bunch of questions here. First, I want to say, you know, your very low bar goal of saving people's lives. That's you know, it really emphasizes the importance of this sort of research. And for those of you who didn't see Jeff Masters' talk, which was in the previous, before we switched to this new live stream, if you can still go back and watch it, it's just a riveting account of flying into a hurricane, a Category 5 hurricane. That this is just an amazing experience there. So a couple questions here. Sydney asked about ground accumulation, whether that is something that could be used to indicate the amount of rain that you got in a hurricane.
Yeah, so just like the amount of rainfall, I guess.
Yeah.
Yeah, so that's typically how we measure. Kind of that's what I was showing for Hurricane Helene, is just like how much rainfall accumulated in a certain location over the 4 days or whatever that they were getting rainfall. So that's kind of the typical way that we measure how much rainfall is impacted or is created by the hurricane. So yeah, for Hurricane Helene, for example, that was one location had a rain gauge and it had 30 inches of rain in 4 days. That's a lot.
Let's see, another question. Do we have any cool new models that help predict rapid intensification a little better? Ever since Otis, I've been interested to see what we're cooking.
Yeah, that's a great question. So rapid intensification, which is where a hurricane rapidly intensifies. There's a specific threshold for it. I can't really remember it off the top of my head, but yeah, our hurricane forecast models unfortunately have a really tough time capturing and forecasting rapid intensification. It's getting better, but it's a big focus of the National Hurricane Center and the research arm of the National Hurricane Center, which is funded by NOAA. right now. They are working on improving their model. And they are also working on finding new observations to assimilate into the model. So that means when we're taking observations and we're basically putting them into the model as often as we can, and that helps us make better forecasts. And so they are constantly trying to think of new ways to assimilate the observations in the models. What other observations can we use? I actually just went to a graduate student's defense in my department a few days ago who was talking about assimilating like the newest NASA satellite observations into this hurricane model. So definitely still a challenge in hurricane forecasting, but there are a lot of people working on it. And as I said, we need this research to continue because I really think it has a lot of potential.
Okay, and this may be a difficult question. It is so disheartening to see science funding disappear, especially as someone planning to go into botany or ecology. Any advice to students planning to go into science right now?
Yeah, I totally sympathize. I think everyone feels your pain. And I would say, don't change your mind. Like, still go into science, follow what you're passionate in, because there are so many people that are willing to help you. So I know, as a professor, like, I don't want to see less people going into meteorology. I still want students to come in and we want to teach you. And I think there are a lot of different career paths opening up right now for scientists, because scientists gain a lot of transferable skills no matter what exact major you're doing. So you gain not only like math skills, but statistics and critical thinking and communication, a lot of like data science and computing and stuff all kind of go into a science degree. And so those skills are extremely transferable to so many different careers. So I think that's one thing is that, but everything is temporary. And I'm definitely hoping that this kind of hard time for science is also temporary. And I think it will be. I'm going to stay positive. So I really encourage you to try to stay positive, focus on what you really love and why you love doing it. And just persevere.
Okay, great. Thank you very much. And I think we are ready to switch over to our next speaker and our next host. So thank you, Alyssa, and really enjoyed your talk. And I am signing off now and passing you on to Nick, I guess.
Well, awesome. Thanks, Karen. Thanks, Alyssa, for a great talk. And we've pushed over into hour 60 of the 100-hour live stream. So, 60% of the way there. All right, so welcome to the graveyard shift. I'll be with you guys to the early morning Eastern time. And before we get started, I just want to remind everyone why we're here. There are a lot of proposed cuts to weather and climate research in the U.S., and we're hoping to raise awareness of this and to show people both the awesome research that's being carried out right now, including the many amazing early career researchers. I mean, so many of the great presentations have been given by grad students, postdocs, people just starting faculty positions. And the best way that you can support this research and these activities are to watch the stream, to ask great questions, and to call your representatives. So you can see on the banner going down at the bottom of the screen, there's a link to a website where you can has more information about how you can call your representatives and the message that we would like you to communicate to them. We've already had over 6,000 calls placed to Congress as a result of this live stream. We're into hour 61, so maybe we'll get up to 10,000 calls at current pace. So, okay, with that, let's move on to our next speaker. So since we're getting late into the night, we're going to start getting a little weird. And we're going to have a talk from Michael Battalio, who's an early career planetary climate scientist. So we're going to move off Earth, I think, a little bit and study Mars.
Well, hello, everyone. Thanks, Nick, for that introduction. Thank you for hosting the Great Night Shift. Thanks all of you for being here. I can see on the YouTube channel there are almost 500 of you still hanging in there. Thanks for being with us. I want to reiterate what Nick said. I would much rather you go to wclivestream.com/act and call your congresspeople right now instead of listen to me. Keep me on in the background, but much more important to call your congressperson. Did you call yesterday? Great. It's a new day. Call again today, at least here on the East Coast. So thanks again also to the early career people for doing this. You've done a fantastic job. I've checked in every once in a while when I've not been busy and tried to catch up on talks. Just an absolutely fabulous job. The community is proud of all of you postdocs and students for doing this. Thank you so much on behalf of everyone, from someone kind of later in the early career. So I'm a planetary scientist. I started off doing atmospheric science. I've kind of gone over to the planetary side, and I want to talk about how the US government funds my planetary research, but we're not just looking at faraway planets. We're also helping to understand Earth as well. And I want to kind of connect NASA's research throughout the solar system to better understanding Earth. So I've liked something that a lot of people have done so far, which is give a little taste of the personality of the people behind the science. So who am I? I'm an associate research scientist. I'm not a professor. I'm graduated in 2017, but there's always some luck that's involved in getting to be a professor, and I just haven't hit it yet. So I'm fully self-supported. I raise all of the funds that I need for my salary myself. But I was born and raised in Mississippi, Vicksburg. Yes, the big Civil War battle. Yes, family and I went to the National Military Park lots of times. 3 times Bachelor of Science and a master's degree at MSU, Mississippi State. A fun tidbit about me is that, see that little arrow down at the bottom? That's me conducting the famous Maroon Band. That's the 350 something odd marching band from Mississippi State University. Here I am conducting the patriotic show right around Veterans Day. I think this was 2009 when I was an undergraduate still, and there's me in front of 60,000 of my friends and conducting 600 people on the field. Big rush. I miss it still every once in a while. I've also kind of included, here is my tiny lap polar bear, Bennett, sitting with me. You'll hear him barking, I'm sure, at a leaf falling in the next county over, intermittently over the next 30 minutes. So listen for that. After Mississippi, I went and got my PhD from Texas A&M in atmospheric science. And among all those other things, I'm an avid gardener and a classically trained pianist and cellist. So I do want to hit on and really push on, first of all, how important science funding is to me, and not just to me, but to everyone. So science funding is more than just research. Science funding is fundamentally a jobs program. Hundreds of thousands of people are funded by the US government to do cool science for all of you, the US taxpayers, to work and contribute to the economy. Not only that, science is a technology program. Inventions like the cell camera, global positioning system, magnetic resonance imaging, air purifiers, on and on and on and on. Cool things are invented because we do cool science here in the US, paid for by all of you. Science funding is also, it's a national security program. When we discover cool things, we can help protect the rest of our fellow citizens from threats, both inside and without. We protect ourselves by advancing our technology. And in doing our science, we attract the smartest people in the world to come here to do science and to do research at our world-renowned higher education. Then they go back out and tell everyone how great the United States is. We want to keep doing that. We want to accelerate that, not cut funding. Finally, science is at its most fundamental, inspirational. From whether or not you're a small child or an adult, you really can inspire awe and amazement at how wonderful the world that we live in is. You, the taxpayers, through the US government, pay for that. So on behalf of all of us, thank you so much for doing that. However, also you're welcome, because every aspect of your life, of every person, watching on this live stream has been touched and improved by the science research that you have paid for. Thank you, but also you're welcome. So I want to talk about how I do my science, where I get my money from. So again, I'm an associate research scientist. I'm all soft money. 100% of my money comes from grant funding that I write, apply, and win grants that provide my salary and my health insurance and my spouse's health insurance as well. My institution, I've deliberately not named where I am now. It's somewhere famous, but it's immaterial where I am because I bring all of my money in externally. My institution doesn't actually provide me any salary. They take a little bit off the top to help manage the money and do some of the paperwork, and then also provide me facilities and computational resources. But I bring all of that money in for both of us. That's not to say I back my truck up to the back of Fort Knox and to the free money booth, and it's just dumped in. No. Writing grants is hard. It's a lot harder than you think, because even when times are not tough, even before any of the proposed cuts of the budget that was released earlier today happen, and hopefully they don't, again, call your Congress people if you haven't already, funding rates are like 10 to 25%. That does not mean that 90% of grants aren't good. For example, a few years ago, I wrote a proposal. It was scored 5 out of 5. NASA calls that literally an excellent proposal. It was excellent. But because they didn't have enough money, it wasn't funded. That's not my fault. That's not their fault. We underfund science. We should accelerate funding for science, not cut it. So on average, I have to write 10-ish grants. You practice it a lot. You don't have to write so many to get some successes. But you have to write like 10 grants to get one. And you need more than one at a time just to support yourself. So that's who I am, what I do, why you should fund science, and how I get my money. Why study other planets? Well, if you were watching the live stream with me when it first started some 61 hours ago, you'll remember that the very first talk, right before they kicked people out of the building at NASA GISS, it was motivated, the research at NASA GISS, by understanding that Venus's climate is a runaway greenhouse. So we looked at other planets to help others understand what's going on Earth. And that's what I do. So I study planetary weather and climate to understand impacts that we might face. For example, on Mars, we may not get a big snowstorm or fire, but we do get extreme weather on Mars. And I'll show you more examples of that in just a second. Cool dust storm movies in just a second. This image here on the right, Sol 1, 2, 1, 3, 5, 7, 9, 11. These are different time periods. A Sol is a Mars day following the start of the last global scale dust storm on Mars back in 2018. And I promise, it's hard to see. There's a little speck right there. That's the sun in the same spot as on Sol 1. In just 10 days, day literally becomes night on Mars. And this is work I did with Mark Lemon, my PhD advisor at Texas A&M. So we understand and look to other planets to help understand our planet. Right now, we are pushing the Earth's climate from equilibrium. We're all living in a grand experiment right now. So what I do is look at in-members, different types of climates that we have in the solar system to understand maybe not necessarily where we'll end up, but maybe some of the flavor of what we might experience, whether it's a runaway greenhouse on Venus, or drying like we see on Mars, or extreme weather like we see on Saturn's moon Titan. When we understand and look at all the different types of climates as best as we can throughout the solar system, we understand this continuum of all the possible climate regimes that there might be. So we can kind of better follow the trajectory that Earth might move as its climate changes. So that's why I study planetary science. All right. I promised you cool dust movies. Let's do it. So I'm showing 2 movies right now. On the left, I'm showing one movie, but the bottom frame is the natural movie, what you might see in the camera. This is from the surface of Mars. I'm the participating scientist. My grant was just renewed just last week. Yay. On MSL, which is in Gale Crater near the equator of Mars. This is a movie looking down the bottom of the basin. And this is just the raw movie, just images we took straight from Mars. And the top has been contrast enhanced, so you can see dust spreading up and over the rover from the surface. So dust storms begin locally. They don't just spontaneously erupt everywhere all at once. We can also see dust moving around above us as well. This is already a contrast enhanced movie. Here's the ground down here in case you can't make it out. But you can see individual fronts, just like clouds, gravity waves passing over you here on Earth. And this is dust and CO2 clouds on Mars. I'm actually going to be on operations on Monday, and we'll be taking movies just like this again and returning them to Earth on Tuesday. So storms begin locally, but they then grow and spread across some specific paths. So this is work I did a few years ago. I made a gigantic data set of all the dust storms that happen on Mars, and I'll have a QR code where everyone can go download this data set. After all of you paid for it as taxpayers. It's free to you. You paid for it. It's yours. You own it. So you can download it and use it to do whatever you want with it. And I'll have a QR code at the end for you to download it. So there's specific trajectories. Let me try and go back and rerun the little animation. So there's specific trajectories of storms in Mars's atmosphere. Just like on Earth, they start at the high latitude, so near the poles, and they go west to east. But unlike on Earth, sometimes they turn and go and cross the equator. And I'll show you a movie of that in a second.
Mike, sorry, since this is a graveyard shift, can we be a little more informal? There's a question in the chat.
Sure.
I think would be helpful is, what do the names represent?
The names are topography on Mars. So I was just about to say that Arcadia, Acidalia, and Utopia are basins on Mars. They're what would be oceans if there was still a lot of water on Mars. And then Tharsis and Arabia are mountain ranges on Mars. Hard to tell because there's no water, no big dividing lines, but Tharsis is about 20 kilometers higher than the lowest impact basin, which is Hellas down here. And the numbers show you the number of storms that have gone through each of those paths. So I want to piece all of this together now. Here are the same labels again. Sorry, Nick?
As the storms are moving down the paths that you showed, are they moving up and like up the topography or down the topography?
They're going around it. Yeah, good question. They're going around it. So here is a mountain right here. This is Tharsis again. This is Arabia right here again. And these are the storms going around it. So at first, they're confined to the high latitudes, and they're just kind of stuck up here, and they go around and around over and over and over again. And then the waves grow around the mountains and through the basins. You can see this one kind of spreading, and the bottom of it goes down here. This dark is one of the lowland channels. This is a mountain right here, and it's kind of being smushed and spread around it. So the second phase of these big storms growing is they kind of go around the mountains and head towards the tropics. Once they get a little bit further, they can cross the equator from the northern hemisphere to the southern hemisphere. And a typical behavior is what is shown here, where it goes from Utopia down to Hellas through this channel here. And once it gets into the southern hemisphere, really cool and weird things happen. This behavior, by the way, is called flushing from the northern hemisphere to the southern hemisphere. One of my postdoc advisors coined that name. After this, so I'm gonna run, this whole movie goes through the whole sequence of storms. So it's gonna start all the way from the beginning and go all the way through. So this is new right here. This is a new part of the movie. You see, as they cross the equator and start growing in the southern hemisphere, they can blossom up into huge, gigantic storms that can become global in nature. And it all starts from these little itty bitty local things all the way up to the northern hemisphere until they grow to be really big in the southern hemisphere. So to understand these...
Sorry, can we go back to that last image? There's some questions in the chat here. Just can you tell us how the images are made?
Absolutely. Great question. The images all of these data come from NASA satellites. The images that you're looking at right now are from the Mars Reconnaissance Orbiter, which has been in orbit since 2007. Every single day, it takes and makes one of these big global maps of Mars. Each one of these swaths, so down the center of each one of these swaths is the path of the orbiter.
Centipedes.
Sorry?
People have been comparing it to centipedes. like the segments in a
Yeah, it sort of is. Yeah, sure. It sort of is. I've never thought of it that way. That's pretty cool. So each one of these centers here, the center of the strips is like the path of the orbiter. So they're polar orbiting satellites. They go from one pole to the other pole and then back again. We only get one map a day because it's day on only one side of the planet. And so we get one picture every day of what's happening on the surface of Mars. We call them Mars Daily Global Maps. And there's a data set. These are also freely available to everyone to go download. On my website, there will be a link to the planetary data system. That's where all NASA mission data is provided free to the public, sometimes in less useful data formats than you might want, but you can download and use all of them. These are all TIFF images, actually, that you can just download and look at. So there are since 2007, a Mars year is about 2 Earth years. So we have about a decade of Mars daily global maps over the last 20 years. Not only is there a visible imager on Mars Reconnaissance Orbiter, there is also a temperature sounder. So we get temperatures from Mars that we can make data sets from, just like we do for Earth, and make cool weather maps, just like we do for Earth. So you might see something like this, probably a little bit cleaner and not as messy, but on your meteorologist, like the Weather Channel or something like that. And so the difference is, instead of the data coming from the National Weather Service like it does for Earth, these data come from Mars. So I've labeled the mountains again, and I'm going to follow these weather maps, just a couple of them, from the movies that we just saw. So the only thing I want to point out to you is here's a low pressure system. This is a cyclone. It's got a cold front. So there's cold air back here behind the cyclone, and then warm air back here in front of the cyclone. Here's the warm front. And so the dust storms will follow that trajectory. Here's the cold front again, and here's the dust storm being pushed up in front of the cold front and squeezed between it and this warm front. So the storms spread down in between the basins. And then after that, when the cyclones reach maximum intensity, these fronts trail all the way down towards the equator, much bigger than they get on Earth, just because Mars is a smaller planet than Earth. And then once they do that, the storms in the northern hemisphere weaken, but then they get sucked into the big overturning circulation that Mars has, just like Earth. In summer, it goes, in this perspective, counterclockwise. In winter, which is the time these storms happen, it goes counterclockwise. And here's an arrow showing where the dust storms, they start from the northern hemisphere and they go into the southern hemisphere. Once they get down into this area, in sort of the mid-latitudes of the southern hemisphere, they can get pulled upwards as well. And then they can really explode in growth. So much so that they can turn into what is literally a global dust storm on Mars. Clear here on the left, dusty here on the right. So that's kind of a lot of maps. I want to show you the timing. It's just, here's one full year of dust storms on Mars. Each one of these little dots is a dust storm. Time is marching forwards as you go further to the right. These are just storms collected together in latitude here on the y-axis. But it's not the only one that happens. There's one, and then a pause, and then another, and then another, and then another, and another. So they come in like these little chunks of waves. So how does this relate to better understanding Earth's climate? So we want to better understand the theory of all climate rather than just Mars's climate. So here's an example from Earth. This is from Earth. This is the Western Pacific storm tracks off the coast of Japan. So these are in the atmosphere. These are waves in the atmosphere. Each one of these squiggles is a different year. But the thing I want to point out to you is that the storms are stronger in the fall, October, November-ish. And then they're weaker in January and February, so in the middle of winter, and then stronger again in spring. So stronger, weaker, stronger. That's not what you would expect if you knew that these storms grow off how big the temperature gradients are from the equator to the pole. So if you just sort of assume that the temperatures of the equator are about the same, not changing all that much. In the middle of winter, though, it's much, much colder. So the temperature gradient is much stronger. So you would expect that the storms would be weaker in the middle of, stronger in the middle of January, but they're not, they're weaker. One of the theories that was kind of bouncing around for a while is that, oh no, can you not see my slides?
People can't see the slides.
Yeah.
I can see them.
Still says I'm sharing. Yeah, it still says I'm sharing. Let me stop and try again. There's always something, right?
Yeah.
It's the late night shift. Bound to break.
Yeah. Oh, someone said they could see it for a second. That's the wrong present. That's the next presentation.
Oh, we're back. All right.
In the chat, we're back.
I see it back on the YouTube. Yeah, thanks for stopping me. So one of the theories for why, I don't know where I cut off. So you would expect, I'll step back a little bit. You would expect that during the middle of winter, the storms would be stronger, not weaker. And one of the theories that has been bouncing around for decades now is that maybe there's some interaction between tropical convection and moisture and things like that, with the storm tracks way up north and things that are happening down near the equator. Looks like the sharing is off again.
I'm seeing the slides.
I don't see them in the YouTube.
Maybe they're gone again.
Director, what should I do?
Yeah. Are they back?
Looks like they're back again. I haven't touched them. They're back again. Okay.
Okay.
So I was saying that moist processes were thought to be what's contributing to this. Well, a couple of years ago, I put out a paper that shows that Mars has the exact same thing happening on it as related to these dust storms and the waves that kick off the dust storms on Mars. The exact same thing happens. So sort of famously, Mars doesn't have any moisture on it right now. So it can't be one of those reasons. It has to be dry dynamics that are driving the problems with why things are weaker instead of stronger. Looks like I'm gone again.
Yeah, okay. Well, why don't we move on to some questions?
Yeah, we can just.
In the
I was
chat.
going to talk a little bit about Titan and talk a little bit about the Great Red Spot, but you know,
There's a great dog photo. I feel that people will want this, but
so if it comes back, I'll.
yeah.
So
Let's just hope
I'll
for
just
that.
leave it right here. Here's my tiny polar bear.
Yeah, there's a dog that's bigger than you. So Stu Weiss asks, are there equivalents to atmospheric rivers on Mars?
Yes, great question. Holy cow, great question. So yes, there's something in Earth community, the Earth atmospheric river community called dry atmospheric rivers, where it's not a river of moisture, it's a river of dust from like a desert. These happen a lot in China. And an idea I've been playing around a lot with is trying to think of the big plumes of dust that are going up in front of the cyclones on Mars are basically dry atmospheric rivers on Mars, just like we see on Earth. I'm working with someone else right now, looking at dust storms from the perspective of atmospheric blocking as well, which is kind of another sort of facet of extreme weather as well. So there are lots of parallels because the waves that I showed you with the fronts called baroclinic waves, they act very similarly on Mars and Earth for reasons of, you know, Mars's day length is about the same as Earth's day length. And so that means some of the dynamics are actually quite similar between Mars and Earth.
Well, yeah, so you mentioned a QR code earlier. Could you?
Yeah. Here you go.
This
Here's
is
the
great.
movie again.
Yeah, also, I feel like I can't let you go without giving you like 30 seconds there's a question. As someone who's an expert on Mars, do you think it would be actually possible to inhabit the planet in the future? 30 seconds.
Is it possible? Sure, it's possible. Is it going to happen before we or our grandchildren die? Probably not. It's a long way off. And I'll leave it ambiguously there without being political.
Awesome. Thanks so much, Mike. That was fantastic. I think the audience really liked it. Definitely in the graveyard shift spirit. And thanks for that insight into the to the life of soft money researchers. Really underappreciated part of science. So many great scientists are in these roles and in these precarious positions. And we just have to keep hoping that funding is available to keep people like this going. So thanks so much.
Yeah, thanks. Good night, everybody.
Call your representatives. Okay, so before moving on to the next speaker, just a reminder, this is the Weather and Climate live stream. We're here to raise awareness of the proposed cuts to weather and climate research in the US and to showcase all the great research that this funding pays for. If you want to support climate and weather science in the US, please tune in, ask questions, share the stream with your friends and family. And if you feel inclined to, call your representatives. You can see at the banner at the bottom a link to a website where there's more information about how you can call your representatives and the message that we'd like you to convey to them. We're in hour 61 of this, and we've already had more than 6,000 calls as a result, representatives as a result of this stream. So we're happy about that, but we're striving for more. So let's try to get to 10,000 by the end of the 100 hours. Okay, and with that, I'll introduce our next speaker on the graveyard shift. Continuing the theme of keeping it weird into late night, we have Professor Ross Salawitch, who's a professor of atmospheric science at the University of Maryland, and he's going to be telling us, his talk is titled "What the Frack."
Okay, great. Thank you, Nick. Thank you, Paulina, backstage, making all this happen. We've had quite a night here, and Mike, that's a tough act to follow. Great energy. And by the way, I volunteer to go to Mars. The hard part is getting the people back, so I'll just take the one-way trip. That's the hard part. Okay, the graveyard shift, weirding out and all that. Well, couldn't have planned this any better. I'm going to talk about fracking, and I took this photograph. I'm not going to say where or when I took this photograph, but you kind of get the idea of where I stand on this. These are my thoughts. They don't reflect the University of Maryland nor any of the funding agencies. I'm going to mention a lot of funding agencies. So I'm a storyteller. We've told a story in this particular book. I hope that we've seen the slide advance. It looked like it went blank when I'm looking over.
I'm seeing the next slide.
You are? Okay, great. Super. Okay, so.
Are you guys seeing it? It says Paris Climate Agreement, Beacon of Hope.
Okay, until I hear otherwise, I'm going to assume it's visible. Shout out to NASA who supported this work through the Climate Indicators Program.
On the slide.
What's that, Nick?
Yep, they're seeing the slide. So
okay, super. Book is for free because NASA is so great about free access to the research. I will talk again at the normal shift, a scientific presentation directly relatable to the content of the book on the Paris Climate Agreement. Today, I'm talking more about what I teach at University of Maryland, taking a big fracking lecture and making it compatible for the late night shift here. Some of this is in the book. And our chapter 1 on Earth's climate system tends to be the most popular download. All right, so if you're here, you know what fracking is, so I'm not going to go over this entire slide. I want to emphasize a few points. The extraction of methane or natural gas by hydraulic fracturing became commercially viable.
I'm wondering if you could make your slide full screen. The text is a little small for me.
Okay, let's see if I can do that. I think I just messed it up. Slideshow from beginning, display settings. Is this better?
I'm not seeing a slide right now.
Okay.
Phoebe suggests resizing the window.
Resizing the window. Okay. Well, that's
all right. I think that's as good as we're gonna get. Let's
yep.
Sorry about that.
Yep. Okay. So they drill down, they turn it hydraulically, became available, commercially viable in 2002. And a very important point I'll come back to is they put a chemical brine in that loosens the deposits of natural gas from the shale rock that's drilled through. Now, I want to shout out to EIA, which is part of the Department of Energy, which has great information on climate-related material. This graph shows the liquid natural gas imports to the U.S. as a function of time and the countries. The red line is what I want to focus on. And we went from a net importer to a net exporter in this year around 2017, 2016, because of the tremendous supply of natural gas from fracking. You can't really talk about this very difficult issue in a meaningful fashion without realizing the tremendous economic benefit that going from a net importer to a net exporter has had on our nation's economy. However, this has come at a considerable cost, which of course I will get into. Another shout out to the great NOAA. NOAA is the go-to place for up-to-date information on greenhouse gases. This chart has been shown before. Methane is a function of time. It will be shown again from NOAA in Boulder, Colorado. Okay, so what's going on in the US? This is a chart from another shout out, American Chemical Society, Chemistry in Context book, a book I helped modify for the 7th edition. What we're showing here is the energy yield from combustion of natural gas or methane, and I just want to compare it to coal. So in the US, we transitioned a lot from coal power plants to methane power plants for two reasons. One, the availability of this source of methane coming out of our ground. And second, without going through all the math and all the numbers, natural gas is about 70%. We get 70% more energy out of burning natural gas compared to coal per CO2 molecule to release to the atmosphere. So if nothing else happens, like if methane doesn't leak, there is a climate benefit. Again, don't worry, I'm going to talk about the costs. There's a climate benefit of burning methane compared to coal, but that's only if you don't leak any of the methane. All right, so where does this happen? It happens throughout the US at these things, they use a word I don't really like, plays, the shale plays. You can see the maps here. The 5 biggest states are Texas, Pennsylvania, Louisiana, West Virginia, and Oklahoma for this extraction process. Now, Maryland, my Maryland, banned fracking. Here's our governor, Governor Hogan, looking very reluctant, signing it. This is a very famous climate activist, well-known, Mike Tidwell of the Chesapeake Climate Action Network, peeking over, like, is he really going to sign this? Yes, he did on April 4th, 2017. So Maryland, the Marcellus Shale does go through Western Maryland. We don't frack, but we are the primary place where fracked gas goes throughout the world. So we have a place in our Maryland, my Maryland, in Lusby, Maryland, called Cove Point Terminal. And so we get economic benefit from the fracking. Very complicated issue economically. We banned it, yet we'll happily pipe it through and ship it out. Okay, so concern number one is earthquakes. There was a Washington Post article in 2015 that talked about worries in Oklahoma, swarms of earthquakes, connection to the oil industry. Science implicated the oil and gas industry, and basically the deep water wells linked to increase in earthquakes. Here's a map. This colored stuff is where the groundwater goes in, and the circles are the size of the earthquakes. 2011, 2012, John Stewart talked about this in the show, shaking on the plane, yada, yada. All right, USA Today, 2016. This is big time getting in the USA Today. I've blown up this picture. I kind of laugh at this. We don't know who really this is. It looks like she's checking her cell phone as she's walking through the facade of a building that's been shaken by the earthquakes. So I wondered, what do they do in Oklahoma? Have they stopped this? No. Here's the number of gas wells in Oklahoma as a function of time, a slight decline, but they're still fracking. And what are they doing now? The next graph to me is horrifying, although you might think it's funny. I don't. This comes from a recent article, and what they're doing in Oklahoma. I was born in 1960. When I was the age of these children whose identity I'm hiding here, we did these duck and cover because when I was a child of the 60s, when I was in grade school, it was basically the height of the Cold War, just after the height of the Cold War, the Bay of Pigs, the Cuban Missile Crisis, all that stuff. We did this for atomic bombs. My elementary school had a fallout shelter in it. And now this is like full circle. So they're still fracking, they're still having earthquakes, and the kids in Oklahoma are ducking under desks. If anybody's online from Oklahoma and cares to engage about this, I would love to hear your thoughts on this. All right, concern number 2, you all know this, water quality. This comes from a great article. Sadly, it's behind a paywall from the Baltimore Sun, my hometown newspaper. This person lives in Pennsylvania. They frack on her property, so she let them on there, but she's now regretting it because the groundwater contamination, they talk about Cove Point, provides incentive for Maryland, even though we banned fracking, just what I said. All right, so water quality. Well, we're really worried about carcinogenic chemicals like MTBE getting into the ground and spreading quickly because, see, if it's in the gas phase, it can spread more quickly than water can. And here's some of the processes with the physical processes of the spread. So the U.S. government was aware of this. And in 2011, they formed something called Frack Focus, a central disclosure registry, searchable for seeing what goes on in the wells. So I looked at it. Pennsylvania, I'm sorry, you can't really read this. Washington, I like birds, photography, bird run. You wait a while, and what do you get? You see what they're putting into the water. And this is, I like halogens. Chlorine dioxide, I know what that is. I know a chlorine bicarbonate, a chlorine third-party additive. This one, proprietary, confidential, proprietary. I am not cherry picking. Throughout this, it's proprietary this and confidential that because there's a way out. They don't have to disclose what's being pumped into the ground in this proppant if it's proprietary or confidential. This stinks. This website doesn't look this way anymore. It's much less complicated, much more simple. So a lot less chemical compounds and still hidden what's really going in. All right, air quality. This is what I do for a living. I look at ozone up high in the stratosphere where it's good, down low where we breathe it, where it's bad, it's toxic. So tropospheric ozone is produced by reactions of nitrogen oxides and VOCs, volatile organic compounds. The biggest pollution from fracking is when the drill is in and it's using diesel generators. And when they drill, all the stuff comes out because they're going into hydrocarbon rich areas. So we have these, some of these are bad gases on their own, and some of these react in the atmosphere to produce ozone. We've known about this for a long time as well. So one state I'm going to highlight is the state of Colorado. If anybody, I'm sure we got some people from Colorado online. So here's some news articles. This is from the Denver Post. Colorado lets oil and gas companies pollute for 90 days without federally required permits. So there's a state law in Colorado that lets them have 90 days before they have to actually have permits. Well, that's huge because you can drill and tear down the drill in 90 days. And as far as I know, this is still in place. So, quoting an article from this website in Colorado, written by a woman named Heidi Leithwood, published recently, Colorado has been trying to solve the ozone problem for over 15 years. Surface ozone, bad ozone. What's the answer? She writes, rein in fracking emissions. So Colorado is in non-attainment for the EPA National Ambient Air Quality Standard for surface ozone, which is 70 ppb of ozone, 8-hour maximum. I teach this so I can rattle off all the stuff. We need to demand a much stronger plan this time, writes Heidi, in reining in these emissions. And here's a chart showing the number of days where Colorado has ozone higher than 75 ppb, which was the old standard. And here's the days where it's between 71 and 75 ppb. The current standard is 70 ppb. So this is a huge amount of days. I mean, this is a considerable fraction of the year. And my group at the University of Maryland does research flying airplanes over Colorado, trying to measure all of this, publicly funded, of course. Okay, moving on to climate. So if we leak methane, that's a problem because methane is a much more potent greenhouse gas than CO2. I've done a little bit of math here. Hopefully this is visible. Here I'm looking at when do we have a balance between the climate benefit of methane being 70% more efficient than CO2, and when do we have loss if we leak methane? Now here I'm looking at a 100-year time horizon, which IPCC says we should look at when we look at the global warming potential. But people like Mike Tidwell and myself think that's ridiculous. I'm not going to be around for another 100 years. I hope, God willing, to be around for another 20 years. Methane with a 10, 12-year lifetime is much more potent on the short term. If we look at the 20-year time horizon, a 2.4% leak, a small leak, turns climate benefit into climate penalty. So what are the leaks? Well, here's a figure, a table from our book. So we talk about fracking a little bit in our book. When we fly airplanes over, when we use satellites, we tend to find leakages that are considerably higher than the 2.4%. I should say the industry is getting better. This one study with a really small leakage, 0.42, this is percent, not fraction, percent, tiny leakage, scientists were invited into the grounds. Do you think they may have gone around with some instruments ahead of time, their own instruments, before inviting the scientists in and know they were sort of clean on those days? I think maybe, but regardless, when we just fly airplanes over, we tend to see that leakages from the wells puts us into a nebulous area for climate. All right, so I'm going to switch gears. One of my favorite authors is Jared Diamond. I used to teach a freshman class on climate. Believe it or not, we read Collapse from Jared Diamond. It was an honors course, all disciplines. And Jared Diamond talks about sunken costs of historical governments. The U.S. has placed a sunken cost in natural gas. For better or worse, we've replaced many coal-fired power plants with natural gas power plants, and it's very hard to reverse that. Now, there is an entity in the U.S. that knows how and really well how to capture CO2 out of fairly high concentrated regions, and that's our military, and they have to do it on submarines. It uses a chemical process using something called amines, and this can be scaled up for power plants. So I believe that carbon capture and sequestration needs to be thought about to overcome the sunken costs of natural gas power plants. Here's a graphic about the capture. Sequestration, we could talk a lot about sequestration. I referred you to this Herzog et al. Article in Scientific American a quarter of a century ago. The most favorable option is putting it in the deep sea. There's this thing off the coast of Norway called the Sleipner rig that does it all the time. Of course, if there's earthquakes, that could be a problem. You hope it's permanent. Will it really be permanent? Who knows? But this has to be part of our conversation, in my opinion, because of the sunken costs. So let's look at the economics quickly. The IPCC had a report published in 2005 on carbon capture and sequestration that many people don't know about because it's 20 years old. And here's my summary table of the costs. And way back when, they said that it would be about that entities would want to capture carbon if we could price carbon at $54 a ton. This is the work of the great Edward Rubin at CMU in Pittsburgh. I don't know him. I call him great based on his publications. My read of his publications is that the current cost is about $100 per ton. there's a large uncertainty with this number. But I'll segue into costs and pricing. Many people don't know that in certain states, the green states here, so Maryland, Delaware, I'm not going to name them all, Pennsylvania's in court, Virginia maybe will one day join, we put a price on carbon. This is the price through an auction of how much it costs to emit a ton of CO2. It's now $20 for all the states, and it's pretty complicated how they do the auction, but you can Google RGGI, RGGI, and learn about this. This is in place, $20 per ton of CO2. So I'm going to relate this to something we can think about. It turns out that it costs about $21 to buy coal at the price of coal this month to get a ton of CO2 in the atmosphere after you burn the coal. So in other words, the RGGI price sort of doubles the cost of the fuel. Now, according to my math, it costs about $54 to buy natural gas in enough quantity. They price it by volume. After which you burn it, you have a ton of CO2 in the atmosphere. So if you will, the RGGI price doesn't even double the cost of natural gas. Now, we can make electricity cleaner using natural gas, even though it's more costly per ton of CO2 than coal, because coal is nasty to move around, nasty with the other pollutants. It's just tough to work with. Natural gas, you can, turn on and off, just by turning a valve. I wonder if people can guess what the gasoline is. So Nick, maybe you can help me with reading the chat. How much do people think it costs to fill your car more than one time, to put enough gasoline in it such that after you burn the gasoline, you've released a ton of CO2 to the atmosphere? And I did this calculation for the current cost of gasoline, $3.16. And, oh, wait, we're playing Price is Right rules. Closest without going over. All right. Do you see any numbers in there? People still awake?
So the average, I think the average American emits like a ton a year.
Okay, I don't know that. That could be. But so how much do you think you pay?
I say like 20% of that is gas. Then.
Okay, well, I'm talking CO2. So the oxygen comes from the atmosphere.
Okay.
So yeah, I mean, is it C or
maybe
CO2?
like a year's? No.
Like try to think of the cost of gasoline per gallon and how much a gallon might weigh.
Okay, yeah. I'm going pretty high here. Like maybe, yeah, I'm seeing numbers like 2,000, 200.
Down. Okay.
200.
Okay. I'm going to give a countdown. 5,
average American emits something like 13 tons
4.
per CO2.
Okay, according to my math, you ready? It is, drum roll, 356. The point of this is that if we actually priced carbon at $100 per ton of CO2, it would be about the third of cost of gasoline. And the point of this also is when you're talking about putting a price on carbon, it's really hard to know what are you putting a price on, because gasoline is so much more costly per ton of CO2 than natural gas. So it becomes pretty complicated. But I think these are numbers that folks need to know if you want to talk to policymakers on the Hill, which I do quite frequently. That's a good segue into my next slide. So, oops, sorry, I jumped ahead. Well, okay, so we have a number of places in the US where we have prices on carbon. Washington, state of Washington, California does, Massachusetts does, and the states in RGGI, the Regional Greenhouse Gas Initiative. The good news is the prices are rising over time for those of us who want to mitigate. And some of those prices, like in Washington, are approaching the magic $100 per ton. And by the way, Norway got Sleipner to put carbon back into the ground for $50 a ton. But that was some time ago. All right, let's talk about the Hill. So I teach at the University of Maryland. We're on the subway system. We get down to the Hill. Before the pandemic, I used to go down there all the time. Things have changed since the pandemic, okay, but we're not going there. All right, there's one thing on the Hill that we have bipartisan support on, as hard as it is to think about this, and that's CCS, carbon capture and sequestration. So there are 15 facilities in the US that have carbon capture and sequestration. There's something called the 45Q federal tax credit that's around CCS. And now this is bad news. I'll just read what I wrote here, read what they wrote, the Congressional Budget Office. Almost all CCS facilities recoup some of their costs, yikes, by using captured CO2 to force more oil out of the ground. We don't want to do that. We want to put it in the ground and keep it in the ground and not bring out more oil. Nonetheless, there is bipartisan support for doing this on Capitol Hill that, to my knowledge, exists even today. All right, so this is my last slide. I have many slides in backup should we want to go to anything I have there. We have to understand that there has been enormous economic benefit from fracking. It's occurred under both elected political parties. The costs of fracking are earthquakes, pollution of water, air pollution, and this climate penalty. And we have a sunken cost. We can't shut those power plants off as much as we would like to replace them with renewable energy. So therefore, in my personal opinion, just my opinion, carbon capture and sequestration is something we might want to consider. Obviously is not as the only option, but is part of the options for moving forward. And we really have to scale up what occurs on submarines throughout the world, where they do scrub CO2 very effectively, very efficiently, and store it. We just have to scale it up. If we could ever price carbon at this much, according to the research from CMU, not my research, this would be economically viable. With that, I have left a few minutes for questions, I think, and thanks for your attention during the witching hour.
Yeah, that was awesome, Ross. Totally in the spirit of the graveyard shift. We went from dust storms on Mars to fracking, CCS. That's what we're all here for. For everyone in that chat, the calculation Ross did was with a gas price of, I think, $3.15 a gallon.
$3.16, which is the average price that I get.
A gallon. So you need to use that number if you want to check the math. We have some other questions from Mike Evans. How persistent are the ingredients to the fracking liquids? Like, how long do they exist before breaking down? Like, if we do some fracking, how long have we screwed up the water supply, the local water?
Hey, Mike, thanks for joining, buddy. You asked me a question that the only way I can answer is I honestly don't know. And hold on. I honestly don't know because I don't know what they're putting in there. This is one of the great frustrations. One of the really great frustrations in fracking is, okay, look, I know we have a line we're not supposed to cross over, but I'm going to do it in this way. The U.S. Congress gets a lot of money from the fossil fuel industry, both parties.
Yeah, I think we'll have to ask you to we're trying to keep this apolitical.
Yeah, but I'm not going, okay. Anyway, somehow they don't have to disclose what's in, so I don't know what's in it. I don't know. We don't know.
Yeah, I think that's a scary enough answer, actually. I'd like to know what's in your water. Another question that I thought this was a good one is, how close do you have to be to the oil rigs to feel a fracking-induced earthquake?
Well, apparently it's in areas that have some sort of active fault, so some seismicity, and apparently it's that water that's put in to fracture the shale. So it is a local problem, and those maps from the Washington Post, which I'll just quickly go back to, boom, 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 because I can get there real quickly. So what you're seeing here are where the earthquakes are in the circles, and the places where the water is put in is in this yellow area. So it's not a one-to-one correspondence. They're putting water here and water here without earthquakes. But the research on this started about 14, 15 years ago, and the seismologists, so here there's a year without much earthquakes. Here's the year without. Here's a year with big earthquakes. So the seismologists are pretty convinced that these earthquakes are not natural, that they're anthropogenic or human-driven, and they are co-located with some of the water injections.
That's great. Thanks. The map's really helpful. We also have I think a clarification question, which would be worth answering. So Shannon Fume asks, but coal is so low given its carbon intensity. Can you talk a bit about that?
Sure. Coal. Where to begin with coal? Well, the reason why methane okay, I'm a chemist. The reason why methane gives you the most energy is it's the most reduced form of carbon. So it's a carbon with 4 hydrogens. Combustion is when you turn carbon from its most reduced form, which is a bunch of hydrogens around it, to its most oxidized form, which is CO2. So from a chemical point of view, methane is ideal for combustion. Coal is not ideal for combustion. We relied on coal back in the buildup of the post-World War II buildup of the U.S. And, my family, being a child of the 60s, benefited enormously from it.
Shannon was asking how it's a low cost per dollar in the chart in the slides.
Oh, low cost per, yeah. That's like, the dollar. Yeah. Sorry, that. Okay. That just has to do with the fact that, okay, I think that he's asking about these numbers.
Yeah.
There's a whole lot of long discussion behind this, but basically, coal is somewhat easier to extract. It's transported in railways the old-fashioned way. Actually, a lot of the price is driven by the cost of transporting the coal and not extracting it. And there are international players. This is the cost of the coal in the U.S. that I factored in here.
More carbon intensive per unit mass than per unit volume than natural gas. So maybe it's easier to transport.
Yep.
Cool. Okay. Well, thanks. That was awesome, Ross. Thanks again. And we're gonna. Sorry. You have any last words?
Write your elected officials. We have to stand up and call for action.
Totally agree. Thank you so much. Thanks everyone for tuning into the Graveyard Shift. We're going to keep this going. First, just a reminder why we're all here. So, there are a lot of very heavy proposed cuts to weather and climate research funding in the US. And we're here to showcase all of the amazing research that people have been doing, funded by this research. Especially, as you might notice, there's just tons of really amazing early career researchers, grad students, postdocs, people in soft money positions, as we heard from Mike a few minutes ago. And so we're here to showcase that research. And if you want to support weather and climate research, please watch the stream, comment, engage, tell your friends about this, your family, and most importantly, try to get people to call the representatives. Make your voices heard, make our voices heard about this issue. We're here rolling into hour 62, and we've had over 6,000 calls to representatives that have been inspired by this show, and we want to keep this going and get up over the 10,000 mark. And with that, the Graveyard Shift is going to keep going. It's gotten a little bit weird here. We've gone to Mars. We've been talking about fracking. Now we're going to get back to meat and potatoes with some good meteorology from our next speaker, James Ryan, who's a PhD candidate at Indiana University, who's going to be telling us about precursors to extreme cold in the Midwest.
Hi, Nick, and thanks so much for the introduction. And hello, and thanks for everyone for tuning in to learn more about meteorology and the role of funding in it. I'll introduce myself. My name is James Ryan. I'm a PhD candidate in atmospheric science, graduating this summer from Indiana University. And the research I'm about to show is funded by a Department of Energy funded project called HILAT-RASM, which does a lot of work on predictability and Arctic and mid-latitude weather, and how weather is connected from one part of the world to the next. And so what I'll be talking about is extreme wintertime cold events in the Midwest United States and different ways we can predict them or not on the scale of a couple weeks out. So why are we talking about this? Here's a chart on the right showing on the x-axis forecast time. So for instance, if you launch a weather model and you have it run for a few weeks, for the first few days, it may be running really well. And that's represented by this y-axis showing forecast skill. Ignore these various different colored lines from a figure I'm working on for an upcoming paper, but just look at this black line. It's from a particular model called the CESM2. And in general, in the first few days of the model run, the forecast is great. It's really skillful. It's pretty darn accurate. For the most part, if the model says it'll be warmer than average, we observe warmer than average temperatures. But as we get to 1, 2, 3 weeks out, it gets much, much worse. Why is that? Well, weather can be very difficult to predict, especially further out in time. If it wasn't, you wouldn't be having 4 days of talks talking about how difficult this is and why this is so important. But why is it that the atmosphere is so difficult to predict? It's that it is what we call a chaotic system. Now, the term chaos theory is very popular, and it dates back to around the 1960s when a scientist named Ed Lorenz ran some computer code and found that really tiny changes would lead to vastly different outcomes sometimes. It basically just means that your results will be really sensitive to initial conditions. Sometimes we hear of this called the butterfly effect, where basically some tiny change can lead to massive changes further on. But what this means is that if small changes can lead to different outcomes, then could there be some types of events that, even if we normally can't predict them well a couple weeks out, some of these could be predicted better than average a couple weeks out? We can call these forecasts of opportunity. And we're going to see in this talk if some severe cold events in the Midwest in winter could be forecasted better than some of the other types of cold events in the Midwest. Why are we focusing on the Midwest? Well, for one, I go to Indiana University. For two, tens of millions of people live in the Midwest. And for three, a heck of a lot of our food is grown out there. So the better our predictability can be, the better we can help everyone all across America.
James?
So, yes.
Yeah, sorry, can I interrupt you for a second?
Of course.
Can you go back to the previous slide?
Absolutely.
Can you tell us a little bit about what you mean by forecast skill here?
Oh, certainly. Thanks so much. So, yes, this figure here is showing how well that temperatures in the United States, specifically just in winter, are correlated, or basically how similar they are. So, for instance, at this point, for instance, this is showing how well that our temperatures that we observe are correlated with predicted temperatures from this one particular model at 5 days out. And in this, the higher the black line is, it means the model is doing better. It means we're predicting stuff really, really well. But as we get lower, as we get closer to zero, it means the model's out to lunch. There's no predictive value there. You may as well just flip a coin to determine if it's a good or bad forecast. Apologies for not explaining that better. It's 2 a.m.
No. This is a graveyard shift, so we're being a little bit more informal here. But go ahead.
I got you, and thanks a bunch.
Apparently, the organizers are already playing a drinking game of taking a shot every time you say Ed Lorenz's name.
Oh, man. Okay. Yeah, I'd imagine you've probably gone through quite a few shots already throughout the day. Best of luck. May God bless your livers. All right, so what we're going to do in this methodology is first we're going to identify these cold air outbreaks, or basically just periods of time where it's really, really cold for several days in the region that we're looking at, in this case, Indiana. And next, we are going to find what we call weather regimes, basically days under some large weather patterns in different parts of North America. And so this way, we might be able to find that some weather regimes have really predictable cold events, and some of them might not, and why. Next, we'll find out, once we identify these cold events, what happens before these cold events. So that way, even if our model can't really predict 1, 2, 3 weeks out that well, maybe if we see some clue, we see some pattern going on in, say, the Pacific Ocean or something, then that could tell us, okay, there's a higher than average risk of extreme cold 2 weeks out, for instance. And these patterns that we're going to check, they're called teleconnection indices. Now, that's a fancy word, teleconnection, but one that's really famous that a lot of people have heard about is called the El Nino Southern Oscillation, or ENSO. El Nino is just when ocean water gets a lot warmer than it normally does in the tropical Pacific, and that has profound impacts on weather around the world. But ENSO is not the only teleconnection. There are some other ones that work a lot faster, and are just a little less famous because they do a little bit less, but have a lot of more local factors in North America. And finally, we'll see, can we use these to predict extreme cold? The goal of this is basically, if we see pattern X, does that raise our odds of extreme cold in the Midwest? If we see X, will we see temperature Y? So first, we got to define cold air outbreaks. Now, these are going to be long-lasting, extreme cold over a large area. What we'll be focusing on is just, temperatures that you feel walking around at the ground, and we just average them basically over Illinois, Indiana, and Kentucky for the most part. Then we're finding days that are in that coldest tenth of days compared to normal. So basically, this would be an event that could happen, say, once or twice a winter on average. And if you have these really, really cold days, you'll have to have 3 really, really cold days in a row compared to your already pretty cold Midwestern winters. And so when we apply these criteria, we get 43 different cold air outbreaks. If this looks like there's a sprinkled Pop-Tart on your figure, or on this figure here, we'll explain that in a second. These 3 different colors represent a few different weather regimes that all of these can happen in. So what this Pop-Tart is showing in this y-axis is what year all of these were happening in, all the way from December 1st on the left over to February 28th on the right, showing your whole winter season. And this top row is 1980, and this bottom row is the winter of 2020 to 2021. You'll notice some of these are in red, gray, or blue for different weather regimes that these can happen in. And what you'll notice is these can happen in multiple different weather regimes. Therefore, all of these cold air outbreaks might have separate causes that we need to look out for. What are those causes? Or at least, what are those precursor patterns? What happens before all of these? But first, what are North American weather regimes? So, weather regimes are really common patterns of so-called height anomalies that last for several days or more. And we'll explain what height means in a sec, but you can look on the right, and basically where you have red, that means you've got higher than average pressure in the upper atmosphere. And where you've got blue, you've got lower than average pressure in the upper atmosphere. And so most days in winter, your pattern compared to normal for heights will look like one of these more or less. Some days it'll look a little more, some days it'll look a little less, but these will describe the patterns pretty well. Now, what exactly what are these heights of? This is a height of the so-called 500 millibar pressure level, so air pressure. It's a metric that we actually use a lot in our day-to-day lives. So every so often when you need to deal with tire pressures, if you get a flat tire or just need to refill a tire a little bit when it gets cooler or warmer, what you're measuring is the pressure difference from inside and outside of your tire. And so air pressure is a lot like that. It's just how much force is the air exerting on you. And more importantly, as you go up in the atmosphere, air pressure decreases. The 500 millibar height, that's kind of right in the middle of the atmosphere. About half of it is above you, half of it is below you. We find it 5-6 kilometers up, and it summarizes a lot of stuff. The important thing here is that where you have higher than average heights, you've got warmer than average air. And where you've got lower than average heights, colder than average. So it summarizes a lot of things about temperature from all the way from there to the bottom of the atmosphere, or just the ground where we all are.
So when we look at these beautiful images that you made, we can think of the red colors as warm temperatures and the blue colors as cold temperatures?
Generally, yeah. So yeah, height, or I guess thickness of a pressure layer, for instance, from 500 millibars down to 1,000 or so millibars at most places on the ground, is proportional to the average temperature in that layer, actually. And that's just because air gets less dense as you warm it up. Same with any fluid generally. So yeah, where you've got red, you'll generally have warmer than average air below, and where you've got cold, you've got colder than average air below. And that's a really fitting question for this, because note that I only had 3 weather regimes popping up here, but we identified 5 going on here. Why is that? Well, if we're looking at the Midwest, you see where the Great Lakes are, look right around there into the south. If we want it to be really cold, well, okay, not if we wanted to, but if we're looking for extreme cold, we'll need it to be blue, or at least not red over there. We'll need it to be cooler than average, and that's proportional with lower than average heights aloft. And so that's really only possible in this one on the top left called West Coast Ridge, named because there's a ridge on the West Coast, ridge just meaning higher than average heights. And then, apologies, it's a little late. And then these next 2 here, where you've got blue in or near the Midwest, indicating colder than average air at the ground, or lower than average heights aloft generally. Now, there's no hard and fast rule on the ideal number of these regimes, but usually you go with 4 or 5. I'm certainly not the first person to come up with this. Meteorology, like any science, is very collaborative. We build on previous things. And so that means if, say, funding is cut drastically one particular year, it doesn't just affect that year. It also means there's less science for future researchers to build on in the future. So a lot of this work is based on methods by Oliver Millen et al. And his team at Oklahoma University back in 2022, looking at the Great Plains. We are comparing their findings with further east in the central US and the Midwest to see what we have there. We use a technique called k-means clustering. Not going to get into the specifics of that at this hour, but email me if you have any questions. But anyway, we have these 3 different weather regimes that can have extreme cold. And so we'll break down all of those different weather regimes, cold events, to see what we get. The reason we do that is because they all have different properties when we group them by regime, in terms of how cold they get, how long they last, and just how severe they are when we multiply these together. I realize I'm running low on time, so I won't get into this slide too much unless there are questions. But then why do these happen? Well, for 2 of the 3 of these, Millen identified that, and we find the same cause in the Midwest as well. Basically, polar vortex stuff. That term got real popular in the past 10 years or so, and I'm glad there's some more awareness about that. But basically, if you have a weak stratospheric polar vortex, it's easier for displaced Arctic air to end up in the mid-latitudes. But there's this 3rd type of event that happens more further east in the country than the Great Plains, called the West Coast Ridge event. And I'll get a bit past this figure, but basically the West Coast Ridge event, or the West Coast Ridge regime in the top left, rarely gets that cold in the Great Plains, but it does more in the eastern third of the country. So if we look at precursors, at basically what happens before in this 500 millibar height field, pay attention to this 3rd column, that one that says WCR. And in the 11 to 8 days before, we see in the North Pacific that you generally have higher than average heights in the North Pacific, and lower than average heights as you get closer to the equator, or at least the lower latitudes.
James, could you help?
Sorry, what did you say?
Could you help orient us a little bit? So now
Absolutely.
we're looking down.
Yeah, so there's a lot going on in these figures. But basically what you're seeing before is you're looking at the whole Northern Hemisphere. So there are different map projections that are really useful to use. This one is centered on the North Pole. North America is on the bottom half of this. So basically it's the focus of this. And then what you're looking at are 3 different weather regimes, cold events that happen like during each of them. And then on the right, just the average for all of them together. And what this figure is supposed to do is basically show why we're separating our cold events by weather regime. Basically, each of them have different events that occur before them, represented by these blobs of higher than average or lower than average 500 millibar height. So for instance, where you've got a bold line, that indicates statistical significance at all of those grid points after applying various significance tests that feel free to email me if you want technical points. But basically, we don't have any of those blobs with statistical significance with the West Coast Ridge type until just 3 days before severe cold gets to the Midwest, which indicates it's really hard to predict. There might not be a thing where we can see something going on in the Pacific and say, therefore it's going to get really cold here. However, we might just be looking at the wrong thing. Because these tests are all applied at individual grid points, but it doesn't say anything about the relationships between heights in different parts of the world. You might want to look at a gradient instead. And so this is where we turn to a teleconnection index, one of those relationships that describes how different parts of the world have related weather. And this one is called the West Pacific Oscillation. And what we do is we take 500 millibar heights in the North Pacific and subtract 500 millibar heights in the further South Pacific as you get closer to the equator, basically. So think like near Siberia minus like off the coast of Japan, for instance. And basically, if this index is positive, it means that we'll have really strong winds compared to average over the Pacific. And if it's negative, we'll have weaker than average winds. And what we end up finding in this figure, where to orient you, this top left one is the one we're looking at. This shows 9 different teleconnection indices that we tested. Focus on the WPO, this one down here. There's also this one called the NAO, the North Atlantic Oscillation, that has a lot. And I realize I'm going over time, so I am going to...
Okay, you have to the half hour.
Oh, okay. Sounds good. So, all right. So look at this row here. Can you see my cursor or no?
Yep.
Oh, okay. So look at this second to bottom row here with the WPO. And at 10 or so days before we get really cold air moving into the Midwest, we do, as we expected, have a negative West Pacific oscillation. However, what if we looked further back into the past as well? I'm not trying to be someone who's implying that we can predict weather to the day 50, 60 days out. I'm not doing that. But if we already know that, say, 50 days ago, there was a positive North Atlantic oscillation, or basically colder than average temperatures over Greenland, warmer than average over the central Atlantic, basically. If we already know that that happened, say, 50 days ago, and we currently have a negative West Pacific oscillation, maybe that'll increase our odds of having this type of cold event happen in the Midwest, and would be something to look out for. And while the 60-day connection seems a bit like a stretch, other papers as recently as 2016 have found that a positive North Atlantic oscillation, so again, that pattern over Greenland and the central Atlantic, can lead to strong troughing or lower than average heights in East Asia and the West Pacific about 2 months later, roughly matching with that 50 or so day timeline we were looking at. And that's consistent with our results. And so that might raise our odds of extreme cold in the Midwest a bit later. So what we looked at is if we have our most positive NAO days and most negative West Pacific oscillation days, how many of those days are actually really cold in the Midwest compared to what we would expect? So normally, if we need to get days that are in the coldest 10th compared to normal, and we need 3 of those really cold days in a row, then just by default, if we have no other information, any given winter day in Indiana only has a 5 to 6% chance of being in a cold air outbreak. But with just these 2 pieces of information being true, then we have an 18% chance. This triples the risk of extreme cold in Indiana. However, what if we bring in weather regimes into the equation? If we also somehow miraculously know that we'll be under the West Coast regime, the West Coast ridge regime across North America in about 9 days, then combined with those other two pieces of information, we have a 38% chance of a colder outbreak day. That is a 6 times increase in risk compared to the default if all of that is combined. However, can we actually forecast weather regimes that well? Kinda. It varies by study. But even without that, we still have a tripling of risk normally. And finally, where do we get this height data? Everything that I've shown you so far has been from a product called reanalysis, specifically the MERA-2, which is a NASA product paid for by our taxpayer dollars. The inputs for it include a lot of different types of measurements, both at the surface and aloft, and this includes the weather balloons, or radiosondes, launched daily by lots of National Weather Service offices across the country. And so without these critical observations, we wouldn't be able to know the heights or really much of anything in the upper atmosphere as well as we can with them. So to conclude, colder outbreaks in the central US and most weather regimes are preceded by a weak stratospheric polar vortex. That's something we've already known and corroborate with researchers at Oklahoma. But West Coast ridge colder outbreaks, so when it's really cold in the Midwest and also warmer than average in, say, California, are typically preceded by weaker than average winds in the West Pacific about 10 days before we get extreme cold in Indiana, and a very positive North Atlantic oscillation pattern about 60 days before it happens. And we can measure these patterns largely thanks to the people at the Weather Service who are measuring and recording this data. Here are the various works that I cited showing that science builds. And thanks. Let me know if you have any questions. And if you ever want to collaborate or ask more in-depth questions, feel free to email me. Thanks so much for your time, everyone.
Awesome. That's a great talk, James.
Thanks.
You said you're going to defend your thesis soon?
I actually defended back 2 months, and depending on your time zone, 3 or 4 days ago. I have some edits to make on my second and third chapters, but I'm proud to say that this work has been published in the International Journal of Climatology. So feel free to check it out.
Awesome.
Thanks.
Yeah, a lot of great questions. Sydney Lindquist asked, and I think this would be good for a bunch of people in the audience, is high-low pressure caused by rising falling air?
Yes, great question. So low pressure is indeed caused by rising air. So if you have, like, picture just like a box that has some amount of air in it, if some air goes up, assuming you're on the ground, then there's less air in the box than there was before. And so other air from around will have to try to fill in because there's one force and one force only that can generate wind, and that's called the pressure gradient force. Air will flow from high to low. The Earth is rotating, so it'll actually get deflected to the right in the northern hemisphere, which is why we get circulations. But in general, the pressure gradient force. So yeah, in short, as air goes up, the area that it left will get lower pressure. Similarly, where you have descent, you'll get higher pressure. Great question.
Great. We have another question from Fish's Failure Son, which is, what's the margin of error for this? I think that's kind of a general question about when you're using these weather regimes to try to forecast cold spells. What kind of margins of error are you thinking? Are we talking about?
Oh yeah, absolutely. So this is a probabilistic thing, so not a yes or no. So as for what the margin of error is, I haven't tried to make this into a sort of model yet. So this is more of just looking back in history, this has happened X% of the time. So I can't answer that question. Oh, what'd you say?
This is the graveyard shift. No one's going to hold you to it. Just
fair.
Let it fly. Another question is, in a warming world, would a more wavy polar vortex have more effects on the West Coast?
Interesting. Okay, so I'll admit I grew up in the East Coast and have spent basically my whole life in the eastern half of the country. So I'm not sure as much on the West Coast. That being said, there have been various conflicting studies about how global warming will or will not change the waviness of the jet stream, as well as the speed of it and placement of it. There's a lot of interesting literature out there. Obviously, Francis and Vavris did a lot of work on that, and still do a lot of their papers in, say, the 20 teens. I've also seen more conflicting takes by Tiffany Shaw's group at Chicago. So yeah, feel free to look into a lot of their work. I'm not sure what it would do specifically to the West Coast, but the good or bad news, depending on your perspective, is that we aren't even totally sure about the waviness stuff yet.
Yeah, how about to the Midwest then? Would a wavier polar vortex lead to more cold air outbreaks?
Theoretically, yeah. I mean, so if indeed things are getting wavier, then you would get more intense cold getting pushed further equatorward, including in regions like the Midwest. With the western US, you do have the Rocky Mountains partly helping to shield the Southwest from extreme cold to an extent. But I mean, waviness, depending on where exactly the waves are. Like if you have a ridge over the west and that gets wavier, then you're having more intense heat potentially over the western half of North America. Or if that ridge is over the east, then that. So it's a wavier jet would imply more of both extremes, though also where each ridge or trough is located, east and west, would also have an impact.
Okay, great. Well, thanks so much, James.
Thanks so much. And let me know if you have any questions. Have a great night. And thanks, everyone, for tuning in. Bye.
Yeah. So yeah, thanks everyone for tuning in. This is Graveyard Shift. We've been jumping all over the place. We've had Martian dust storms. We've had methane leaks, and we had some good meteorology there. As a reminder, this is a weather and climate live stream. We're here showcasing some of the amazing weather and climate research that is being funded in the US. And we're doing this to draw attention to the fact that there are large cuts proposed to this funding, and we're trying to raise awareness of this and encourage people to action. So if you want to support the research that you're seeing, please tune in, please share information about this live stream with your friends, family, engage in the comments. We love getting questions. And most importantly, call your representatives. So you see on the bottom, there's a banner which has a link to a website with instructions for how to contact your representatives and the message that we're trying to convey to them. We're here in hour 62 of that 100-hour live stream, and we've had more than 6,000 calls to representatives, so about 1,000 an hour. Let's try to get this over 10,000 by the end of the 100 hours. All right, so wrapping up the Graveyard Shift is Glen Chua, who's an early career climate scientist. And he's going to be telling us about the atmospheric detergent, past and present drivers.
Hello. Hi, just checking, like, does everything look okay? Sorry, I'm trying to figure out, should I share my screen? Can you hear me?
Yeah, I can hear you.
And should I, like, go, like, full screen with my slides?
Yeah, maybe try, yeah, can you go full screen?
Like play from start, or?
Yeah, maybe try that.
Maybe something like this is okay. This is, I don't know.
Yeah, that's what's working for you.
Okay, yeah. Thanks for having me on. I'm happy to close off the graveyard shift. My name is Glen, and I'm currently a NASA postdoctoral program postdoc fellow, working at the NASA Goddard Institute for Space Studies in New York City. And I'm going to talk to you a little bit about the atmospheric detergent and some of its past and future drivers. And spoiler on my title slide, the atmospheric detergent is this chemical species called the hydroxyl radical, and it kind of ties some concepts in the atmosphere like climate and chemistry together. As I mentioned, so the atmosphere is sort of made up of these different gases that we breathe and live in. But what we don't really see is that there's like a lot of chemical reactions that are happening in the atmosphere all the time. And one of the primary drivers of the atmospheric, the various sorts of chemistry is the all these different oxidants in the atmosphere, and the primary oxidant is the hydroxyl radical. And this, the reason why it's called the atmospheric detergent is because most things in the atmosphere, chemical species, react with it, and so it's able to remove many pollutants, and including some important greenhouse gases like methane. And so I think this is the first instance that I could find. 1986, the Nobel Prize winner Paul Crutzen coining this term, the detergent. So how is it formed in the atmosphere? This is supposed to be a video and it should be playing, but never mind. It is this. Okay, let me try to get this video to.
Can you try like presenter mode or something?
Yeah, maybe I'll try presenter mode. This is yeah. Well, you can see the video, but it might be looking like the presenter view. Anyway,
we're not seeing the video.
You're not seeing the video? Do you see it now? No. Can
you try play from the start? Or play from current slide?
Yeah, maybe I'll try play from current slide. Sorry about that. Do you see the video
now?
It's
working.
This is working now? Okay, great. Yeah. Yeah, so, as I was mentioning, this is the primary way in which the hydroxyl radical is formed. It's through it basically follows the sun. So you can see where the reds are happening. It's
how high in the atmosphere is this? Is this at the surface or it's?
So this is if I recall this particular video, I think it's the surface, but the primary production happens throughout the tropospheric column basically. But yeah, so this video I took it from the one of the NASA websites, and yeah, as you can see, there's a lot of spatial temporal heterogeneity, and as I was mentioning just now, one of the reasons why it's important is it's a major driver of methane trends. So methane is a major greenhouse gas, second to CO2. And by greenhouse gas, I mean a gas that contributes to surface warming. And atmospheric methane is increasing. And so given that this tropospheric hydroxyl radical is a major sink of methane, if you understand how the major sink of methane changes, it can help you understand how methane is evolving. So I have to go through a little bit of chemistry before I go on, but it's going to be very, very abbreviated and pretty simplified. So as I mentioned just now, the main way that the hydroxy radical is produced is via this process with the sunlight. So it follows the sun, and water vapor is important in that too. And then there are many other processes that then happen, but one of the main things that, as I mentioned, the hydroxy radical being a detergent, it reacts with many different things. So, for example, methane, as we mentioned, it reacts with other volatile organic compounds, basically carbon compounds with different lengths, carbon monoxide, and then there are also many other things that it reacts with. And then there are these other secondary production, the pathways that are important too. So stuff like nitrogen oxides, basically like think car exhaust fumes, and also like ozone, which is like a important like air pollutant in the surface, can help to reproduce OH. And so like these are sort of like primary versus secondary production, but just kind of highlighting some of the important like ways in which humans can directly affect the hydroxy radical. So for example, if you have natural gas leaks, you increase methane, or like you have more cows or something, and that can like reduce OH. Also, like if you have like air pollution from car exhaust, for example, you can increase nitrogen oxide, so that could help to increase that recycling of OH. So you tend to get enhanced OH, but you could also have like pollution in form like the carbon monoxide is also produced from like car exhaust, and that can be a sink of hydroxy radicals as well, and all sorts of other like volatile organic carbons, so you can imagine, can be emitted from burning of fossil fuels from power plants or cars. One other interesting way in which the hydroxy radical can be impacted is just via like just changes in background climate. So as I mentioned, like this primary production thing, there's that implicit dependence on the background water vapor, and the background water vapor is kind of controlled by like your temperatures. And so if you have anything that you do to the Earth system that is changing your temperatures, you can also affect the hydroxy radical by having like higher temperatures, leads to higher water vapor. You can boost the primary production of hydroxy radical. So that's why the hydroxy radical in this sort of like human chemistry, climate sort of interactions, like it's like an interesting species to look at.
Yeah, I'm a little confused, like because you called it detergent, which makes me feel like it's good to have more hydroxide.
Yeah. It's like a self cleansing, like it's sort of like the Earth's like ability to like self cleanse itself of things. And so yeah, like I'll get into a little bit of like interesting things between like how, I don't know, like our so like as I will talk about a little bit later, there is sort of like a small little negative feedback. For example, like if you have like increased temperatures, you have increased hydroxy radicals, it can like reduce methane concentrations, like all things being equal. Like if methane emissions are like not increasing more than the sink increase. Given that the hydroxy radical is driven by many different climate responsive and chemical drivers, it's pretty complicated. And it is also very hard to directly measure. Like think about not only like the very, very short lifetime, like less than 1 second. These sort of like computer models that can simulate all sorts of different Earth system processes are very useful tools for us to understand what happens in with OH. So think about like the Earth system models that are based in some of the American like federal labs. So like where I did my PhD, the Geophysical Fluid Dynamics lab GFDL, based out of Princeton, or the NSF with NCARS, the Community Earth System Model CSM, or at where I am now, NASA GISS with the GISS Earth System Model E. Yep. So what's happening to the hydroxyl radical in these models? So just focusing on this historical period for now. On the left is like a older sort of like multi-model, like the project and all the various models that participated in it. So you can see in general, like in the hydroxyl radical concentrations, like the absolute values, there's like quite a big range across different models. But models seem to converge on some sort of like increase from 1980 onwards. And in the latest multi-model comparison project, the CMIP6, the models that participated in that Earth system models that participated also show like a increase in this 1980 to 2010 period. Why is it increasing? I did some single forcing experiments in this historical period using the GFDL model, the AM 4.1, and also like GFDL supercomputer resources to do single forcing experiments. And so I'm just kind of explaining what these different bar charts mean. So the leftmost bar chart is the like historical, like all factors involved, like what is the trend in the OH that you see. And so you see like OH trend is positive, so it's increasing. But among all the single drivers, like you can see that the NOx emissions, which is the red bar, contribute like very positively to the increasing OH trend. And that's kind of offset by that green bar, which is the increasing methane during that period too. And so the combined CH4 plus NOx change in that period matches what you get in the base case increase. So what that means is that in this period, while many developed countries saw like NOx emissions, criterion air pollutant in this period due to air pollution policies, including in the US. Many rapidly developing countries were actually seeing really rapid increases in NOx emissions in this period. And methane concentrations were increasing in this period too, but the NOx effect seemed to be more important, at least in the current generation of climate models. So what this also means in terms of implications is that the unintended increase in OH due to unabated air pollution actually helped to dampen the growth of atmospheric methane in this period. So I'm just showing on this here, like methane lifetime in the single forcing experiments. So the blue line shows like the methane lifetime decline in this period due to the OH increase due to all factors, and the red line is the methane lifetime decline due to the increased NOx emissions. So you can see that the increased NOx emissions was the ones that's driving the reduced methane lifetime. And so, to your point about like the kind of interesting sort of interplay between the pollution itself and the ability of the atmosphere to cleanse itself. Yeah. And so then I also like looked into the future, kind of cognizant of time. I just will kind of speed up a
We
little
have
bit
10 more minutes.
Yeah. So I kind of what will happen in the future. So these what I was showing just now was like what was driving the like more recent historical period. The future is a little bit more complicated because we have to rely on various like scenarios, and these scenarios are inherently they have many different like different policy assumptions inherent to them. But there was in particular in the most recent set of like experiments, there's an experiment called the SSP-1 that has low warming but strong air pollution control and strong methane mitigation. And in the SSP-370, there's higher warming and weaker air pollution control and strong methane growth. And so in the SSP-1 2.6, you see that OH is actually modeled to increase, but in the SSP-370, the OH actually will decrease. And kind of thinking about like, oh, maybe like we don't want the OH to decrease because we want to make sure our atmosphere is still healthy ability to cleanse itself. So I guess
Glenn, I saw there's,
yep.
Yeah, I saw there's 3 different lines on each plot. I think they each correspond to a different model. Like what's causing the difference between the models? Is that differences in how they represent the chemistry or?
Yeah. So that is also like kind of like an active field of current like it's different models, like have different chemistry, but especially with the SSP-370, part of it is also potentially that like the different climate sensitivities of different models. So the temperature effect, as I alluded to before, like can be a big role there too. So so both a combination of like potentially like climate sensitivity and also like representation of like background chemistry. Yeah.
Cool, thanks.
Yeah. So yeah, I sort of asked a question about like, can we get a understanding of like some of the individual levers on the future OH with, since it's kind of hard to decouple like what is the most important like factors, since everything is changing all at once. I kind of used some of these CMIP-6 experiments to isolate the impact of these various factors. And one of them that I was able to use was different experiments where they kept surface temperatures constant versus like increasing as per the SSP-370 scenario. And so taking the difference of that gives me the role of the future temperature growth. And so just kind of highlighting some potential like drivers here, but I don't think I have time to go through them. But the interesting thing is that despite the sort of model diversity, all models simulate increasing OH and therefore decreasing methane lifetime with increasing temperature. And this kind of leads to like a small negative climate feedback by reducing the methane-related radiative forcing with increasing temperature. So the conclusion so far is that in SSP 370, like the increasing temperature does drive like the OH to increase, but yet we still see that the OH in general decreases in the SSP 370. So this kind of highlights the importance of the red bar is not enough to offset the blue bar, and so what that means is that what I call the chemical drivers, so basically air pollution control or methane growth, weak air pollution control and methane growth is a stronger driver in pushing the OH down in this. And so I asked the further question, like, which is more important? And so I find that I use similar sort of like single change experiments available in the CMIP6 to look at it. And so basically it looks like if you reduce like the methane mitigation here, so like the bars that I highlight, as you can see, when you pursue methane mitigation alone from the relative to the SSP 370, you get an increase in OH. So the methane mitigation seems to be very important if we want to achieve increased OH. And meanwhile, the combined effect of the air pollution controls and increased methane is that OH still increases. But one circle that did not pop up because I forgot to copy one slide was that if you look at the low NTCF bar there, that's basically like the impact of just reducing air pollution emissions alone without touching methane. And you can see that if you just reduce the air pollution alone, the OH would actually decrease, and that would extend methane lifetime. So just targeting air pollution alone is good for like health purposes, but you would have some sort of unintended effects in terms of reducing OH. And so one of the conclusions from this is that if you want to pursue aggressive like air pollution policies, like it's also important to simultaneously reduce methane emissions and so there is some evidence of COVID-related NOx emission changes, reductions leading to decreased OH, and some studies have attributed about half of the observed methane concentration increase in 2020 to this effect alone. But obviously, we all want clean air, so this is a desirable like outcome. This is just a picture from India in like before and after like the COVID, and so this adds to existing literature about the importance of doing both together. Yeah. So in this last bit, like I'm just gonna speed through this because I really don't have enough time for this. But another emerging chemical sink of OH is atmospheric hydrogen. Like, why would we even think of that? So sorry, I have the headers up for some reason. I thought I removed them. I took these slides from something else. Just bear with me. So why is there growing interest in hydrogen nowadays? Like there's like financial market hype, and like just kind of showing here like if you invested in hydrogen now, like you would have profited, but this is not updated as of yet. There was money pouring in from the US government up till recently, and then because there's a potential to help reduce like some of these hard to abate emission sectors, and it can also help with like helping with energy storage from renewable energy, and hydrogen leakage can come the same way that natural gas leaks from our supply chains. but the hydrogen can react with the hydroxyl radical too. So kind of forms like this additional hydroxyl radical loss here. And when the hydrogen leaks, it actually increases surface warming, because when you reduce the OH, you actually extend methane lifetime, as I was discussing just now, and you get increasing methane, you get increasing warming from that. And both hydrogen and methane actually have very similar impacts on climate and atmospheric composition. And so some of the questions here are like, what does hydrogen do basically in the atmosphere, and how does that interact with atmospheric methane? I also ran simulations with the GFDL model to try to understand this. And so basically,
Glenn,
yep.
can I jump in? Yeah,
Yep,
just
yep,
because we're
yep.
starting to run short on time. I kind of
Yep.
wanted to recap something, or try to recap
Yeah.
something that I
Yeah.
feel like I learned from this
Yeah.
talk.
Yeah.
And I came up a little bit in the chat. Like, I think Kelly was talking about this. So if I understand correctly, within a certain range, the Earth can, it's on the screen. The Earth can self-regulate methane concentrations by the increased production of hydroxyl radicals. Is that?
Yeah, I mean,
right?
that I think, yes,
So
that's true.
we emit
Yes,
more
yeah.
methane that comes with
Yeah.
more hydroxyl radicals, which then
Yes.
reduce the methane.
Yes.
Okay, so then
Yeah. I mean,
that kind of complicates the
that's
story,
true.
the air pollution story, right? So we want to reduce air pollution, but that's also going to reduce the amount of hydroxyl radicals in the kind of reduce the amount of detergent in the atmosphere.
Yeah. There's definitely like a potential for that to happen. But I think it's hard to really like weigh like what you think is like a priority. Like, there's a lot of like public health benefits in targeting like air pollution. I think it's important to do that. And the sort of like additional like factors that you could get in from like in terms of like affecting the like potential warming from methane, like it's, I don't know, like it's up to people to like make sort of like the judgments on what they want to do. And I think ultimately, like, if we could achieve both like methane like reductions and like targeting air pollution like together, like that would be probably the best thing to do.
Right. It reminds me a bit of the ship tracks question, right? Where we've cleaned up the ship tracks, but that's kind of uncovered this extra warming because the air pollution is negative forcing.
Yeah, totally. I guess, the other interesting like bit of this is that as you have extra warming in the Earth system, you also do generate more like OH, like hydroxyl radical. And so then that is also kind of like a self-feedback in a way, like kind of dampening some.
Like, people are always disappointed when scientists don't give straight answers, right?
Right. Yeah.
Cool. Okay. Well, that was awesome. Thanks so much, Glenn. Thanks everyone for sticking through the graveyard shift. And I'm going to pass the baton on to Stella, who's going to be your host for the rest of the graveyard shift.
Yeah, hi, good morning or good evening, whatever it is for you where you're watching. So hi, I'm Stella, happy to be back on screen here. I'll be your host for the next 2 hours. I'm a PhD student at the University of Washington studying atmospheric and climate science, and excited to bring some energy for the next 2 hours. Just kind of going through our normal little spiel here. Thanks for joining us at hour 63. If you guys didn't notice, it changed up there in the upper right-hand corner, hour 63, which means only 37 hours to go. which sounds like not a lot, but still a bit of time left to tune in. So we've seen a lot of great talks so far. This next speaker is going to be a really cool and maybe a little bit different experience for you all that I'll introduce in a second. But before I do that, just a brief reminder, all of our speakers are appearing in personal capacities, expressing their own views, which may or may not be those of other participants. And we're all here with a purpose. Americans deserve good weather and climate forecasts. And U.S. scientists have been world leaders in weather and climate predictions. This excellence is definitely because of investments by you, the public, and U.S. federal funding for science is absolutely essential. I was funded by NOAA throughout my undergrad. I had a bunch of great internship opportunities because of that. And so shout out NOAA, really grateful for all of the funding that they provide for scientists at every stage of their career. And right now, funding cuts are affecting all areas of weather and climate science, which we've heard about today. And so to help us save the forecasts, you can we have the call screen down there also to like and comment and then share with your friends. But we also have our call your representatives. If you're I guess you could leave a message at this point. I don't think any representative office you'll get through to at this point in the evening, but do feel free to call and leave a message and let them know that you care about what we're doing here. And so without further ado, I'll bring on screen Henri Drake, who will be doing a very cool interactive thing for you.
Please do. Sorry, I was just calling my representatives, but I'm back now.
Incredible. Welcome. Yeah, so like I said, we have a bit of an interactive thing for you all right now. And Henri will be leading an experiment in YouTube Plays Climate Modeling. And he has a notebook loaded that he'll introduce to you all.
Yeah. All right. So I'm Henri. I'm a climate modeler. And I spend a lot of my time looking at screens like this. So what we're going to do today is, instead of giving you a talk with polished results, we're going to start from the very beginning. So actually, the chat is going to tell me what this talk is going to be about. So I've got this programming notebook loaded up here, where I've already loaded in a bunch of climate model data. And it's a bunch of output or data from a global climate model. So the whole globe, we have a few sets of years here. I've loaded in years 2005 to 2014 and 2090 to 2099. So it's a future prediction or projection. And we've got a bunch of variables like temperature, precipitation, pressure, clouds, you name it, just the atmosphere though. And yeah, I guess, what does the chat want to see? So just to give you a sense of what we can do here, I'm gonna just plot what the temperature looks like in 2010. So I'll do ds_hist. This is my data set where I have historical temperatures. And the variable for temperature is called TAS for surface temperature. And you can see this data set here is almost 1 gigabyte, 700 megabytes. And I'm just going to do a simple thing. I'm going to average in time and make a plot. And so now this is calculating the plot. So it's calculating the mean, and then it'll make a plot in a few seconds. Okay, so while we wait for that, there it is. Okay, so let's just digest this for a second. So the color bar here is the temperature. The units are degrees Kelvin. So maybe that's not very familiar for some of you. So let's convert that into Celsius by subtracting 273.15. That's more like it. So here we have temperatures in Celsius. So you can see that Antarctica, well below 0 degrees Celsius. So it's freezing down there, freezing in Greenland, freezing in the Himalayas, and much warmer in the tropics and around the globe. Okay, so that's kind of what we can do here. We have, the data is for every day for these 10-year periods. So from 2005 to 2015 and from 2090 to 2099. So my director, I guess, will help me maybe parse through the chat because there's going to be a lot of stuff going on. Okay, so someone said, Claire said, I've got wildfires on the mind. I think, unfortunately, this model doesn't have wildfires in it, but I could be wrong. We can maybe, let's see. Okay, so the variables that I have, and maybe help me out here, Stella, because I don't know what all these variables are off the top of my head. Let's start at the top.
Best guess.
Okay, I think this is going to be albedo. This is total cloud. This is humidity. This is precipitation. This is sea level pressure. This is radiation of some kind. This is surface wind. This is maximum temperature in a day, minimum temperature in a day. We got winds. And we've got geopotential heights. I don't think we have fires, unfortunately. All right, we've got Natasha Bitter asking for precipitation in Los Angeles in 2099. So let's see if we can load that up. So I'm gonna just comment here. So give a title. This was our test analysis of temperature in Celsius. That's an S. Okay, so now we're gonna start a new chapter. This is, does it rain in the future in LA? Okay, so right now I've got temperature loaded, and so we need to get precipitation. Thankfully, I actually have precipitation loaded over here because I anticipated this. So we're going to do the same thing. We start with our data set, and now I'm going to get the variable PR for precipitation and 2099. So I'm going to select just the year 2099. So now my data set, which used to be 700 megabytes, almost a gigabyte, it's now 10 times smaller because we just picked 1 year out of 10. And if we look here, we have all of the days in the year 2099. So, okay, so now let's just make an average over time and get a look at what this precipitation plot looks like. And then we can zoom in on Los Angeles. Okay, so here's the precipitation. Notice that I haven't actually plotted the continents, but you can kind of see where the continents are here. So while I'm doing this, can someone in the chat look up what the coordinates of Los Angeles are? It's like longitude and latitude. I don't actually know off the top of my head because I'm gonna have to select those out. Okay, so right now we don't have units on this plot, so it's not very helpful what these numbers are. So if I look into my data set here, what's cool about this climate model data is that these variables come with a ton of metadata. So even though this thing is just called PR and it's a little bit vague, we know that the variable itself is precipitation, and its units are in kilograms per second per meter squared. So it's basically what is the weight of the drops of rain that are falling down in a little box 1 meter square by 1 meter square every second. Okay, Kelly's got coordinates for us. So I'm now going to select the longitude is minus 118.2426. And the latitude is 34.0549 north. Okay, so if I run that, it gives me an error. The reason is because even though this looks like I have data everywhere, I actually don't have data for the exact point of that coordinate in Los Angeles. So what I need to do here is I need to give it, I don't need the exact point, I just need the nearest point in the data set. So if I do that, I get this. So let's call this precipitation LA 2099. Actually, this is the whole. Yeah, so this is precipitation in LA. Okay, and so this is now the precipitation at the longitude. Okay, so I made a little mistake here because, so the longitude is 118 west. but the problem is that my longitudes go from 0 all the way to 360. And so essentially what I have to do is I have to count backwards from 360 and subtract the 118. So if I do ln 360 minus 118, that should give me the right longitude. Okay, so I think that's right, but just to make sure this is correct, I'm going to do the same plot as before, but now I'm going to plot the coordinates of LA on top of that plot just to make sure that it shows up where we think it is. And I'm going to make this a big red dot. PRLA.
And I'll just say that figuring out the latitude-longitude system that you're in is a classic problem in atmospheric science and geospatial data. So
yeah, for sure.
Not alone in this.
Okay, so does that look like we're in LA? Is that the right spot? I think so. Yeah, okay. So you can kind of see that there's the coasts. I mean, even though we're just plotting rain here, because the continents and their position has such a big influence on the rain, you can see the coastlines. Like here's the Andes, and there's a bunch of rain right on the shoreward side of the Andes. Okay, so we've picked out LA. So now let's see what the precipitation looks like in LA. And actually, this is still all 10 years. So from 2090 all the way to 2099. So I'm going to select, again, just year 2099. And now let's plot this. Oh, I still have to tell it which variable. All right, so that is the precipitation in LA in 2099. So what do we think? What's interesting about this? All right, so while people comment on this plot, I'm gonna catch up on some of these comments in the chat.
Chat to people.
Yeah, okay. Oh, sorry, what's up, Sal?
No, go for it. Go for it.
I just noticed Natasha has a follow-up, which is, can you do comparisons between years? So we can do that. I just need to do the same thing, but this is precipitation in LA historical. And I think that should be all I need to do. Cell time equals 2010. So we're doing 2010, yeah. Okay. So I am plotting them on the same plot, but right now the axis is time. And so it's not the most helpful plot. So instead what I'm going to do is just plot them as a function of day of the year. And then they'll be overlapping. Okay, so there we go. So let's put some labels on this plot, because right now you probably don't really know what's going on. So let's call this, so this one is 2099. This one is 2010. We're going to add a legend to this plot, and let's add some labels. Day of year. Rainfall rate, kilograms per meter squared per second. Okay, there's our plot. So what's the interpretation here?
Can we get some more interpretable units on the plot?
What do you mean by that?
Like, can we convert to millimeters per hour so folks have a sense of what that means?
Yeah. Okay, so
it's 3,600. If you multiply, I think it's 3,600.
Oh, you actually know the number?
Kilograms meters squared per second. I think if you just multiply, or maybe you have to divide. Wait. It is 12 a.m. Hang on.
Okay. Hey, let's do this methodologically. Okay, so kilograms per meter cubed. So we need the density of water, which I happen to know because I'm an oceanographer. Oh, actually, that's salty water. This is fresh water. So that will give us into meters per second. So then I'm going to look up how many inches in a meter. Okay, so inches per meter is about 39. So if we do kilograms meter squared second, 2 inches per second, that should be that I divide by row water and then multiply by inches per meter. Okay, I think this is right. Okay, so what we're doing right now is trying to get the plot into inches per second because that's maybe more intuitive for people. And maybe inches per second is going to be a small number. So let's do inches per day. So 8,600 is how many seconds there are in a day. Okay, I think this is right. Normally you don't do science under stress like this, so I would be much more careful if I was like doing this for real science.
Coding in front of people is really hard. We gotta.
I think this is right. I think we just did it, everyone.
That looks like the correct units. Yeah.
Yeah. Okay, so we now have, for the year 2010 and the year 2099, we've got daily rainfall rate in inches per day. So we have one day in 2099 where in LA it's raining 3 inches per day. Does anyone know if that's a lot? I don't know if that's a lot in LA, even though I live in Orange County.
That's a lot. That's a pretty huge rainfall event.
Yeah, but we also get like atmospheric rivers with a lot of rain, so
right.
I don't know how much falls during those.
I mean, we get like 2 inches of rain in an atmospheric river in Seattle.
Oh, really?
So,
okay, so this is probably an atmospheric river. Actually, we can figure this out. So let's look at this atmospheric river. All right, we're just going all in on this. Maybe we can do another thing in the second half of the hour, but we're going to try and understand what's going on this one day in 2099. So the first thing I need to do is figure out what day this was. So if I take my time series, so this is the rainfall in, I still need to select 2099. So let's just make a new variable so I don't keep getting confused. Okay, so I have all of these numbers, and we can actually look at the values of these numbers. Okay, so these are actually all the numbers in this data set here. And so it's kind of hard to pick out by hand which of these is the biggest one. So what I'm going to do instead is use some programming magic. So if I do IDX max, that will tell me what day was the one with the most rain. And so it was February 7th, which sounds about right for an atmospheric river.
Yeah.
So rainy day was 2099. Okay, so so what variable should we look at to figure out where this this atmospheric river is? Did anyone go to atmospheric river talks? I didn't actually get to see any yet.
That's a question.
Although actually I heard.
Yeah.
Yeah.
I haven't heard
humidity. Oh yeah, that's good. Okay, so now we need to load in humidity. So let's do that. So this is going to be our humidity. I think it's called HUR. That's specific. Do you know, Stella?
Probably. I actually tried to look up a table, and
Nice.
did not succeed.
All right. Well, I think this will be relative humidity. Hopefully, that's good enough.
Proceed with that assumption. Yeah.
Yeah. All right. Well, I guess while that's loading in, we can look at what the temperature is doing on that day. Maybe there's something interesting there. So if I look for that day, oops, and we plot the temperature. Okay. Well, I don't know what I was expecting to see, but actually you can kind of see that there's some like sweeping feature. Let's zoom in on LA. 200 to 280. Enhance. I don't know anyone. I don't know everyone. I don't know what we're seeing here. I think this is like just cold in the mountains. And then it kind of looks like there's some warm tropical air getting swept up. Maybe that's his atmospheric river. Okay, we're still loading in the humidity.
While we're loading it in, there's a question in the chat about like what CMIP is and what specific, when you say CMIP model output, what model made the output and what scenario are we looking at versus the historical?
Yeah, these are all great questions. Let me walk through that. So we are looking at a specific climate model that is developed by NOAA GFDL, the Geophysical Fluid Dynamics Laboratory. This is also the laboratory that Glenn, the previous speaker, did his PhD at. I did my postdoc there. They're the ones who invented climate models, so they've been kind of at the top of the game for a long time. And this is their Earth system model, which means that in addition to simulating things like atmospheric temperature and winds and the ocean, they're also simulating biogeochemical cycles. So like the carbon cycle and methane and all of these other aerosols in the atmosphere. It's basically the most comprehensive type of climate model that we have. And this is their version 4, which is the one that they published in CMIP 6. CMIP 6 is the Coupled Model Intercomparison Project, version 6 or phase 6, which came out in around 2015, 2018 or something. And it was basically a collection of the world's best climate models. So, there's like maybe, I don't know, 8 contributed by the US, but then a bunch from all around the world. In total, there's something like 40 or 50 of these. And what's cool is that in these models, they run all the same exact experiments. So they have the same emissions into the atmosphere. They try to run a historical simulation from 1850 to 2015 as realistically as possible. And what that means is that you can compare all of them against each other, which is really, really valuable. In this case, because we're just doing a live demo in 1 hour, I just have one model. But normally you would want to probably compare this to a bunch of others to see if you have robust results. Okay. Any other follow-up questions? Oh yeah, so then the scenarios. So I have, for 2010, this is the historical scenario. So 2010 is in the past, so we know what happened. We know what we emitted in the run-up to 2010. And so that is just trying to simulate reality until the present, basically. But then for 2090, obviously that hasn't happened yet. And so we need to make some assumptions about what humans are going to emit as we go out into the future. And so that's what they're doing in this scenario called SSP 370. So we can break down this code a bit. SSP stands for, Stella, do you know? Oh, you're muted.
It's shared socioeconomic pathway.
That's right. Yeah. Shared socioeconomic pathway. And they have 5 of these. And this is number 3. That's what the 3 here means. And so do you know what the third one is?
It's a middle one for sure. It's not 2.4. It's not, yeah.
I think it's like the competitive future, right? I think it's a future where basically all of the countries become kind of like nationalist and insular and like go all in on like fossil fuel like development of their own countries and stop trade. And anyway, so like
yes,
social scientists are doing these kinds of this modeling of what future countries might do and what that means for emissions of carbon dioxide and whatnot. Yeah, Rocky Road, that's what it's called.
Rocky Road, regional rivalry. Yeah.
Yeah. And then the outcome of this is a radiative forcing of 7.0 watts per meter squared by 2100, which means that all the emissions that we put in the atmosphere are heating the planet at a rate of 7.0 watts per meter squared by 2100. So that's the simulation. So this is like kind of a sort of a worst case scenario, both socioeconomically and in terms of climate that we're considering here. Okay, and feel free to follow up with questions. So I think what we'll do is I'll do some analysis, and then while we're waiting for like the next step, we'll break it down and answer questions. Okay, so, oh no, this is not the variable I thought it was.
It's, yeah, what variable did you?
I got HUR. I don't know what that is.
Yeah, so I just was sent, let's see, relative humidity is HUR.
Oh, really? Okay.
Yeah, were you looking for specific or relative?
It says this is pressure. Oh, that's the coordinate. Okay, no, this is right. Yeah, this is relative humidity. Okay, so this is a slightly different variable because the variable we were looking at before was surface temperature. So it, by definition, only existed at the surface. So it was only a function of longitude, latitude, and time. But now we have this, the relative humidity also, we have it at every pressure level in the atmosphere. And so what I need to do is just pick out the first one. So surface rel hum is, I pick the first of the 19 pressure levels. Okay. And now we want to pick out this one day. So the rainy day. And we're going to plot what that looks like. Oh, I have to plot the variable. I just realized we never even plotted the precipitation on this day. Okay, so maybe this is a little bit too low of a pressure. Let's go a little bit higher in the atmosphere.
Henri, could we add the like national borders or state borders? Is that like something you could do easily?
Yeah, I can figure out a way. Let me think.
It's a little bit annoying because I think you'd have to load in Cartopy and then.
No, there's some hacky ways. Like we can find a variable that has a mask that's just land.
Ooh, yeah.
That's what I was thinking. Oh, actually, yeah, I know what to do. I've got my own little functions that I can do fancy stuff with. Hold on one moment.
This is like fancy coding right here, everyone.
This is what happens when you work with the same models for like 8 years. You develop your own little library of functions so you can do stuff this fast. Okay. Okay. Well, while that loads, we can break this down a bit. Okay. So I'm working on adding in the borders of the continents, but for now you can kind of see that this is North America. Here's South America. Here's Greenland. The reason that some of these are white is because these are high elevation areas where there's actually no pressure this high, right? The surface pressure at these locations is lower than 900, or what was this, 90,000 pascals, so 900 millibars, I think.
Yes.
Yeah. Okay, so anyways, for now, this will do. So we're picking kind of like a low slice in the atmosphere, which is basically kind of like, I'll guess maybe this is like 1,000 feet in the air or something like that at like most places. And we're looking at the relative humidity. So you can already see all these different swirls going around with high relative humidity. And I think we were right that this is an atmospheric river that is bringing moisture from the tropics up, crashing into Southern California.
Whoa, very cool. Can you tell us more about exactly like why you think that from looking at the, can you like, I don't know, maybe zoom in a little bit on your screen and move your mouse around?
Yeah. Well, the reason I wasn't doing that is because I'm still loading in this other thing, but I think I'll just quit that for now. Okay, so let's see. Actually, can you look up what specific humidity is? I think we'll be able to see it better if we do that.
Yes, we need to shout out Miriam here because Miriam found the table and sent it to me. It's HUS.
Oh, I see. Okay. So I'm going to load that and clouds in while we while we do this other stuff. So let's do surface temperature. I think that's total cloud and specific humidity.
And we also have a question about the swirling eddies that we see over the ocean when we plot relative humidity. Why does that happen, Henri?
Yeah, so these swirling eddies would actually happen everywhere, I think. It's just that we're only really seeing it over the ocean because we have these weird masks over land because there's mountains and things. But these are, well, okay, let's first back up and notice that there aren't really the same swirls in the tropics. And so this is because at the tropics, the effect of Earth's rotation isn't very strong. The effects of Earth's rotation on flow. But then as you get away from the tropics, the effect of Earth's rotation on the flow starts becoming dominant. And so things start wanting to kind of swirl together. And so all these swirls are basically extratropical storms of some kind. And the reason that they show up in the relative humidity is because they're taking air from somewhere where it's moister, like the tropics, and like bringing it, yanking it down or up to higher, towards the poles, basically. This kind of model, unfortunately, it's too coarse. So each of these pixels here is about like 100 miles. And so we can't actually simulate things like hurricanes in this model. So that's why we're not seeing like little swirls of hurricanes, because they just don't exist in this kind of climate model. Yeah. Okay, so let's zoom in on LA here.
Also interrupting, specific humidity is HUSS, and I might have told you incorrectly. I think that HUS is a monthly mean.
Okay.
Yeah. Thanks,
Let's try that.
Miriam, for that in the chat.
Wait, actually, I don't know if I have that. Let me just check what I have. Oh yeah, HUSS. Cool.
Okay, cool. Yeah.
Oh, but that's going to be a 3D, whatever. We'll just do it. It's going to be bigger, so it'll take longer to load, which is why I'm thinking.
Let me check what HUS 850 is. That's not in the table that Mary. I mean, I know it's HUS at 850, but I don't know what its dimensions.
That's fine. Okay, so 20 to 50. So now I'm just zooming in on kind of Southern California area for this plot. And I went too far away from the coast. Oh, Nice. Okay, I think I've got land now. Let's see here. Oh yeah, we've got a land mask.
Yay.
All right, there's our continents. So let's make this a contour plot. Let's make the colors black. All right, beautiful. Oh. Okay, I think this should work. There we go. Okay, so I think this is around, I mean, I don't know what these, I guess these are like Catalina and the, whatever these islands are. I forget what their names are, but I think this is Catalina.
Baja California. Wait,
oh,
no, I think,
yeah,
wait.
you're totally right. That
I
is
think Baja California.
Yeah. Okay. So in this model, Baja California is actually an island chain, I guess.
Nice.
Yeah, that's what happens when you have a model that's 100, where each pixel is like 100 kilometers wide. You get some kind of funky things like that. Okay, but so we're now seeing this relative humidity, like LA. Oh yeah, we have the coordinates for LA. So if we plot, let's plot our red circle. Yeah, there it is. So now we can see we have this really high relative humidity. So remember, relative humidity only goes up to a maximum of 100. So let's set that maximum and the minimum to 0 and replot this. Yeah, okay, so when it's yellow, that means that it's like as humid as the atmosphere can get, basically. It's saturated. And here we have this air that's nearly saturated coming up from the tropics and smashing into LA and dumping a bunch of rain on the same day where we found was the most rainy that it gets in the year 2099.
Nice.
I think that's pretty conclusive.
Yeah, I think so.
Okay.
I feel like people have lots of questions about ARs in the chat, but I'm hoping that we have another talk about ARs coming up sometime in the next 37 hours.
Yeah.
That someone's going to give you all really good answers to. Not that Henri could not, but let's keep...
I probably could not. I'm not an expert on ARs, although I've been through enough of them since I've lived in Southern California now that I'm starting to learn.
Yep.
Okay, so let's pick another topic maybe. Do you want to pick, Stella?
We also have questions about like temperature in the Midwest out at the end of the century.
Okay.
I'm from the Midwest.
Yeah, we can do that.
That sounds interesting.
Yeah, let's see. At the end of the century, so okay, so Emilio Castaneda asks, can we please see what temperature, precipitation, and humidity in 2090 to 2099 looks like for the Midwest? Wondering about what climate change impacts on crop production. All right, so I'm just going to take my land mask so that way we know where the continents are again and bring it over to this notebook where I already loaded in all this data. So we're looking at surface temperature. Let me bring it down to this section over here. So we ended up doing, did it rain in the future in LA? So conditions in the Midwest in a hotter 2090 to 2099. Okay, so surface temperature, let's just average over all 10 years and make a plot. And let's add our land mask. Let's just reuse that code I wrote down here. Okay. All right. Should we get this in Fahrenheit? Okay, so
Yeah, the chat's having some arguments about metric versus, yeah.
all right, let's just go with Fahrenheit. So I'm making a little function here, Kelvin to Fahrenheit, or if I give it a temperature, it'll convert it. So take a temperature and I subtract 273.15 and I add 32. No, I multiply by 1.8 and then I add 32. Yeah, I think that's right. All right, there's temperature in Fahrenheit. Let's zoom in on the US. 20, 22, 300. Okay, so this is kind of a saturated color bar, so let's change the limits to, let's say, like 32 to 80. Okay, so it looks like, actually, let's do a different kind of plot.
People in the chat are saying they stayed up past their bedtime to watch because this was so addictive. So I think you're doing a good job.
That's great. Okay, so we've got, this is the average temperature over all 10 years in from 2099 to 2090 to 2099 in the Midwest. Maybe what we need is the reference point. So I'm going to also do the same thing for the historical for 2005 to 2014. So I'm going to start loading that in as well. And then once that's done, we can add it on. Okay, so this is surface temperature. So you can already see that this is like the Rocky Mountains. So these are colder at the surface. Actually, they're so cold that at the top, even in a future climate, they're pretty close to freezing on average. But then in the Midwest over here, we've got average temperatures about 60 degrees Fahrenheit. Okay, so what should we plot next here?
And we're still loading in the comparison data.
We actually just got it, so let's put that up side by side for a comparison. So I'm going to do historical on the left, climate change on the right. I'm just doing this these magic functions to make the plot look good. And that should work. Okay, there we go. So let's add some labels here, I guess. Average temperature 2090 to 2099 on the right. Average temperature 2005 to 2014 on the left. Okay, so we have 2005 to 2014. So in the Midwest, we've got this color, which I think maps onto somewhere between 48 and 56 degrees Fahrenheit. And then if you notice in the future, that these bands have basically shifted one whole temperature band southwards, right? Northwards. So they are getting basically one whole band, or like 5-ish degrees warmer in this like worst case scenario climate change.
Yikes.
Yeah.
as a reminder to the chat, this is one choice about what the future could look like, not a definitive pathway.
Yeah, this is the worst, kind of the worst case.
But climate change is bad, folks, as Miriam says in the chat.
Yeah.
Um,
All right. So I don't know enough about crop production to know how temperature would affect it, but maybe we can look at precipitation. Although I didn't actually load that in, so let me get that loading and then we can maybe look at that in a sec.
yeah, if the person.
Oh, actually, oh, sorry, what's that?
Oh, I was gonna say if the person that asked that question wanted to tell us in the chat what they think that means, go for it.
Oh, that worked really fast, I think. Maybe I could just do the same thing, but really quick with precipitation. Okay, I'm not sure why the precipitation is not working right now.
People are interested in moisture content of the soil layer.
I don't think that's one of the ones that I have kind of preloaded.
Totally fair.
Well, we can check. Let's see. So these are the variables I have.
Yeah,
so
the user says it's MRSOS.
Doesn't look like
Doesn't look like we've got that. Sorry.
Yeah, I've got surface pressure. I've got a bunch of these radiation things.
Yeah, I don't think we have the land variables right now, but appreciate that question. Can we plot maximum temperature values, like maybe over a certain month, or we could do it for the Midwest too, just to see.
Yeah, we can do that just to see how they compare.
Yeah.
Okay, so let me see if I can load those up. Let's do max and min.
Nice.
Okay, that's getting loaded. Yeah, so I'm thinking I want to see clouds too. I feel like chat has like clouds. Yeah, I'm seeing some clouds in the chat.
Clouds. Yeah.
Okay, let's see what I've got over here. Things are loading still, so maybe while this one's loading, let's do precipitation also in the US and compare the two simulations. I think that should work.
Okay, fantastic. We have the chat hyping you up. Lots of goat emojis.
I'm pretty sure that's my grad student. Well, these are all my grad students.
Okay, that's cheating a little bit.
That's hilarious.
That means you're a good advisor, though.
Okay, this is still loading. So this is the average precipitation between the two simulations. It's a little saturated, so it's kind of hard to tell what's going on. Well, let's look at the maximum, maybe. Or the quantile. Let's look at the top 99 percentile.
And if we could convert our units to inches again, that'd be super cool.
Yeah, that should be easy. Where did we do that? Here we go. Okay, I don't remember what this quantile function is, but I think it's something like, yeah, okay. So this is looking at the most, like the 1% most extreme rainfall over this period. I think that will work. So the title will be wrong, but why did that not work? Let's see. Oh, I see. I was doing it over space as well, and I need to just do it over time.
Nice.
Okay, while that one's going, we can plot the clouds. By the way, this is what I usually do, is I have two of these things going so that while I wait on one, I get the other one. I sometimes pretend it's twice as efficient, but actually it just makes me have like multitasking brain, and sometimes nothing gets done.
That's exactly how I code too. And Miriam was saying, I think that that's how she codes as well. And so it's nice that we kind of scroll around code and run multiple things at once. But we kind of all do that, maybe not alone.
Yeah. Okay, I think this is clouds. Oh, but this is probably going to be throughout the atmosphere, right? Do I have to pick a pressure level? No, this is, what is this? Total cloud cover percentage. Sweet.
We are getting clouds for the chat.
Yeah. Okay, here's the, so this is precipitation rate. This is the 1% highest precipitation rate averaged, or out of the years, on the left, years 2005 to 2014, on the right, 2090 to 2099. It is the 1% rainiest days, or the rainfall on, no, it's the, okay, it's like, it's the rainfall of the 99th percentile. Stella, do you have a better way of explaining this?
Out of all of the, I mean, it is 1 a.m. I don't know if I can explain it better than you just did. Yeah.
Okay, let's just call it extreme rain.
Extreme rain.
It's a measure of how extreme the rain is. Let's just leave it at that. And let's pick a better color bar so we can see how this compares. Okay, and then here's our clouds. So this is average clouds. On the left is, again, historical. On the right is the future. And I don't really see any obvious changes, but you can see some interesting patterns. So Southern California, not very cloudy along the coast and along Baja California, but then off over the ocean gets pretty cloudy. Up in Vancouver, Seattle, Canada gets pretty cloudy. I guess in Quebec it gets cloudy. I didn't know that.
Yeah, and how does it
this
look
is assuming the model's any good. We should also be like comparing to observations, but we don't have the time for that.
in model land?
Yeah, in model land it's cloudy.
And what does it look like? Can you tell like kind of what looks like it's changing between the two?
I can't really tell any changes in the clouds here, but I don't know, maybe there's obvious changes if we zoom out. Let me just set the minimum and maximum, and I think we're getting close to the hour, so.
Yep.
All right, let's just do global clouds, and let's just do 1 day. Well, we can do that below. Okay, there's our global clouds.
Cool.
And then let's just pick a single day. So this is average clouds over 10 years, current climate, future climate. I don't really see much change in the clouds. But you can see there's a dot, which I think is Hawaii, where it's really cloudy.
I mean, it looks like there's like a little bit of a change in the like stratocumulus decks off the coast of South America.
Of South America?
Like in the Pacific. Yeah, well, it looks like there's. I'm squinting to be clear, potentially making.
Oh yeah, no, It looks like there's more.
Looks like, yeah, it looks like there's a change in how that's
Yeah, actually, over Africa, it looks like there's less clouds.
right. But then maybe less clouds over the Amazon.
Oh yeah, way less clouds over the Amazon. Yeah,
I have some theories for that. Yeah, cool.
interesting. This is a single day of clouds.
So that's the eddies that one of our users pointed out, right?
Yeah, you can see all these extratropical eddies, these swirls. And then over the Amazon, it's like just completely covered in clouds.
Yeah, lots of big storms there.
Cool. And then here's our extreme precipitation. So if you remember one thing from a bunch of the talks today, in a future climate, the most extreme rainfall gets rainier. And that checks out in this model. Looks like maybe a 20-30% increase in the rainiest days, which is kind of in line with what Isaac Held was saying. We get based on Clausius-Clapeyron relationship.
Incredible. All right. Well, thank you so much. You have made it an entire hour successfully live coding in front of an audience of over 400 people. So can we get some appreciation for Henri in the chat again for taking on that task. I hope it was fun for you all. It was really fun hearing about your questions.
Yeah, thanks for the great guidance. My nightmare was that there's going to be no one in the chat, and I was just going to have to like type random things into the void.
Thankfully, Tumblr made sure that didn't happen. So
yeah,
yeah.
All right, thanks everyone. Have a great night.
Alrighty. Yeah, thanks, Henri. I'll go ahead and take you off stage. Alrighty. So yeah, thanks so much for engaging with us as we experimented with some Jupyter Notebook magic. And as you may have noticed, the hour in the upper right-hand corner has now changed to hour 64. So shout out to y'all for being with us. Good evening or good morning. I guess it's definitely morning, wherever you are. I'm personally here in Seattle, Washington, where it is the lovely hour of 1 a.m. And excited to welcome you all to another great set of talks. And so as a reminder, brief reminder that all of our speakers are appealing in their personal capacities and expressing their own views, which may or may not be those of other participants. However, we are here with a purpose. We definitely are if we're here at 1 a.m., right? Americans deserve good weather and climate forecasts. And U.S. scientists have historically been world leaders in weather and climate predictions. We've done a lot of really cool things, including develop some of the first climate models, right, at GFDL, as Henri was talking about. And we have this really cool unparalleled network of observations, right? So much data, weather stations, satellites, planes, balloons, boats, floats. And all this excellence is because of investments by you, the public, and U.S. taxpayer dollars, and that federal funding for science is super essential. And we are here, right now at 1 a.m. or 4 a.m. or whatever time it may be for you, because funding cuts are affecting all areas of weather and climate science. Yeah, I guess personal testimony is I actually did my qualifying exam for my PhD yesterday, and I passed, but I'm exhausted, but I'm here right now, though it's 1 a.m. because I really care about the future of climate and weather in this country. And we really need to make sure that these funding cuts do not drain us of our ability to do good weather and science and keep the people of this country safe. And so to help us save our forecasts, please make sure that you are tuning in, sharing with friends. And we also have a 5 calls link, as we've been highlighting, and I know it is 1 a.m., but if you are like me and you might get scared of calling your representative and hearing them talk back to you, you can call and leave a voicemail at your representative's office using the 5 call script that's scrolling across the bottom of the screen. All right. So without further ado, I'm going to go ahead and bring our next speaker on screen, Dr. Ian Faloona. Hopefully I said that right. He is a professor of atmospheric science at UC Davis, and he'll be talking about dirt, wind, and fire, air pollution in the 21st century. Thank you so much for being with us, and take it away.
Hey, Stella, great to be here. Thanks. Welcome. Hello, all you fellow night owls. I just, I wanted to tell you a little bit about some of my work that, of course, relies on so many other people's work. And all of that, most of it is funded through federal agencies. So I'm gonna highlight that as I go along here. But what I wanted to talk about was how our understanding of air pollution, and we have had some great triumphs in the past 50 years or so in cleaning up our air, but how the nature of air pollution is really changing in the 21st century. And so it's not going to be like the pollution we had in the 20th century. And so I wanted to talk about some of the main issues there and how we've discovered this through continual observations in that are funded by the US EPA and NOAA and all these federal agencies. So let me just start by mentioning why there's so much interest in understanding air pollution, and that is because it is the leading environmental cause of death worldwide. Their estimates, vary. It's not perfectly certain, but the numbers somewhere for air pollution in particular usually come around 6 or 7 million premature deaths across the globe per year. And if you think, well, there's 8 billion people or whatever, and that's something there's something like 60 million deaths per year globally, just to put it into context. So 1 out of 10 of those is a premature death due to air pollution, which I think is pretty fascinating, and therefore makes it very important to understand this phenomenon in our atmosphere and in our environment. So this study came from Lancet and several years ago, but it put up the other sort of leading causes of environmental death. And I also just patched on there COVID-19 for the 2 years that it was really at its peak. It was killing a little over 2 or 3 million per year. So air pollution is doing that twice that every year. So it's an important aspect. If you look more closely at the US, those numbers usually come in more like a couple 100,000 per year. If you look at California, where I am, it's about 20,000. Most of that's due to particulate matter, so I'm going to talk about that. But ozone is also central to both production of particulate matter and its own air pollutant, which damages tissues and crop yields and can actually affect the amount of carbon that the biosphere soaks up in principle. So ozone's really important and central to our understanding of air pollution. And it's also linked to global climate change because it is the third most powerful anthropogenic greenhouse gas. And that is something that we sometimes overlook. This bar graph might be a little too much here, but if you look at these reddish colors, so CO2 is the biggest one, of course, greenhouse gas. Methane is the other one you've probably heard about a lot. But tropospheric ozone is right there. That other bar is, that third bar there, tropospheric ozone, is pretty close to methane. It's almost as powerful as methane. Just as an aside, this yellow colored bar here that they've plugged on top of the methane bar, and there's nitrous oxide there, but then this halogens they call, these are the CFCs and their replacement compounds, but mostly the CFCs from old ozone hole days. So it turns out, had we not limited ozone, these CFCs that were destroying stratospheric ozone, this is a different type of ozone, but had we not limited that, we would have, turns out those were very powerful greenhouse gases. And so had we not limited it, this yellow bar would have been about 3 times bigger. And so we would have had a lot more global warming due to that. So I'd like to point out that we have encountered these big environmental crises in the past, and we have risen to the occasion. So the American Lung Association every year puts out sort of a list of the 10 worst cities, or most polluted cities. And this top list here is for ozone, because you can measure how bad is the air by ozone. And the bottom list is by particulate matter, usually called PM. And the maps on the right are from the US EPA, which track through monitoring across the nation, track which counties are out of compliance. And I'll get to what that means in a second, but that's what those colored little county maps are on the right. So you can see there's a smattering of places across the country for ozone in the upper right there. But of course, California is still number one. This is really, California was kind of birthplace of air pollution science, really, and thanks to LA, but also throughout the state. And you can see that we're still having a hard time passing the crown here. We still have really a lot of air pollution problems. And so 6 out of the 10 most polluted cities in the country, whether by measurements of ozone or PM, are in California. So I also wanted to point out that there was also an interesting study that came out. And now when I'm referring to these other studies, I want to put in parentheses who funded them. And so this was a study that was funded by the National Science Foundation and NOAA, looking at PM across these sort of Western states that don't have really big urban centers where we traditionally would have particulate pollution. And these researchers noticed that there was a slight beginning of a trend upwards, so that something else was being impacting the air pollution across this broad area of the northwestern US, and that was wildfires. Okay, so this is the kind of data that the US EPA, monitors, collects, analyzes. It's a huge project. Those colored circles on the left are all the monitoring sites that the EPA takes care of, calibrates, maintains, and you can get this data at the site called Air Now. It's a really fun site you can play with. So I put this link up here, and this is giving you the air quality index, which is usually some sort of combination of particulate matter and ozone, sort of the two dominant air pollutants. And just to point out something here, you can see in the north, right into the near the Canadian border, you can see this probably effluent from those wildfires in Manitoba. You can see that in real time here, thanks to this monitoring network. And then in terms of, you can also go to the APA and get this data going back to 1980s. And this is a picture of all these different pollutants that they've been monitoring in this network and how they've changed over the past 3.5 decades or so. And now, of course, they're all different measurements, but they all reference them to what's called the air quality standard is. That is the U.S. Clean Air Act of 1970, and then amended in 1990, determined what the sort of upper limit of air pollution should reasonably be to protect public health. And so that's usually called the NAAQS, it's an acronym, the National Ambient Air Quality Standards. And so that's what each of these pollutants is sort of referenced to. So you can plot them all in the same figure. And I've colored some of these. So SO2, back in the day, that was a big problem for acid rain, but you don't hear about that anymore because of the success in regulating that and reducing the emissions we have and the quantities that are in the atmosphere. PM is this purple one. PM 2.5 is usually what they mostly care about because they're smaller than 2.5 microns in diameter, and therefore they get into your lungs more readily. But this one you can see hasn't gone that far below the NAAQS. This is the national average, by the way, right? And then the green one is ozone. And it's also sort of dancing around that national average. So notice that the green and the purple, it's really PM and ozone that are still problematic. Most of these other what are so-called criteria pollutants from the Clean Air Act have been cleaned out pretty successfully. So we don't really usually worry about those, but it's this PM and ozone that we primarily are concerned with. And that's why they go into making the air quality index, which I'm sure you've seen in your typical weather forecast. They will try to predict, for example, what the air quality index is. And so it's these two, and these two are a little tricky because they're secondary pollutants. So it's just another map. Again, on the left is the ozone counties across the country as of this spring that are out of compliance, that is above that standard for ozone. And then the one on the right is the PM 2.5. Now, this is adjusted because last year, the US EPA, as in accordance with the Clean Air Act, every 7 or 8 years, they compile all the data that's known about the health impacts of these pollutants, and they revisit, hey, what should that threshold be? What should that air quality standard be? And last year they lowered it from 12 to 9 micrograms per cubic meter concentration. And so this map on the right is a prediction of what counties now are going to be out of compliance with this new standard to protect public health. And you can see that most inland California is out of compliance, and a bunch more counties across the nation are, because of this lowered standard, which again is a result of our deeper understanding of how much these things affect health. So I just want to let you know that where does this come from? We said it's a secondary pollutant. That is, it comes from other pollutants that are, we call primary pollutants, that are directly emitted. And usually if you talk about atmospheric chemistry, air pollution, you'll see some sort of cartoon like this with lots of processes and places where the sources are and where the sinks are. And then there's all this chemistry going on. I don't want you to necessarily grok all that in just a glance, but really just realize that ozone, both ozone and PM 2.5, the main air pollutants that go into generating the air quality index, they come from these precursors known as VOCs, volatile organic compounds, and NOx, which are nitrogen oxides. And both of these have sources that come from natural sources like forests emitting the smell of the forest, those pinings that you smell in a pine forest, for example. Wildfires also put out these VOCs and also NOx. And so they have natural sources, but they also have, of course, what we call anthropogenic sources. And those are the things that we've been cleaning up to achieve those improved air quality over the past several decades from that last figure. Okay, but now we've been successful in that, but what my belief is, and what I'm trying to present and make clear to people, is that these, what we used to call natural sources, specifically for NOx, I'm going to focus on NOx because that tends to be, we've done such a good job limiting that from our anthropogenic sources that it really seems to be, that's the thing that's controlling a lot of the chemistry that produces ozone and PM. So what we've learned, though, is that it also comes from soils, particularly when you put down a bunch of nitrogen as fertilizer on soils, and then microbes in the soils start using that and then leak some of it out into the air as these nitrogen oxides. So there's a soil source which is natural, but it's modified by agriculture. And there's also wildfires, which, we used to think of as natural, but we know that we are affecting the climate, we're affecting the forests, and therefore we're affecting the wildfires. And this is a really nice study that came out a couple of years ago showing how the wildfires of the 20th century, this is a 15-year period from then, are very different than the wildfires of this century. And those orange dots are showing you 99th percentile big fires in terms of area burned relative to this first period in the 20th century. And then the dark red ones are 99th percentile in this second period here in the 21st century. So you can see that the amount of wildfires are increasing and the extreme large area burns are also increasing. And this is, happening in the West, like I said, where those air pollution, the PM has observed to be rising in this Pacific Northwest and throughout the Western states, but it's also happening, in the South and Texas, and it's happening throughout the country. Lightning is another natural source, but it's primarily east of the Rockies where that impact is biggest. So I'm not going to really focus on that. I'm going to focus on the Western states and California. So in California, these are color-coded regions that we tend to think about as air basins, because in the old days, it was like pollution was a local idea. And then if you had bad air quality, it was because you were doing something. It was emissions within your air basin. But of course, this picture has expanded, and that's not really exactly the case anymore. Yet we still kind of section things off this way. So these are color-coded into the Sacramento Valley, the San Joaquin Valley, Southern California, the Los Angeles Basin, San Diego area, and I put Coachella on here for just for fun, someplace I've been studying recently. But you notice that in the 21st century, the first couple decades, there's been this continued decrease. But what happened around 2015, 2016 in California and also in the other places across the West is it just stopped improving. And so you can kind of see that here. And this is ozone up here. And even if you look at PM 2.5, a similar thing happened. The trend that we were all used to, it was sort of, as people like my age or even younger or older studying this air pollution, we came of age understanding that it has been decreasing because of the regulations we've successfully implemented to improve the air. But something's happened now where it's just stopped as of the last about decade. So that's what I'm really interested in talking about. Some of our work that I've done with colleagues at NOAA involves just simple like curve fitting. So you don't need to see the details of all this, but just taking these monitoring data. Again, this is publicly available data that comes from the US EPA, very easy to download and play with. And so we took it from all over the place and started just doing these long time series curve fits just to get these ideas of shapes. And what we noticed is that there are certain places where it's just not going to come down to that national ambient air quality standard anytime soon. It seems to be plateauing off. And we think and then we did this for sites all across the whole continental US, but in the Southwest in particular, this is all these offsets that we found. This plot here on the right is a map of these offsets. That is, where is it plateauing? It doesn't look like the ozone's going to get any lower than these values. And these values are very close to that national ambient air quality standard right now. And so what we've kind of concluded just from looking at these observations is that something is preventing continued improvement of the air. And so what we did was we assumed that it was linked to wildfire prevalence and soils, which for climate change reasons are both increasing. And so we did this across several urban areas here in this figure and tried to separate out what we thought was due to those wildfires. And the light blue is also due to background ozone, which is another question which I won't get into here, but it's just sort of the natural background that's happening just due to all the global chemistry before it arrives on the western shores of North America. But the point is still that these air quality standards that we're at now, there's just very little room for us to regulate our local emissions to improve it anymore. Something else is happening, and we believe that something is wildfires and soil. Those are the two, I would argue, main things that we don't have enough understanding of and are increasing to sort of prevent further improvements in air quality. So again, without getting into all the details, the bottom line for the soil emissions is that because we apply more fertilizer than plants need, approximately twice as much, that nitrogen it's reactive, it sits in the soils, and microbes just start to use it metabolically. They just start shuttling it around, oxidizing it, reducing it, back and forth, and a bunch of it leaks out as NO, this precursor gas, and that is temperature dependent. So we use more fertilizer just as we grow more, but we also the soils are warming, and so the emissions are increasing. So that's the soil source that we think is important. And the other one I just wanted to mention, because it's so incredibly critical in the West, is this wildfires. And so this is the area burned here on a semi-log axis. And what you notice year to year is that there's this just continual trend. This is a line fit here, this red line, but of course, because it's a log axis on the y-axis, that's an exponential curve. And so that has a doubling time of about 20 years. So the average area burned in this decade is twice as big as it was at the turn of the century, which was twice as big as it was in 1980. And so this is an alarming thing. And the main meteorological variable that seems to correlate with this is called vapor pressure deficit. It's basically relative humidity. It's how dry the air is relative to how much the air, how much water vapor could exist in the air. And as the temperatures warm, it turns out, this is a fascinating study that came out thanks to research funded by NOAA and NSF, that in the Southwestern, in particular, the Southwestern US, climate models have the relative humidity approximately staying the same over these decades, but the observations show that it's actually drying out. And so if we wanted to predict how these wildfires are going to change and how they're going to impact our air quality, it's very challenging to do. And one of the underlying meteorological variables driving this, relative humidity, is not even fully understood. We're not capturing these long-term trends in this region of the world. So those are the main points I wanted to make. We've done some satellite studies, again, thanks to funding by the USDA, which funds 2/3 of my effort due to the Ag Experiment Station at UC Davis. And we looked at satellite studies in these various regions across California. And we saw, this is for NO2, this is part of the NOx, that in the forest regions, the NOx is actually increasing over these 12 years of this study. Urban areas, it's still decreasing, this red line, because we are improving the vehicle fleet. You know, we're electrifying that. Emissions are lower. That's fantastic. But then in regions of like croplands and shrublands and those exurbs, there just doesn't seem to be, NOx hasn't changed in a while. So these are observations from satellite, which really tell us that something's going on where we're no longer improving these emissions of this primary pollutant in regions outside of the urban cores. And so that's where I want to stop to give a couple of minutes of discussion. But I just wanted to point out that, you know, we made great improvements. As we learn more, we realize our health is really sensitive to the quality of the air, and that the things that are influencing our air quality are changing dramatically as we sort of careen into the Anthropocene, and we affect these other sources, which traditionally we haven't really fully understood, because they're different than what used to be the main source, which was, of course, fossil fuel combustion. So I want to stop there just so we have a couple minutes of questions or discussion.
Yeah, for sure. Thank you so much. Yeah, we do have a few questions in the chat, and I know one is maybe outside of your area of expertise, and you can totally punt this if you don't feel like you're comfortable answering it. But there's some questions about air pollution and air quality and impacts on human mental health. And about how that affects human mental health.
That's a fascinating one. Well, like I said, I mean, the profusion of scientific information coming out about this, it really is mind-boggling. I mean, the more we look, the more we find, particularly PM, this particulate matter, it has impacts on, yes, cardiovascular, all kinds of health impacts, but now people have been finding that it is linked to, cognitive decline. They found in certain studies as well. So definitely there's that aspect. I wouldn't be surprised if, as we continue to study this, that there are definite mental health impacts, just because, you know, the systems are all connected. What people really found out during COVID was that places that were had really persistent air pollution problems just had worse outcomes in COVID. So there was definitely a link between continued exposure to particulate matter and negative outcomes from a respiratory virus. So, but yeah, mental health is a great question. I think it's a ripe field for study.
Absolutely. Yeah. Thank you so much for that answer. I'm sure folks in the chat are interested to hear that. There's a question about I'm going to maybe try to reword this question for you, but which things in the last decade have maybe risen the fastest, or if anything is rising in terms of our air quality measurements, and what was most unexpected?
I mean, so the wildfires, I think, you know, they're so erratic. It's funny. So they, you know, I showed you this sort of simple exponential curve, but each year is so different. 2020 was literally off the charts. So you had to sort of expand our figures to include that. And then 2021 was also bad, but then the last 3 years have been relatively mild. I mean, the loss of structures in LA in January was insane, but in terms of area burned, it hasn't been that large. So I feel like people's thoughts about wildfires kind of waxes and wanes with what's, when it's happening. But you can see in that study by Iglesias I showed you, this long term over many decades, you can see that it's just changing behavior. The fires of this century are not like the fires of last century. And so to me, that's the most sort of terrifying element, this just 20-year doubling time of area burned. I mean, at some point you're going to run on the things to burn. So to me, that's sort of, I think, the most shocking. And the fact that we're probably not going to forecast it that well if we can't get the humidity right in these places. And then it has all these other factors that are complicating in terms of biomass and how much growth happens in the wet season and then dries out, and these sort of details of the meteorology, which are complicated, and then ignition sources and all of that. But to me, yeah, I think in the last few years, what I've become so shocked at is that figure I showed you, is just how rapidly the area burned, it has been increasing in the past couple decades.
Yeah, absolutely. That's a scary answer, but a real one. So thank you. Yeah. I guess maybe as a follow-up, this person asked if we're starting to introduce relative humidity in climate predictions and wildfire predictions.
So not that I know of. This is something I talk about whenever I go out into conferences and things. And I haven't heard a lot of discussion about, I don't think we exactly know why the models are not picking that up. I mean, it's got something to do with some sort of land surface feedback, I think. But, we generally think globally that as the temperatures rise, the evaporation rates off the oceans are going to rise. And so you're just going to have more water vapor. And people generally have thought that relative humidity shouldn't change too much. But something about the arid climate of the Southwest is not behaving that way. So no, I don't think anyone has a really good explanation. I mean, I'd love to hear it if someone knew of anything. But I just read that paper last year, and I was floored by it because it was so surprising.
Yeah, absolutely. Okay, let's see. Are there other questions in the chat here? We have stuff about burning forests, changing things from carbon sources. Well, yeah, so natural forces are normally carbon sinks, so maybe like carbon sinks to carbon sources would be the question. I'll reword a little bit. Like if we burn enough of our forest.
Oh, yeah. Well, I mean, yeah, that's right. I mean, there's regrowth that happens really rapidly. But yes, in terms of, I'm not exactly sure how it's going to affect the global carbon cycle. I mean, it's definitely not helping. Yeah, but I don't know. I don't know what it does to the long-term ecosystem. I mean, that's a good question. I'm just not really familiar with the vegetation dynamics in post-fire regrowth, which I think is something that we're going to need to do as well. Like not only take care of the forest to sort of minimize or control burn, but we're going to need to really think about how we replant these things. Because right now, I believe a lot of the invasive species that regrow rapidly after a fire are also very flammable. So that really brings up a good point that we need to be much more intelligent and proactive about how we seed those fire areas, because it is important.
Yeah, great. Thanks for answering that question, even if you're not a carbon cycle person. Appreciate that. I guess maybe one final question, and I appreciate you staying on a little extra for questions here. I know we answered some of this, but maybe just a recap of you talked about satellite data. You also talked about some of these different ground-based networks that you use. Who manages all of these networks, and maybe just a recap of where the funding comes from.
Right. So the networks, most of the networks data that I showed you came from the US EPA. The states also do some. So the California Resources Board which was really the model of the US EPA. The California had an EPA first in the late 60s, and then the national one was sort of modeled after that. But so there's some of that, but primarily it's the EPA that maintains that whole network across the continent. Satellite data that we used came from NOAA and NASA. So that's generally who does that type of perspective, and linking. Yeah, so those are the main sources, I would say, but it's just, and the access to this data, I was just teaching a class on environmental monitoring, and the undergraduates, just, we have such access to so much data now. Like, if you're just a curious person, there's just, because it's publicly funded, because it's publicly available, it's really not that hard to come up with a question, and you can just start digging in with the available data now, and people are so much more adept at large data set manipulation that it's really impressive what you can do just as a sort of a curious bystander without having to deal with all of the details of like maintaining this massive network of instruments that are continuously making these measurements. So I don't know if that answered, but those are the main sources for funding. But it's funny because and I was going, typically in science, we'll do the references and there'll be a name and a year in a journal or something. But I started going through and just saying, hey, who funded this? Because they're usually always written in the acknowledgments. So it's interesting exercise to go through and just say, oh yeah, this, boom. And it's so much of it comes from our federal agencies. It's just phenomenal. Like, if you think about what you know as a grad student or any level you're at, it's when you link it back, you're just like, wow, there's this huge machine of knowledge that's been publicly funded for so long. It's just phenomenal. It's just really impressive that we do this.
Yeah, absolutely. Yeah. Shout out to our federal data resources. Absolutely. Yeah. Thank you so much. All right. Well, we will let you go. We've held you a bit extra with questions. So thank you.
Oh yeah, I'm always happy to talk about it. Thanks so much for what you're doing, and thanks for giving me this chance.
Yeah, absolutely. Appreciate the late hour for sure. Yeah. So thank you to Dr. Faloona.
And congrats on passing your qualifying. That's no small feat.
Thank you. Thank you. Yeah. Hoping to take a nice rest after all of this.
Yeah, good job. All right.
All right.
Bye, everyone.
Yeah. All right. So I am going to bring Miriam on screen. I don't know why I'm introducing her like this, but you all know who Miriam is.
Hello.
from the chat, the one and only. I think our next speaker might be experiencing some connectivity issues. So I've got Miriam on screen here with me to chat.
Just hang out. I think you need more congrats for passing your qualifying exam. That's incredible. I mean, at least in my program, that's the last time they can kick you out for a while. So it's a huge deal.
Yes, that is also the case in our program. Yes.
Job
so
security.
Cool. We're good. Unless I like fail my generals, then we're chilling. We're good. Yeah, I guess, does the chat have questions that like they think that Miriam and I could answer?
Yeah, we could talk about like becoming grad students or something, because that's if there's anyone who's thinking about it, that's maybe something we can be that's useful.
Yes.
Especially in #these times.
Exactly. We do have expert knowledge about grad student in these times. Yeah,
explain what a qualifying exam even is.
Oh,
that's
well,
jargon we're using.
It's jargon, and the great thing is the jargon is different in like every program. And what it means and what year in your program you might take an exam is different in every program also. And it also varies between every program, like within atmospheric science and also between disciplines. Like, so not, this, like, what I'm about to say might not hold in literally any other context. It might be completely specific to the UW program of atmospheric and climate science. And actually, it just changed this year. But what it means for us is it's like the exam you take after your second year of grad school, after you finished all of your master's classes, and you talk about your master's work, which for me is a manuscript that you write. Usually you write one paper for your master's degree, and you like talk about all of that. And then for us, we also get quizzed on like all of the kind of general concepts that we should know to be an expert in our field, or to start being able to form our own independent research questions in our field. And it's like a 2-hour oral exam with your committee, which is a bunch of people that are really smart, just asking you questions. It's quite intimidating, but a fun time. Also, it can be both. But in different programs.
That's great that it was fun.
Yeah, it was a little bit fun. It got a little intense, but it was fun. Because one of my advisors is like from not located in UW, and she came and we got to chat in person, which is always really fun to talk about science in person.
Oh, that's great.
So, yeah, it was a good time.
Oh, nice.
That's a qualifying exam in this
I
program.
guess yours is pretty similar to the one that I went through in the new version. I have heard horror stories because I'm at Columbia, sort of. I'm affiliated with NASA KISS, but we're part of Columbia, but all of the Earth and Environmental Science department is mostly at Lamont, but it's Earth and Environmental Science, where I do like climate modeling, hydroclimate extremes, atmosphere, land stuff, but there's people who do like exoplanets and volcanoes and all sorts of other stuff there. And apparently the qualifying exam used to be like all of Earth science. So there was a professor who was infamous for showing up with a bag of rocks to like atmospheric science students, dumping them on the table and being like, "What's that?" Fortunately, they changed it like a few years before I started, where it was like, they have to be able to connect the question to your research. It could be like a tangential. It could be like, how does this mountain range affect this wind pattern that affects your region of interest or something? But they have to be able to connect it. They can't just be like, "Tell me what this type of rock is," because I would simply never pass.
That sounds so intimidating. I think it'd be kind of fun, but in like the worst way possible.
Especially if you've like never even considered studying that. I'm like, I think some rocks are pretty, but I couldn't identify them.
Yeah, no. My house collectively, I live with a geophysicist and a geologist and an oceanographer. So I think if you put all of my house together, we could pass that exam, but not independently. Not at all. Yeah, that's crazy.
Yeah.
I think there's some people in the chat that are asking what our research is like generally on, which is like always a very stressful question to answer live without any sort of preparation.
Yeah.
I don't know if you're further along in your program, so I feel like you get the like answering that question first.
I can try. I mean, you think I'd be better at this considering I have to hand in a draft of my dissertation within the next month. The short answer is I'm trying to figure out if we'll be able to end droughts in the future. So kind of similar to that question that Ari was showing with the code, like will rainfall patterns change and or dryness patterns change such that we'll be able to end these droughts in the future in places that are already drying, like the Mediterranean and the US West.
Yeah, absolutely. That's super cool. I am also like super interested in hydroclimate stuff, so that your work is super cool. I know Lily and I, yay hydroclimate things. I think our next speaker is potentially here, and we're just gonna wait for her to get her slides uploaded, which is cool. But while we do that, I also think about the hydroclimate, but like specifically right now on the mesoscale. So I'm looking at like mesoscale convective systems, which are these like storms, really big storms that dominate rainfall in the tropics of the world, and they matter a lot for rain in that part. They also matter a lot for energy balance due to a bunch of other complicated things. But I'm looking at how they can be studied at different resolutions, because we have like really cool global cloud resolving models where we can like model things at really high resolution, and we also have these like reanalysis data sets that are at like 25 kilometer resolution, as well as our GCMs. And none of it's really doing mesoscale systems well because none of it's really designed to do the mesoscale well. And so the rain that happens due to those storms doesn't really get captured. And I'm kind of trying to figure out why, and also how it changes under climate change, how the mesoscale precipitation changes under climate change, which is how rain changes under climate change seems to be a theme.
That seems like a way harder question than what I'm looking at. You're like, we can't even do this. It's broken.
It's broken. I mean, I feel like that's when you work with observational data, you're like, oh, it's all, there's like flaws with all of it. And then there's also flaws with the models. And then you're like, oh.
But then if like, I mean, the nice thing about Model Land is you can just be like, here's all the flaws, and that can be half your paper.
Yeah. Yeah. So true. Yeah. I feel like, yeah. Well, I mean, with reanalysis and satellites, you can be like, we compare them to each other and their flaws are the whole paper. So you're like, actually, yeah, we don't know which is the truth, really. Well, we know that our satellites are more truth than our models constrained by satellites, but there's a lot of confusing things here. And yeah, so what a mesoscale is, sorry to not like say that is kind of silly, but we think of mesoscale as like basically anything that's like larger than like a little, like a tornado, like larger than a tornado, or like larger than like a small thunderstorm that happens like over a mountain. All the way up to, and usually including like a tropical cyclone, like a hurricane. So like, yeah, kind of like think about it like from really small thunderstorms to really big thunderstorms. But so like they can be like the sizes of states, which is kind of cool. Like you can see like you find like papers where like they show one over the entire state of Missouri, just like engulfed in an entire cloud shield. It's kind of cool. So yeah.
Here's a question for you. With mesoscale, meso means middle, right? So is it just like not the super biggest storms and not the super smallest things, just but like that huge middle?
It's
because I feel like I see it all the time.
It's a pretty huge middle. I mean, I think that like obviously there's like different scientists define the scales differently, and there's also like, at least like when I took mesoscale meteorology in undergrad and also in grad school, there's like alpha, beta. Like you can break the scales down even further, which like to be clear, like for thunderstorms you don't really do, because thunderstorms can be any size.
Yeah.
But yeah, I don't know. I feel like there's and the other confusing thing, not to like, but like the mesoscale in the ocean and oceanography is completely different. Like it's a different set of scales than the mesoscale in the atmosphere, which is just really weird. And I wish we would agree on that, but we didn't agree on it when we started our fields, like
they did, well, they're like coupling the ocean and the atmosphere was such a big deal because these groups simply didn't talk to each other at all.
Yeah. Nope. But now we're like all in the same buildings everywhere, which is pretty cool. So yeah, that's pretty great. Yeah. Folks in the chat that are asking if people still need speakers. I think that we might be all full actually going forward.
Here we are.
But
we have a little bit of a wait list going in case people message us to say they're dropping out. But so far, I don't know, I'm kind of pleasantly surprised that like we've had all these people sign up and basically everyone has shown up. It's really, really cool.
It's been super awesome. Yeah. We got everything plugged in, including like the really crazy times, which is awesome. So yeah.
I think like our main slippage has only been technical difficulties, which is unfortunate, but like it is sort of the nature of the beast.
Doing things online. Yeah. Yeah.
Yeah, they're saying, should we go for more than 100 hours? I think that we all would simply fall down behind the scenes.
One of our organizers suggested their next attempt was going to be 100 days, which made me want to throw up a little bit. I was like, don't say that. Don't speak that into existence, actually. Yeah, I don't know if we could take that.
We already started so big. Like, obviously, the next step is just, several orders of magnitude bigger, but like,
right. An infinite, never-ending conference that you are the organizer of every single day. Yes. Someone asked if we are interested in communication of science to lay people and if we take time to practice communicating.
I love thinking about communicating science to, I would say, just people, mostly because if you spend enough time in our departments where they're combining all these different things, like I'm talking to people who have no idea what I do and they have no idea what they don't have any idea. I don't have any idea what they do. It's 4:30 in the morning, 4:50 in the morning. I'm sorry. Anyway, but like, I'm going to answer the second part of that question. But for my opinion, like spending a lot of time with the kind of deniers or the naysayers, if they're in your family, it's maybe a different story if you're interested in cultivating that relationship. But seeking out like people on the internet who have differing opinions about, basic facts isn't a useful way to spend your time or their time, frankly. I think that we've had a couple speakers bring up the 6 Americas before, where it talks about people who are in denial all the way to people who are super activated. The people that are in denial, while they might be very vocal online, and you might see some of them in the comment sections of these videos, they're completely outnumbered by the people who even just care a little bit. Like, talking to people who care a little bit but aren't activated is so much more valuable than talking with people who are like very aggressively anti. Yeah, it's just like, it's no fun. It makes you sad and everybody goes home mad.
Yeah, absolutely.
But also, like, just communicating in general, climate is the most important thing you can do.
Yes. Yeah. Big fan over here of communicating science. I think a lot of the folks on these calls, right, are like super pumped about getting to talk to people about science in general. And yeah, I mean, I think that's one of the biggest things in academia is sometimes it feels really frustrating. The science is super inaccessible and in language that only folks that know that exact field can understand. And I think, yeah, making sure that our science is able to be read and understood and used by a wide range of people is really, really important. And so we actually are going to bring our next speaker on stage. She's been having technical difficulties, and so she does not have her slides here, but she's joining us live from a conference, which is super cool that she's taking time to talk to us from a conference. And this is Dr. Susana Hancock, who I can find the introduction here in a second if I can scroll correctly through my slides. She is a polar scientist and a global glaciers researcher at the International Cryosphere Climate Initiative. So Dr. Hancock, could you tell us about what conference you're at and what you're presenting on, maybe?
Absolutely. Thank you. And thank you for having me. And thank you so much for running this 100-hour marathon. It's fantastic. It's been great to watch and great to support. And I'm very grateful for you. So yes, as I said, my name is Susana, and I do polar and glacier research. And glaciers, my area right now with them are actually glaciers outside of the polar regions. So I'm currently in Dushanbe, Tajikistan, which was part of why I'm having technical difficulties with geo-blocking. But I'm here at the high-level international conference on preservation of glaciers. So I will talk about that a little bit, but let's see. Right. And so, so I spend part of my time doing fieldwork in polar regions. That's really where my heart has always been. And so as part of that, I ski across polar ice sheets as a way of generating enthusiasm and excitement for these regions of the world, and to really show firsthand how fragile they are. I've had times where I need to, I'm out on the middle of the Arctic Ocean in the ice, and it's melting, and I'm trying to ski, and I'm up to almost my knees in slush, and barely holding myself in the snow, and that I have all my gear with me in a sledge, and trying to figure out, do I have enough time to get to more solid ice, or where can I go? And so I've retraced a few historical expeditions that I've been able to do, which has been fantastic. Oh, yes, excellent. Got some slides.
We got your slides after 22
wonderful.
minutes.
Wonderful, excellent. So yeah, I can just, I'm basically at the beginning, so that's fine.
Yeah, if you just give us a condensed version, that'd be super great.
Yes. Yeah, and so I'm here at this conference. It's part of the it's a UN mandated event, part of the International Year on Glaciers Preservation. And this is to raise ambition, to raise policy and scientific innovation on the preservation of glaciers. So this image here, and I've got 4 images that you can scroll through the next couple, are just of, an ice glacier collapse, the Birch Glacier in Switzerland in Valais region that collapsed the other day and spared a town. They had early warning for it. 300 people lived there. They were able to evacuate, and they were able to even airlift all the livestock out of the area. There's 1 person missing, but otherwise it's an example of really how glaciers can actually impact communities. They're not something that is so distant and so far away. And that's really what we try to communicate. So if you want to just go through a couple of the slides. Just showing, so this is just, seeing the debris that landed on top of this village. It's about 2 kilometer, 1.2 miles of debris spread, and you can go again. And so this is just a lake that is formed, and we're now warning communities that are downstream that they may have some flooding as well, but it's flooding the remaining parts of the village. And one more. All right. And so as part of my work, so there you can see the debris and then the flooding right on top of it. So as part of my work, I'm also involved in the UNFCCC climate negotiations. So since the first COP in 1992, we've lost 8 trillion tons of ice. Atmospheric carbon has risen from 350 parts per million to now more than 431. The last time it was at this level was 2.5 million years ago during the Pliocene, prior to the time of Homo sapiens. So, and emissions have destabilized land masses or ice masses such as Greenland so much that we have still committed a minimum of 27 centimeters of sea level rise, even if we have no further melt, which of course our temperatures are rising, our carbon in the atmosphere is rising, and our ice is continuing to melt. So if you want to, so if you want to advance. So as a cryosphere scientist, cryosphere being the cold, frozen parts of the planet, I really underscore the costs of loss and damage, and that they will be more extreme, with many regions experiencing sea level rise and water resources well beyond the limits of adaptation. And both, in this century, certainly, if our current levels of emissions continue. And mitigation will certainly become more expensive and costly due to these global feedbacks from the loss of sea ice as well as the thawing permafrost, in which the Arctic has recently been confirmed as a source of emissions, their permafrost, rather than a carbon sink. This slide is supposed to advance. So I don't know if you try advancing it. It's got an automation in it, which is just, no, okay. We'll skip that. But that's just showing how much ice is actually preserved under a low emission scenario versus a high. So the point is that it's significant, but you can skip to the next one then. And so I'll just say that, many current NDCs, or nationally determined contributions to the Paris Agreement, are not insufficient to prevent a significant overshoot of this 1.5 degrees, with many governments delaying meaningful action to 2040, 2050, or even beyond. And while this is perceived as short-term advantageously, it is also, because, for example, lowering energy costs, this slower transition away is also securing widespread future losses and damages for decades, centuries, millennia to come. So this slide just demonstrates that our NDCs we're at about 2.7 alignment right now, would lead to escalating loss and damage throughout the century. So I've got several regions here: Caucasus, Middle East, some Asia, Central Europe, and part of the North Americas. And this shows how much ice is lost at different temperature or carbon levels in the atmosphere. So what we can see is that, nearly all tropical and mid-latitude, I don't have tropical on here, but tropical and mid-latitude glaciers are rapidly crossing thresholds that would lead to their eventual complete loss. And even the big water towers of, say, some high mountain Asia are still going to lose about 50% of their ice. But we have the capacity to really mitigate that. And so you can see that blue line that demonstrates quite a lot less ice that's lost if we do follow a rapid drop in emissions. The difference between following a 1.5 path and, say, our current track at 2.7, and this is our current track for policy, not our current track where our actual emissions are headed, is about preserving about half of the ice. So we could save about 54% of the ice we have now if we stayed by the end of the century and beyond at 1.5, whereas we'd only save about 24% if we are at 2.7. And again, we're more on the sort of track for 3.3 or so. So if you want to advance. So here, again, I think this has an animation that didn't quite come through, which is fine. So just apologies for the little bit weirdness on the slide. But one issue that we're looking at outside of the polar regions here is the impacts on the water cycle that we have with permanent, effectively, on our human lifestyles from the losses of snowpack and ice. It's affecting the growing seasons. So we're seeing both this more water initially as more melt, and we have rain on snow impacts, and then less water as more and ice melts and there's less ice to melt. And this water is also melting earlier in the season, so that we are having, say, floods when we want a little bit of water, and then drought when it comes time to harvest, for example. So if you scroll forward again, and so I'm just going to rush through this a little bit. But again, we're looking at, higher than our, again, sort of our 3.3 degrees. And so if we continue to rise in emissions, the loss and damage is going to be extreme, well beyond, again, the limits of adaptation. 10 million people today are currently at risk for high catastrophic flooding events and glacial lake outburst floods, especially in places where we don't have these early warning systems. So in Switzerland, that happened this week, we did. And there was a huge disaster a year and a half ago in India, and they weren't able to warn people, but they now know that they could have. They had the symptoms that they could have warned if they were able to catch it, but they don't have the funding to be able to do that. So instead of measuring in lives saved, they're measuring their events in lives lost. So if we go forward again. Is that the second? Yeah. Oh, okay, here we are. All right. No, we can skip this one. That's fine. Go ahead. So again, we're talking about polar regions, we're talking about ice and glaciers and land ice, whether they're in Greenland and Antarctica, even we've got glaciers in Indonesia, very small, but Europe Alps, the Americas, the Rockies, etc. These impacts are not local. They're very widespread. So here, for example, we've got Belize, and with 1 meter of sea level rise, this is what Belize may look like underwater. Now, we know that this is going to happen with our current committed ice loss, but it could be very possibly within the next 25 years if we continue our current emissions. And if you advance again, and this next slide is Belize at 3 meters. You can see that a significant portion is now lost that we didn't see before. And this could be within the next century. And so this is again just showing the same slide as before, but just looking again at that blue line to show that if we were to take a very low emissions situation, we can keep a significant portion of ice. Although in certain places we still, as I said, lose significant amounts. But what we see here is that by the end of the early next century or two, we may start to see some ice regrowth, which could be one of the early symptoms or symptoms of the planet rebounding from our high emissions situation if we were to rapidly reduce emissions. And that most communities around the world will stay within the means of adaptation with 1.5 degrees. I believe we now know in a study that came out 2 days ago that each 0.1 centigrade that we exceed 1.5 degrees, we lose 2% more ice. So it's a pretty rapid change. So, it's 2 degrees can't be the backup to 1.5. It's got to be, 1.51, for example. Each of that 0.1 adds another 2% loss by the end of the century. And if you want to advance,
I think I'm gonna have to cut you off there. If you have a final point you want to go for,
if you want to go here. This is my final. I'll just let people read this for a moment, and then if you want to go to the next one, just as a wrap up, just what we're looking ahead is that emissions have got to stop. That's really the only solution. Glaciers and ice, it's global. What we do in America impacts high Asia. We can't, problem shoot anything, target shoot. So very important for policy action, and very grateful for everybody who's working in the sphere. So thank you very much.
Yeah, thank you so much. Really appreciate this talk. Clearly really important to get context on glaciers and really policy relevant area of this field for sure. I think we have a lot of really great questions in the chat. Unfortunately, I think we are going to have to move on for time, but I just want you to know that people in the chat are engaged and interested in what you had to say here. And thank you again so much for being so patient with all the technical difficulties and coming to us from across the world and in a weird time zone and with internet difficulties. Really appreciate you being on the call.
Yeah, well, thank you very much for having me, and great to be here, and thanks for doing this.
Yeah, for sure.
All right, thank you.
Alrighty, yeah. And so now, if you saw the ticker in the upright corner should say hour 65, so I'm gonna change it back. And we not to rob anyone of an hour, but I think we changed it twice accidentally. And so I'm gonna hand it over to the next host, Virginia Shortt. I don't know if I'm saying your last name correctly. Maybe I'm not, and please correct me if I'm wrong. But she's going to take it away from me, and I am going to go to bed. So thank you all so much for joining us on the Graveyard Shift, and passing over the mic now.
Thank you, Stella. So my last name is Shooty, and I did not know that until I married my husband. So thank you for trying. You did great.
Thank you.
All right, have a good night. Good morning, everybody in the comments. It is delightful to see some of you that I have been in this time block with for the last several days. I will see you. Oh my gosh, someone just yelled my name in all caps. Listen, it's still just 5:04 for me. I'm still just barely awake today. But I appreciate your energy so much. I am going to be with you for the next 2 hours again. And then at the end of my 2 hours, I am somehow giving a talk for myself. So let's see, in the middle, I don't have a husband making tea for me anymore, so I might go off camera for like a little bit so I can make a second dose of tea for myself. But it's so great to see some of y'all that I've been hanging out with in this time slot. I'm so curious, if I haven't been interacting with you the last 2 days, where are you tuning in from? It's been a very global crowd during this time slot so far, and I'm very excited to see who here is new to me, at least, and where you're tuning in from. While you are putting your responses in the chat for me to look at in a second, I just want to remind everybody why we're here since we're at the top of the hour. It's because we all know that weather and climate is really important, or somebody told us that it's really important, and we should come watch this live stream to figure out why exactly that is and what it's like for the people who are working on weather and climate science. We've seen so many great talks. We have a lot to go. This is top of hour 65, math 35 hours to go. This is so exciting. And I just want to remind y'all that the reason we are doing this is because weather and climate science in the U.S. has been specifically very impactful. U.S. scientists have been world leaders, and they have developed computerized weather forecasts, computer models of climate impacts of carbon pollution, unparalleled network of observations that's not just in the U.S., but covers the ocean and other places in the world. The excellence in the U.S. science scene has been because of consistent investment by the U.S. public for decades in dollars and in terms of supporting the infrastructure as well. That funding is under threat right now. And I don't mean under threat by a little bit. I mean entire divisions are being proposed to be cut or restructured in ways that is shuttering labs, that is short staffing weather stations. I'm not sure I've said this in the live stream yet, but my hometown in Eastern Kentucky no longer has 24/7 weather coverage from the National Weather Service, which is part of why I was really excited to sign up and do this live stream, because this means something very personal to me. And if you want to do something about it, it's not hopeless. We're not done, right? Like, we were always going to wake up today and do something that makes the world a little bit better. So if you want to do something about it, you can follow the link that's in the description to this video. People have been periodically putting it in the chat. And so you can call your representatives if you're in the US, tell them that you want science to remain funded, and you don't have to be an expert or a scientist yourself to be able to do this. That link that you see on the bottom of your screen has all the information you would need to contact your representatives and tell them this is important to you. And I just want to reemphasize to everybody in the world that something you can do to generate support for science is just talk to the people around you that you know, that trust you, about how you think science is important. This is one of the most powerful things is studies show, science shows that people often think they are alone in caring about something that is hugely important. And it can feel discouraging when you feel alone. It can feel like it's all going to be awful forever. But just talking to one another and realizing, oh yeah, we all actually are worried about this and want it to be different, that can be really helpful. So I'm checking the chat really, really quick to see where y'all are from. Austria, Italy, New York. Oh, New York. Good morning, early morning person. Oh my gosh, you're listening from an airplane flying over Michigan right now? That's incredible. Hello to the sky from the ground. It's so great to be with all of y'all here. I do want to hand it over to our next speaker right now. And our next speaker is Robert. Robert, good morning, or good time of day. What time of day is it for you?
Good evening. It's a little past 2 here. I'm also in the Bay Area in California. So
Okay. Well, with that, I'm just gonna let you take the stage.
fantastic. Okay. So I'm going to be talking to you guys today. I'm actually going to be flying blind. I only have one monitor, so to click through the slides, I'm not going to be able to look at the actual stream. But I'll be talking today about the California Delta and a network of flux measurement towers that I work with in my PhD, and that depend upon federal funding and generally approach the issue of subsidence and carbon markets. I'm not going to be talking about that so much today, but if anybody in the chat is curious about how that factors in, I can answer those questions too. So because we're a little past the hour, I'm just going to get right into it. So the two real entities that are at risk in my life right now due to lack of federal funding are Ameriflux and FluxNet, which is the global sort of network of networks that acts as a repository for flux data, which is the foundation of all the science that I do, all the science that many of my colleagues do as well, both in Berkeley and internationally. So just quickly, some acknowledgements. These are the federal funding entities that I really depend on. Department of Energy supports Ameriflux, and also NSF supports FluxNet and many of the fellowships that employ me and others in my lab. And just a quick plug that my advisor is going to be giving a talk at 3 p.m. Pacific, 6 p.m. Eastern. So tune in for that if you're interested. He'll be talking a lot more about the global breathing of the biosphere and a much more synthesized version of the type of science that I'm going to talk about today. So first of all, a quick note about water. For those that aren't native to California, they may not be as familiar, but it's sort of a reality of ours that we're in a state of constant drought. And more importantly than that, that there's an imbalance in the geography of how water falls. So about 2/3 of it falls in the north, but most of the agriculture and most of the human beings and most of the water demand is in the south. So the linchpin of this water network is really the California Delta, right here upstream of the San Francisco Bay. And there's a large entity called the State Water Project. It's actually distinct from the Department of Water that solely exists to transport water from the north to the south. It's a very, very important function in the state, and it supports a multi-billion-dollar economy. So why is this important? Why am I talking about this? The delta itself is where we do all of our research. We monitor directly fluxes of carbon, water, and energy. And historically, it was a large expanse of tidal wetlands. So they were seasonal wetlands, and they were built up through the course of millennia from peat soils generally. So when you get flooded systems, you don't allow air into the soils, and so the soils can't oxidize. And the soils that build up there are generally very, very high in carbon, and they're different than most of the mineral soils that you would find elsewhere. They also tend to be very fertile, and as a result, after the gold rush, many of the miners and immigrants, settlers in California that struck out, moved to the Delta and elsewhere in the Central Valley and started farming. The issue with this is that because those soils are so high in carbon, they literally vaporize when exposed to air. This is a nice figure from Mountain Twist 2005, but essentially this oxidation has gone on for relatively short period of time in geologic time, only about 150 years, but it's resulted already in up to 8 meters of subsidence on some islands, and there are dozens, if not hundreds, of these islands that are massively subsided and essentially surrounded by California's critical water infrastructure. So there's a nice figure that was developed by Department of Water Resources a while ago that shows sort of what the stakes could be if there was a large earthquake, for example, in this graphic, but other scenarios could be a sustained atmospheric river, which happens all the time. It could be just run-of-the-mill levee failure from there's gophers, there's maintenance issues because every one of these islands is actually required to pay for all of its own maintenance. So essentially, if one or especially many of these islands were to fail at the same time, they would fill up with water. And because there's only so much water coming in from upstream, it would cause a vacuum effect, which would ultimately pull in seawater from the ocean into this water redistribution network. This graphic is going to show basically how quickly the salinity is likely to spike, but the upshot is that we would basically have two options: either turn off the pumps and force the entire Central Valley to switch to groundwater, depending on which time of year that may or may not even be possible, or literally salt the earth, which maybe could happen by accident if pumps weren't managed quickly enough or sufficiently. So it's going to switch right now to a little, because I'm a little short on time. Yeah, here we go. So this is over the course of, I think, 72 hours, maybe a little bit longer, about a week, and basically shows that as the tides come in, the entire system fills up with salt water, which obviously cannot be used for irrigation. So one of the solutions for this is to revert the land from agriculture back to its quote-unquote natural state. These wetlands that I'm showing in this GIF are not natural. They're rehabilitated, they're restored, and they're not even connected to to the tides. Because the islands are so massively subsided, they would become lakes. But they're so productive that they actually can result in soil accretion that is faster than sea level rise, at least in the short term. The graphic is starting over now, but I did a little bit of modeling during my PhD that just shows the risk of two levees under different management regimes. This is the relative probability of failure under different global climate scenarios. And essentially what this shows is drained agriculture, that you get more or less a doubling of risk, especially in the worst cases, but a significant increase in risk over the next 70 to 100 years. Whereas if you were to convert to wetlands, you actually get a mitigation of risk in the short term, and potentially, even into the long term, if we can get a handle on sea level rise, which is a entirely different issue, could be a long-term solution to protect these islands and thus California's water supply. So how do we get a lot of this data? We have what's called a meso network, that's what we like to call it, of eddy covariance sites. And I'll explain quickly what that means, but generally we work to compare agriculture with both impounded wetlands, like the one I just showed, and also tidal wetlands of different, varying salinities and construction types. So I'm going to assume that pretty much nobody's heard of eddy covariance. It's a relatively niche measurement technique, and I'm going to try and explain how it works quickly. It really relies on two sensors. One is a sonic anemometer. So it essentially measures wind speed in 3 dimensions at very high frequency, generally 10 or 20 hertz, and decomposes through some fancy math. We decompose that data stream into just the up and the down direction. So just the vertical component. And we match that with the concentration of whatever scalar of interest we're interested in, right? So it could, in theory, be anything. It could be some atmospheric pollutant, but generally what we do is CO2, water, and where we have the funding, methane, because that's much more expensive to measure. We measure these things at 20 hertz continuously and take the average of the flow up and down throughout that time, and we average those into 30-minute data points, of which we then compose a whole year. So the technique is very robust. It kind of works like black magic. A lot of people can't really put their finger on the specifics of what is an error versus what is systematic, but it holds true. It's been found to really match soil fluxes and all the other ways that we have to collect data. Really, its biggest strength is that it is quasi-continuous, like I said, but it also measures a large area. This is a modeled footprint. It's called a flux footprint. It's basically, we use a reverse dispersion model to estimate where our fluxes originate. And this is about, this footprint that you're seeing here is about 7,500 square meters. So it's just big enough to give us a big ecosystem sort of view, but small enough that we can actually be pretty sure what we're really looking at. It's a very useful spatial scale and a very robust temporal scale. It's also non-destructive, so we don't have to touch any of these ecosystems while we're measuring them. We can simply watch them breathe by measuring the air that washes over them. So here's some of the data that we collect. This is cumulative greenhouse gas fluxes, and it's metric tons of CO2 equivalent per acre. Sorry for the size of the axes. These are our suite of wetlands that we have active right now. There's Mayberry wetland, which is the one that you actually saw growing in that GIF. There's West Pond and East End, which are impounded wetlands on a different island, Twitchell Island, but they're located right next to each other. And then we have Hill Slough and Dutch Slough, which are tidal wetlands that are behaving very, very differently. So my advisor, Dennis, loves to use a quote by Anna Karenina. I think it goes, all happy families are alike, but each unhappy family is unhappy in its own way. And so wetlands have a tendency to all be very different and all have very particular reasons for being that way. So I'm just going to talk really quickly about Mayberry because I don't have a ton of time. So first of all, it went through 2 distinct regimes, right? You can see that it was a source. In this case, positive is bad. It's a source to the atmosphere. And then it became a sink in more recent years. But there's this inflection point in the center that we're relatively sure was kind of a 1-2 punch of disturbance. So first of all, it's Mayberry is at the western end of the delta, so it's what we call oligohaline. I'm not an oceanographer or ocean scientist at all, but generally it's not quite brackish. Or maybe it's brackish. It's not quite fresh, right? But it's definitely not seawater. Anyway, this the wetland survives relatively well in that range, but during 2016, 2017, the salinity spiked. Shortly after that, it had a caterpillar infestation, which really culled the canopy. So you can see that this is like a normal year in 2021. 2017, same time of year in July, it was culled entirely by caterpillars. It was a seasonal event. They don't come every year, and we haven't seen them revisit. But anyway, this is measured fluxes from Mayberry. In green, so basically what we do is we measure the total flux of CO2, but then we use partitioning and modeling techniques to tease out what is photosynthesis versus what is respiration, both from the soil and from plants. So the red number is a source, the green number is a sink. Generally, where the green number is higher, that means the whole ecosystem is a sink. During 2016, as I mentioned, we had the salinity year. Both respiration and photosynthesis declined precipitously. Caterpillars happened in 2017. Oddly enough, taking probably a lot of the carbon that they ate with them, which is our theory about why the respiration didn't spike commensurate with all the GPP. And then after that, we saw this consistent, rise in photosynthesis with a relatively stable ecosystem respiration. More importantly, more interestingly, methane. So this shows methane in grams of CO2 equivalent, total annualized, and it was relatively high during the beginning. But ever since that salinity event, it has not increased again. There's been a minor uptick in 2024, which is shown on this graph, but nothing like the first several years of the site's lifetime. So there's some theories about why that is. Generally, poor water salinity is very well correlated with a lack of methane, because there's sulfates in the same area where microbes could be producing that methane. Anyway, I'm pretty sure I'm running short on time. So this is another sort of example of Dutch Slough, which is one of our tidal wetlands. And it's very encouraging that Dutch Slough is one of our most productive sites that really my advisor is very familiar with FluxNet and global fluxes. He's published very well on these things, has never measured a site more productive, and claims that due to his personal database that he's been collecting his whole career is in the top 1 percentile worldwide, even when compared with tropical ecosystems, tropical forests, you name it, even like irrigated, well-watered, fertilized agriculture. Dutch Slough has a higher productivity rate and relatively lower methane than something like a typical impounded wetland. So that's just a bit about my own personal science, but really what we're here to talk about today is federal funding and the implications that has if it were to be pulled. So we give all of our data to Ameriflux, which is a national, actually international repository of data. They take data from all over North and South America, including Brazil and the tropics. Fluxes are completely free to download, and they solicit scientists from all over the world, and they provide them data management services, technical guidance, sometimes even funding. So our lab is old enough in the network that we're what's called a core site. So we sort of present the gold standard with which people compare, and as sort of in return, we are given some small trickle of consistent funding from Ameriflux's pool. Ameriflux is funded by the Department of Energy, but it's up for renewal in the next year, and it's very uncertain. They're at this point, trying to make their case for why they should continue. Even more importantly, potentially, there is what's called FluxNet. So Ameriflux is its own local regional repository, but there's other scientists all around the world that are doing this same type of research. There's Japan Flux, ICOS, which is Europeans Flux. There's even Seon in South Africa. There's Tern in Australia. There is Brazil Flux, Mex Flux, Chile Flux. There's networks all over the world that all come together every other year, essentially, for the FluxNet conference. And we're working on right now reproducing a data set that was put together in 2015, which I'm showing here, that is really the basis for gut checking and ground truthing all of these models that we get from satellite imagery. Satellite imagery and satellite technology in general is increasing really, really quickly in terms of what it can do, but it always needs a ground truth. And this network, the data is being gathered, but the data is not always being shared. And it really relies upon funding that fortunately or unfortunately, has come from the United States up until now to really make this type of network go. So I'm going to leave it at that, and as we all hopefully agree, keep science funded.
Thank you so much, Robert. That was fantastic. You have minutes for questions. And so depending on how long your answers are to these questions, I can ask you at least one, but maybe several. I just want to give you a break for a second by letting you know that people are in the comments. If you look back later to what people are saying, they're debating whether the caterpillars are many small or one single boss level caterpillar that are having all these effects.
There were millions of them. There were so many, and they only ate the cattails.
I think the other thing that people were reacting to, your visuals in the beginning were amazing. So much of the time we go out anywhere and we look around us and we see nature as it is right now. And it's really hard to imagine the changes that have happened. And I'm really impressed with that map that you showed of the global network, how many years so many of the flux sites have been up and sensing. I just want to emphasize for the chat, the power of consistent funding that covers a large region so people can coordinate is different from, somebody getting a private grant one time. So questions for you. Let's see. So someone asked, let's see, this is from G. Willikers. Estuaries are amazing at absorbing energy from storms and protecting inland areas. How much protected estuary land are we losing a year, either by climate loss or loss of legal protection?
That's a really good question. Yeah, let me read that again. That's an amazing question. It's a really hot button topic in California. I think that generally sea level rise is expected to outpace coastal wetlands in terms of sedimentation and accretion, but where there's no wetlands there, then it occurs even faster, and then you have sea level rise intruding onto land. So you're exactly right that they absorb energy from storms. They also sort of mitigate, if not solve, the problem of sea level rise. And where there's active management and sedimentation and higher productivity, then they can go even faster. So in terms of legal protections, I'm not 100% sure, and I'm not a wetland restoration expert. I just do the fluxes.
So I'm going to add my own perspective to that. I have a marine biology background, and I worked for a marine lab in Louisiana for a couple of years. And one of the most profound things I remember a professor there saying is that there are more lawyers in the room when you buy a house than there are when wetlands are being discussed and protected. And in Louisiana and other places where wetlands are in danger of sea level rise, who owns the land? As it creeps inward, what do you do with land loss? So this is a topic that I don't want to take your time with, but very interesting. G. Willikers, thank you so much for asking. Robert, so I think a natural follow-on to that as we look at how land is changing, let's see. I'm going to read this name out loud. And out of time. Out of time asked, can we make our own wetlands? And people in the chat were responding with, what you mean in our front yard? But I want to ask, can you make anything a wetland? If wetlands are disappearing potentially because of climate change, can you just say, well, let's make new ones?
Yeah. So the issue with that, of course, is water, right? One of the reasons that it's such a compelling region, the California Delta, to make wetlands is because there's a California mandate that we must let about 50% of all surface water flow out to the ocean no matter what. And that water is literally seeping into these islands anyway. They're actually spending fossil fuel energy to pump it out. And so these are areas where restoring wetlands isn't actually costing us very much water compared to elsewhere where we might have to irrigate them and keep them flooded. If you create a wetland and it's later drained, much of that carbon ends up back in the atmosphere. It rapidly oxidizes. And if you're going to create a wetland, it's really, really important to keep it flooded and to keep it shielded from the atmosphere. And if you do that, it's very, very productive. But, where you go back and forth, it can actually cause more disturbance to the soil, and it can potentially cause the whole ecosystem to be more of a source, because when it's flooded, it creates methane, which is a very powerful short-term greenhouse gas. So that balance between drawing down CO2 and building soil versus creating methane is kind of tricky and really relies on decades or centuries of protection of these wetlands to really be a benefit.
Okay, so we can make new wetlands, but we should be very sure, because that's the best way to make new wetlands.
Yes, one of the findings from a lot of our measurements is that intentionally restoring wetlands with a strategic and adaptive plan is much better than just flooding them, because I didn't get to show a lot of the data from it. I guess I could have. But hill slough is a huge source of both CO2 and methane to the atmosphere. And it was bought by Ducks Unlimited to create bird habitat and flooded. And it was really a great project, but they had to spend all their money fortifying the road, and they couldn't seed the land, they couldn't prep it properly. And so it's turned into a huge source of CO2 and of methane as well. So versus Dutch Slough was like $60 million and this huge interagency project, smaller, but much more effective.
Got it. Okay. So we are maybe 30 seconds to a minute away. I'd like to give you a chance to give us a last word, either about those caterpillars or about like, how could I, as someone who cares about wetlands, is there anything specific I could do that I don't know about already?
In terms of wetlands, go and visit them. Just, a lot of people, I think there's some stigma around wetlands being built near housing because people think mosquitoes or, I guess creepy crawlies or nasties, but wetlands are really beautiful places. And I think people should just be more connected to the ones that are near them.
Thank you. That is a lovely sign off. I'm going to let you go. Have a great night. Thank you so much for that presentation.
Awesome. Thank you, Virginia.
All right, we are at 5:30 a.m. my time. We are halfway through this hour 65 of the live stream. Thank you so much for the amazing engagement in chat, for those amazing questions for Robert. I want to take a minute or several to remind us all why we are together. Welcome to new people who are joining. Good night or good day to people who are leaving. We are here because we all know that weather and climate science are important, and not just monitoring what's going on right now outside, which we could do with our eyeballs, but monitoring over a large area and then using the data that we have to turn it into forecasts so we can understand what is coming in the next days, in the next weeks, and then with climate stuff in the next years to decades. The United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect. We developed the first computer models of climate impacts of carbon pollution to let you know what you can expect and how we can prepare. To make the forecasts work, the United States has built an unparalleled network of observations that uses everything from weather stations to satellites to planes to balloons to boats to floats. I'm going to keep bringing it back up. 2 days ago now, someone talked about magnetic tapes being the largest repository of historic climate data still, because it is just the most efficient way to store all that data. And I just have not been able to let that go. The resulting forecasting and observation system built by US scientists is a true scientific miracle. And we are so pumped to be talking about the tiny ways that miracle plays out, and the people who are still working on making new miracles today during this live stream with y'all. The American public and decades of their support has made all of this possible, but in recent weeks, funding cuts from the US government have put all of that at risk. Weather stations are so short-staffed that we're losing our observational coverage, which is already hurting our forecasts. And it's not just like we know less well whether it's going to rain, whether we should have an umbrella or a raincoat. It's like we have staff that need to be scrambled and brought in before a system that might cause tornadoes goes through somewhere. So this is serious safety stuff that is already being put at risk. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for basic understanding of the weather and climate is disappearing. One concern for me is the future of science. If we are cutting student funding, then where will the next generation of scientists come from? It does not have to be this way. I know that was a lot of like heavy stuff, but it doesn't have to be this way, which is why we are having the live stream, to unify all of us, to see that there are people out here that support a different way, and to help us all act together, because that's when we make the biggest difference, is when a whole bunch of people act together. If you like what you're seeing in the live stream, then please use the link that's on your screen right now. It's in the description. I know it's been in the chat before. I assume it's going to be in the chat again. And you can, if you're in the US, call your representatives. And if you are not in the US, or if you are, no matter where you are, talk to the people around you about what you think is important in the world, and make sure that people are joining you in your quest to support science. Please spread the word to join the live stream as well. I see someone in the chat saying you feel bad that you haven't been able to consistently tune in. The YouTube channel has past segments of the live stream, and so all of this is just available all the time. If you want to revisit the Happy Science Conference feeling, you can go to the YouTube channel and you can watch the past portions of the live stream. No matter what, we hope that you learn something in the next half hour about weather and climate. And please do keep using the chat for energy, for connection, and for asking questions. I do want to hand it over now to our next speaker. I'm so excited for this. Spencer Hill. That's what I thought. This is going to be a little bit of a different half hour. Is that right? And you're muted. There we go.
Yes, good morning. Hi, Virginia.
Hi. So tell us what we're in for.
Yes, and apologies if there's sort of a loud noise in the background. You'll see in just a minute what that's about, and we'll turn it off before too long here. So yeah, my name is Spencer Hill. I'm an assistant professor of Earth and Atmospheric Sciences at the City College of New York. I'm coming to you live from our lab here in CCNY. And I wanted to do something a little different. So I have 1 hour of this 100-hour event. I have 1%. So I am your 1% for this context, right? And partly just to shake things up, partly because it's 5:30 a.m. on a Saturday, and partly because I just like to zig when others zag. I wanted to, rather than talk about any specific research, do some fun with rotating tanks and try to convince you via real world physical demonstrations that we can understand, we can simplify Earth's incredibly complicated climate system, its atmospheric and oceanic circulations particularly, using really simple devices on a tabletop and food coloring and Legos, believe it or not. And sort of the motivation being that it's that ability in science to take a complicated system and simplify it down to the simplest possible terms that is sort of paramount for progress, right? That true mechanistic understanding comes from that simplified modeling framework.
Fantastic. So we are in for an hour of tank stuff. I'm happy to stay on stage with you if you would like someone to chat to, but it seems like you have got all this together. And so if you'd like to just take it away, feel free to call me in or out, as push me off as you would like.
That's great. I appreciate it. Yeah. So I've done this sort of sequence of teaching demos, et cetera, many times. I've never done it live streaming. I'm going to try to use a second camera. I've also never live streamed anything else for that matter in my life. So please, you and Rudra in the back, bear with me. But yeah, otherwise we can get right into it. I'm going to actually start with just a few slides though, and then we'll get into the demos. So, sorry, thank you for queuing that up. Let me just put that. Okay. So, we're seeing my slides, still hearing me?
Yes and yes.
Wonderful. Okay, so we are going today to make weather on a tabletop. And the subtext there is hopefully convince you all who wouldn't otherwise think of it, why it matters for climate, for weather, that Earth is spinning around its axis once every 24 hours. Okay. First, a little shout out to one of the all-time great indie rock albums and songs, lead track to Daydream Nation from Sonic Youth, Teenage Riot, and the lead lyric here, everybody's talking about the stormy weather. What's a man to do but work out whether it's true? And I guess you would say that's what this whole live stream event is about in some context, or in some sense. And here's my sort of idiosyncratic approach to that. Okay, so how do I try to work out whether that's true, whatever that means grammatically? And it all comes back to this idea of a hierarchy of representations of the Earth system. This is a concept that was popularized by my scientific hero, and who I consider a good friend, Isaac Held. Oh my gosh, I spelled his name wrong. Sorry, Isaac. That should be 2 A's, not 2 S's. So Isaac had a 2005 article in the Bulletin of the American Meteorological Society in which he espoused this approach to modeling the Earth system in which we, for whatever our particular question is that a particular scientist is interested in, we find the numerical model, in his case, the computer model of the Earth system that is maximally simple but still captures that particular phenomenon of interest. So if you're interested in understanding the carbon cycle, you need an Earth system model, right? You need interactive biogeochemistry, et cetera. If you don't need that, but you need to understand, say, the flow over the Rockies and how convective parameterizations influence downslope wind events, blah, 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 you probably need a full complexity atmosphere. If you want to understand sort of the basics of how far the Hadley cells extend into the subtropics, for example, which is one of my research foci, you don't need a full atmospheric model. You can use a simplified octoplanet, et cetera, right? What Isaac presented really beautifully in that essay was this idea of the model organism hierarchy in biology, right? This idea that you can study a lab mouse or a fruit fly or E. coli, depending on what level of complexity you're studying, and sort of making that analogy to Earth system science. Okay, so that might sound a little bit abstract. I wanted to give three examples of how the lay person might think about that in terms more they're used to, I would say. The first is using wiener dogs or dachshunds, okay? So on the left, we have, oh, sorry, and I should have mentioned this figure, I didn't put the credit on there. This is actually not from Isaac's essay. It's from a really nice review led by Penelope Marr et al. From a few years ago in the journal James, I believe. Okay, so let's go back to our dachshunds. And on the left, we have a real photo of a real dachshund. I downloaded this before the AI era, so I promise you it's real. And we see this beautiful brown dog. It's very long, and we see its fur. We see all of it in all of its glory, right? That's great. We can go instead to this sort of impressionistic painting or watercolor, maybe it looks like, in the middle here. And you get pretty much all of the core essence of that wiener dog, right? You also happen to learn that there are both brown versions and this sort of black-brown combo version. But we can simplify this dachshund down way further, right? So it happened to be Pablo Picasso, one of the great artists of all time, but nonetheless, with the pen in his hand, you are able to sketch out the complete long, funny shape of this dachshund in literally one single pen stroke, right? So this is just one continuous stroke of his pen. If you go from the information density, whatever you want to call it, of this left image or even this right center compared to the right, it's, however you want to quantify it, many orders of magnitude simpler here, right? And there's something truly elegant and beautiful about this representation on the right that is different from the elegance and beauty of the dachshund itself or of this lovely watercolor. Okay, now we're going to turn from visual art to music. So there's a song called It Never Entered My Mind. It was a show tune originally from a 1940 Rodgers and Hart musical. And it was recorded many, many times since by many, many different artists over the years. I'm not going to try to play the audio. I'm pushing my luck as it is technically, I think, here. So I'll just, hopefully folks can screenshot this or somehow they can just Google these. The point here is that you could think of this progression of recordings, so the first being roughly from the original musical. So it's a lovely show tune. Then 15 years later, Frank Sinatra does a version of it in his classic In the Wee Small Hours. And then a year later, the Miles Davis Quintet in their classic, one of the 4 Miles Davis Quintet albums, they do yet another version. And as you go from the original show tune to Frank's to Miles's versions, you get a similar dynamic where first Frank and then even especially the Miles Davis Quintet are stripping away elements and playing with the original tune, right? So Frank's becomes very spare. He still has his vocals though, so you retain the lyrics. But it's very spare and he has his very particular stylistic elements, right? And in the Miles Davis Quintet version, it's entirely instrumental. And Davis abstracts, he plays the lead line with his trumpet, but he abstracts it so much, he cuts it down so much that it was multiple years of listening to both Frank and Miles Davis's versions before I even realized, I even made the connection that they were the same song. And for my money, the Miles Davis Quintet recording is one of the all-time great recordings of popular music. Okay, so it's in atmospheric modeling, it's in art, it's in music. We also use a hierarchical approach in physical lab demonstrations or simulations, as it were, of the Earth system. Now, much of the rest of this will be at the rotating tanks, but essentially, if you don't believe me for now, just take my word for it for now that you can simulate the Earth system meaningfully using a rotating tank of water on a tabletop. And there too, we have a sort of hierarchical approach, okay? So this instrument on the left is like a 10-meter wide device, so many millions of euros, I guess, because it's in France, and very complicated. You can see it's massive. They do very cool experiments there. You can go the weather in a tank project out of MIT in the 2000s, sort of brought that down to classroom size. And then in the 20-teens, when I was at UCLA, a group led by Norris Koo and John Arnault, Juan Laura and myself, we stripped this down even further to a little device you can get via Lego pieces and stuff you can buy on Amazon for, at the time, around $50. It's probably more like 100 these days. Okay, so I'm gonna stop. Okay, yes, I'm gonna, last thing before I switch off my slides is just want to give a little bit of a personal connection to weather and climate and honor one of my grandparents. So my grandfather, Laurel Charles Peterson, he went by Chuck. He passed away a couple years ago, and he was a career Navy pilot. He worked his way up to captain ultimately. And part of that career, I would like to go back, talk to my mom and get better on the specific details, but he flew hurricane hunters for the Navy. So this was the setup at his memorial back a couple years ago. And if I zoom in here, you can see these patches that he earned in his hurricane hunter missions, right? So they got different patches for different degrees of heroism or difficulty, I guess, as it were, of the flights that they did. So exceeding 100 knots, low and high, it looks like in these cases. So yeah, so that's a little personal connection I have with weather and climate, going back to my ancestries. Okay, so we'll end my slides. I'm now going to attempt to check my notes. Yeah. Okay, so now I'm going to share okay, we've got this. Okay, great. Okay, so let's actually do some rotating tank demonstrations now. I'm gonna bring this over. Okay, 1 second. Okay, great. You all are still hearing me, I hope?
Yes, we can hear you great.
All right, let's get to it. Okay, so here we are. Question is, why should we think about a rotating tank being at all relevant to the entire planet? Okay, and why does it matter that it's rotating in the first place? So let's take the second question first. Okay, let's start with not a rotating tank of water, but a spinning top, okay? So if I let go of this top, and those are watching, answer all my questions to yourself, all right? Let's make this an interactive, active learning environment here, okay? If I take this spinning top and I let go without spinning it, what's gonna happen? All right, we'll run the experiment. I'm gonna let go, and it fell over. It's the world's most boring toy, right? What matters is, or what happens, what makes it fun for kids, my daughter included, is if I can, when you spin it, it stays put, right? It stays vertical, it doesn't fall over. So roughly speaking, it's that rotation that keeps it vertically aligned. Whatever sort of orientation the rotation has initially, it by conservation of angular momentum for those that matter or those that care, it needs to retain that orientation, and so it won't tip over until eventually friction causes it to slow down and peter out, okay? There's another system that's spinning, and that is Earth, okay? So we are spinning much more slowly than this top, once every 24 hours, but for the scales of motions that we're concerned about, massive storms, Hadley cells, etc., ocean currents, it's enough to make the system, that this spinning sort of dynamics matter for the system a lot, okay? Next issue, okay, so a spinning top, that's easy, but what about, how do we go from this spherical Earth, right, to something flat we can put on a tabletop? Okay, so for that, I'm gonna bring in my friend here. This is, I believe it's Jafar from Aladdin as a Lego figurine. And what I'm gonna do is I'm gonna tape him to the top of this globe here. Bear with me. All right, so here's Jafar on top of the planet. All right, and as the planet spins, all right, he's tired, he's resting, okay? But as the planet spins and he sits on the North Pole, Jafar is rotating with the planet, right? Okay, so the Earth spinning rotates Jafar, it rotates the atmosphere, it rotates the ocean. Now I'm going to take Jafar's friend, a helicopter pilot person here, and put him on the middle of this tabletop. And I'm going to spin that tabletop, and lo and behold, they're spinning in just the same way, right? Moreover, if I, hopefully Jafar stays on, let me take this, let me buckle this gal in here. If I tape her on and I show you, what do we have here? If you can see that through the glare, this is a stereographic map projection, right? So looking down at the North Pole, and hopefully you can see that, at least looking down at the planet from above and from space, as if you were looking down at the North Pole, these two, when they spin, it looks exactly the same, right? I almost forgot the most important part of my demonstration here, since we're thinking about being in space looking into down at the Earth, okay? Okay, so we have a tabletop that spins just like the Earth, right? Next up, okay, we need a tank. We're getting ultimately to a tank of water. So why can we use a tank of water to study the ocean and the atmosphere? For the ocean, that's maybe more straightforward. Ocean is water. The tank is water. That's the most important part. For the atmosphere, well, it's a gas. Maybe that's different. But the key is that both the ocean and atmosphere are fluids, right? So a solid is something that is rigid. It keeps it safe, or keeps its shape. Both liquids and gases, they expand into whatever you pour them into, okay? And with respect to their motions, you can treat them as almost the same, the ocean and the atmosphere, for many, many purposes. Okay, so next up, so we've got a rotating Earth. And we've hopefully convinced you that that a rotating tank of water is a reasonable simulation of that, okay? So I am going to show you this demonstration over here. I hope no one's getting like motion sickness or anything. Like I said, I'm not a live streamer per se. So this setup, apologies for the noise. We've got our Lego-based tabletop demonstration here. We've got one tank of water that's spinning at a constant rotation rate. We've got another that is stationary, okay? And I am going to add food coloring, just plain old food coloring, to each one, and we are going to see what happens, right? So remember the spinning top, right? Remember what happened when it was spinning versus when it wasn't? Make a hypothesis while I'm setting this up of what's going to happen to the dye in each bucket, okay? First step is soap. This is not a geophysical phenomenon. This is just to break the surface tension. So that's like a lab artifact. This has no real world analog, but if you don't do it, it gets trapped in a surface layer. It's just distracting. All right, so here we go. I'm going to put some red and blue in each, and we'll see what happens. Okay, now here's where hopefully we have enough resolution on the camera, etc., is going to reveal the things that I want you to see. Okay, so here's what I know. Well, I'll give you 10 seconds, say. Think to yourself, what do you observe? Jot down your observations in your mental lab notebook here. So on the non-rotating one, what I see are these plumes that are going down. They're slightly denser than the water, so they're sinking overall, but they're also moving laterally a lot, right? The red and the blue are sort of not mixing per se, but they're going all over the place. The rotating system is almost staying in perfect local columns, right? There's very little lateral movement. And you can see that all the way down to the bottom, right? Or as they continue to sink down. How do we make sense of that? Well, the tank is rotating, right? So the tank, The dye in the tank is like this spinning top, where as it sinks, every time it wants to get tilted over, the spinning, the angular momentum, forces it to stay rigid. And so it continues to stay in a single column all the way down. The non-rotating case doesn't have that constraint, and so it can more turbulently move around the domain. Okay, next, we call this solid body rotation. And that name means exactly what it sounds like. The whole tank has been spinning for a long time. And as such, the whole mass of water is basically spinning all at the same rate as if it were a solid. Okay, let's add some stirring to the story here. Let's use, I just need to get a stir. Okay. And so let's pretend we've got air flowing over the Rockies or a seamount or something. We want to get some mechanical stirring in there. We're going to see what happens to the two colors of dye and the system as a whole. Again, make a hypothesis. How much mixing is there going to be in either case? How much clear water is there going to be in either case after we do the spinning, the stirring? Okay? So here I go. I just run it through here, and I run it through there. And this is one where it really pays to look over the top. All right. So I'll give you, again, maybe 10, 15 seconds to observe to yourself what you see or in the chat. What hopefully you see, what I notice, is that in the non-rotating case, it's sort of all just become a single mass, right? It's mostly this sort of blue-red purplish mix. In the rotating case, instead, I'm going to go all the way in, and you should be able to see these vortices, right? These sheets of dye wrapped around one another, right? And you also still see clear water. So there's parts where the system, the dye hasn't even reached to. Okay, so what do we take from that? What we take from that is that in a rotating system, rather than the mixing being much more efficient, you can do it in 3 dimensions. In the rotating case, you sort of only have 2 dimensions, right? You can't, the rotation prevents you from tipping over. And so the fluid, rather than just turning into a purple blob, develops these sheets that wrap around each other, right? Okay, let's turn this off because my ears really hurt from that. Oh, so much better. We need to WD-40 this tank or this tabletop. You can see in the background, as soon as I stop the spinning, right, then you get very strong mixing right away, and it immediately goes to this all blue. Looks like I did more blue than red today, so it's more bluish than purple, but you get the idea. Okay, so now let's recap. Earth is spinning. That matters because, like a spinning top, the rotation sort of prevents it from tipping over, as it were. Okay? And when you combine that with any sort of stirring, as happens naturally in the ocean or the atmosphere, you're going to get in the spinning system these sort of long-lived, coherent swirling structures, vortices we call them, and you're going to get much less efficient mixing overall of, say, salt or heat or carbon monoxide, right? Anything that we care about. Okay, so that's that so far. There's still one big piece of the Earth system that we have not incorporated yet. So let's bring back our globe. Jafar's still kicking it on the North Pole. And I'm going to ask you, is he cold or warm compared to if he was on the equator? All right, so let me get, since we're just already, I'm just kind of going wild. Let's just continue it. We got his homie here. She's kicking it at the equator. Jafar's at the pole. Who's warmer, right? Yeah, Jafar's freezing. She's kicking it. She's probably getting rained on. And that is a huge sort of, just as much as the rotation of the Earth, that is just as important of a feature for its circulations of the atmosphere and the ocean, right? We have this large scale temperature gradient, we call it. Temperature's warmer here, lower here. So these tanks, even though when it was spinning, didn't have that, right? This is just all room temperature. But we go over to our Big Daddy tank over here. This is called the HT3. This was also developed from that DIY-namics whole thing. I'm gonna hopefully not drop my laptop and break this. What you can see, hopefully, is a paint can in the middle with a dumbbell, not because I'm trying to get swole, but because that weights it down. What hopefully you can also see in there is ice, okay? So we have filled this with ice water, threw in a little salt to bring down the freezing point even more to make it cold. And this has been spinning since before I started, okay? So in this situation, we have not just the spinning, but we have the temperature contrast. The inside is colder than the outside. Okay. I have an IR camera here. We can actually check that. So if I do the outside of the tank, I'm reading 64.5, if you can see that. And if I do the inside, I'm reading 62.2, okay? So the near the can is colder than the outside. All right, let's see what happens now. I'm gonna do blue all in the middle to start, red on the outside to start, okay? All right. The big tank, you can really go for it too. And there's a super fun, in between, we're gonna throw in some leak locator fluid, this fluorescent dye thing, which is awesome because it looks really cool. And we'll do that in the middle. All right. Now, I didn't stir it at all, right? I didn't bring my pencil through it like I did the other one, okay? And I put the blue all in the middle to start and the red all on the outside. But let's see, is that still the case? What do we see? Again, apologies for the vertigo / motion sickness, whatever my crummy live streaming is generating for you. Nice, okay, this worked just how I was hoping for. I see this beautiful 1, 2, 3, 4, 5 sort of low pattern in the blue dye, right? So we have these 5 large scale eddies, we call them, that have emerged in the system. So this particular type of eddy, this particular type of swirling disturbance, which is driven by the combination of Earth's rotation and the temperature gradient, we call that baroclinic instability. And baroclinic instability arises in the oceans, and it also arises in the mid-latitudes and extratropics in the atmosphere. So anyone that's in pretty much anywhere in the US, but especially the further north you go, the winter storms that we experience, those are almost always driven by this type of baroclinic instability. And so the winter weather, massive snowstorms versus strong dry patches in between, you can largely think are driven by instabilities exactly analogous to this one, to these ones. The only difference is, well, not the only difference. Obviously, in this case, there's no snow or rain, right? Don't get me wrong, we don't have the whole enchilada, but the underlying physics is largely identical. So check that out, pretty awesome. Notice, one last thing I'll say, and then I'll show you a couple stills, I think. Again, we started with the red dye all outside, the blue all inside, the yellow in the middle. Notice the filaments of red and yellow dye that that the eddies have brought in toward the cold source in the middle, right? And conversely, notice the blue filaments that have made it almost all the way, this one's a good one right here, all the way out to the edge of the tank. So let's think about what that means for the transport of heat, right, that these eddies are affecting. The blue was in the middle, that was the colder water. And some of the blue dye is going out to the outer region, which was initially warmer. The red dye was where it was initially warmer, and the yellow dye, and some of the red and yellow dye is getting moved in towards the cold source. So if you have warmer water moving into the middle, and you have colder water moving out, both of those are acting, well, I'll ask you, what is that going to do to the temperature gradient? Is that going to reinforce? So is it going to make it stronger? It's even colder in the middle than outside, or is it going to weaken that temperature gradient? 15-second mental lab note. So the answer is that is acting to warm the inside and cool the outside, right? You're bringing heat, you're bringing warmer water from the outer part of the tank in towards the middle. And that's sort of a hallmark of fluid instabilities, right? They modify the system in such a way that relaxes the system back towards a state of neutrality relative or in terms of what caused them. That's a little technical. Let me say that in a different way. These baroclinic eddies, these swirling vortexes, they are moving cold water out and they are bringing warm water in. And recall that it was this cold in the middle versus warm on the outside in the first place that caused them to exist, right? Along with the rotation. So these are acting to weaken that large-scale temperature gradient. They are acting to cool the tropics, as it were, and warm the poles, so to speak. Okay, let me check on the timing. We have got, what I want to end with, because we do have time, is now, actually I want to share just a Chrome screen, so, yeah. Bear with me. I want to show you some videos of things like of a very similar demonstration we've done in the past. And I'm just pulling it up. Directors, just bear with me 1 second. I'm pulling up the video. And then we will, then I'll share the screen. Where is that? It's an old school one. Here we go. Okay. I'm just getting through the YouTube ad. Okay, so now I'm going to come back to this and present, share screen. Oh boy. Okay, now it's saying, all right, I think it's good. Okay, I'm going to do something I'm going to switch back. Okay, directors, bear with me. Can you please switch from the lab?
How can we help?
Here's where I may have gotten too cute with all of this.
Your
Okay,
cute is
here's what
just right when you're wearing that helmet, Spencer. We're all good.
Great.
Yeah.
Awesome.
If I give you guys a URL, could you guys put it up? It's just a YouTube link.
I could try sharing it on mine. Yeah.
All right. Sorry about this.
No worries. Do you want to share it in the chat, the private chat?
Yeah, absolutely.
Nice.
Spencer, while you're doing that, I'm just going to pepper you with encouragement. People are yelling at you in the comments about how wonderful this is.
Right on.
If you could personally visit every class that everyone in the chat is in, this is the solution that we have converged upon.
Great. Well, I'm very glad to hear that. It's challenging times. I did put it in the chat, Mark.
Okay, I'm gonna try to set that up. I'll be right back.
Thank you. Yeah, I guess sort of a meta point that I want to convey here is challenging times. Let's not lose our sense of joy and wonder and bewilderment at the Earth system. I got into climate science motivated by climate change, actually. I was an undergrad and took a global warming 101 class, essentially, and wanted to save the world, so to speak. But then once I got into the further coursework, I kind of just fell in love with the physical system and continue to have that love. And there is a acute need for curiosity-driven and joy-driven basic understanding of this and all other natural systems, I would say. So, yeah.
I so appreciate that and agree. People are also, in terms of feelings, holding a moment of silence for your Lego figurines in the chat right now. So we have joy and we also have some whimsy this morning.
I think Jafar looked like he had a pretty warm get up there. So.
All right, I think we got the video set up. I'm not sure if the sound will work, but
It doesn't need sound. It doesn't need sound.
Okay, we're gonna bring it on stage, and I'll take myself.
Thank you so much. Yeah, sorry to throw you guys a bunch of curveballs. Okay, so this was produced by Juan Laura and an undergrad working with him at the time. You're seeing, as it tells you, a time lapse of weather over North America. You can see exactly these baroclinic eddies in the atmosphere. So these swirling storms as visualized in the cloud fields. And what the rest of the video will walk you through is the fact that it's basically the exact demonstration I just did. The key difference, however, is that now this main screen, we have the camera is rotating with the tank, right? So if you go back, right, if you look at here, right, we're looking at it as if we're in space and the world is spinning around us. I have this platform on the top where you can put a camera, right? So then it's like you're in the rotating frame, just like we are, right? So this main image in the video is looking at the baroclinic eddies as like we are when we're rotating. As we're now rotating with the Earth, we've landed, and I'm going to take off my silly helmet. Notice they did the exact same thing, blue on the inside, red on the outside, and we get this exact same pattern of these beautiful baroclinic eddies and these filaments of blue that go all the way to the outer edge, and conversely, the red getting brought into the middle. And you can see those structures look very much like those cloud structures we see in the satellites. What controls their size and other properties? Well, it's a combination of the different factors I mentioned, how fast the tank is rotating, how strong the temperature gradient is, it also matters how deep the water is. And yeah, I guess to reiterate one more time, the net effect of all these swirling eddies, in addition to bringing us crummy weather at times, is to warm the poles and cool the tropics relative to the hypothetical scenario where they didn't exist, right? So all of us who live in the extratropics can be grateful for these, because otherwise we would be much colder indeed, right? Okay, that's that on the video and everything I've got for you guys.
That was incredible. Thank you so much. And the beauty of that presentation, at every moment, it felt like you were anticipating the questions that I was watching come into the chat, because most of the questions people were asking were like, okay, wait, so the tank is the whole globe. This is why weather works, is what you're showing us. And you just wrapped it up with this incredible visual that laid your tank on top of the globe and said, yes.
Thank you. I would say for all the instructors out there who want to teach with not just rotating tanks, but any sort of demonstration, they can be very powerful. They can also end up being like a science magic show, right? Where you just show, oh, wow, that looks cool. But the students, your audience doesn't connect it to the underlying concepts. So we want to be very vigilant about trying to engage actively the audience along the way, so that you're actually making mental connections, as opposed to them just sitting back and recording it and posting it to Tumblr or whatever kids use these days.
Definitely Tumblr. We've got a huge contingent from Tumblr in the chat right now. I want to ask you one thing. That this question is from Funny Things. They asked, and with global warming, this effect will weaken, I assume. So will you talk a little bit about the red, blue dyes, weather, and then global warming and how it affects it all?
It's a great question. In short, it's complicated, right? So one important piece of the story is that, as I think many others in the live stream have talked about, the warming that we are experiencing and are set to experience is not uniform, right? It is polar and especially Arctic amplified. We expect more warming in the high latitudes, the Arctic especially, in the coming century, relative to lower latitudes. So just that piece alone, based on what I said about the temperature gradient, the poles being colder than the equator, by that dynamic alone, you might expect what? Would you expect it to strengthen these eddies or weaken them? It would be to weaken them, right? You're weakening if the cold poles are warming more than the warm tropics, so the difference between them has gone down.
Okay.
There are many other factors, however, and it's how various properties of these storms respond to global warming. They are not my actual expertise. My expertise is mostly in tropical atmospheric dynamics, a different sort of regime altogether. It's closer to non-rotating than rotating. But suffice it to say, yeah, there are many potential changes. Consult the IPCC and your local mid-latitude dynamics expert.
So I was going to ask you, IPCC and mid-latitude dynamics experts are maybe somewhat inaccessible to many of us. What parting kind of feeling action, do you want the average person to take away if this live stream is their most intimate contact with this kind of science?
I'll take the liberty, because others are so being such good soldiers and sticking to the talking points and everything, which I fully support, by the way. I'll take an even sort of bigger perspective there, which is that I hope that everyone watching is just curious. I hope you maintain your curiosity in two distinct and important ways. One is about the world we live in, right? I mean, one of the beauties about climate science, atmospheric science, is that it's literally the air we breathe, right? We walk through it every single day, but we hardly ever sort of take stock of that. And whether or not it's about climate, whether you're really interested in computer science or bugs or anime, or it doesn't really matter, but the more people that are genuinely curious and genuinely want to know about some aspect of this world, I think the better we will be. there's the second part is a corollary, which is more than anything, I think that extends to other people. Okay, I think the more that we are curious about what other people's perspectives are, about what might be behind someone's statement about climate change that I don't agree with, or that gives me an emotional, instinctual negative reaction, what might be behind that? Might there be some nugget of truth? Might there something of value? Even if it's factually incorrect, how might I learn more about this person, more about their perspective, and come to better understand one another in that way? That's a little bit like, what's the word? Like kumbaya. I don't mean to sound like silly, but it's genuinely felt.
I totally hear you. And I know, at least for those who are repeat viewers during my 2 hours of hosting, I've been telling people over and over that the power that we all possess that no one can ever take away is to direct conversation to the things that we think are important, and to make sure people know that, like, they're not alone if they think it's important too. And then we get that feedback of, like, us not being alone if we think it's important. And I think the live stream is also, the chat is reacting to what you're saying by pointing out that I think for a lot of people, this is like one big science fair, or, going to a live science demo, like being invited in to the kind of Saturday morning science show that we all maybe used to watch from our TVs. And I just want to, this has been a theme for me as well during my hosting hour. I am in my house. My kids are asleep.
My daughter's asleep at home too, yeah.
Yeah, we're all, the scientists are all just us. We are all just people. And the scientists are the ones who grabbed that curiosity and said, you know what, I'd like to get paid a little. For us, this is a passion career. If I wanted to make more money, I would be doing something else. But I think we are all you, and you are all us. We just decided to try and make it our job. I think often of scientists as saying, no, I do want to keep asking questions. I cannot stop. And so I guess the only option is for me to try and make this my job now. So I know it does sound kumbaya, but I think it's something that feels maybe like it's a little misunderstood sometimes.
Yeah, I guess my if you'll allow me the last word on that.
Yeah.
The one shade of that, or the point of emphasis where I'm coming from is not just the conversation we want to have, but it's conversations with people you don't necessarily want to have conversations with about this kind of things, right? So I grew up in the Midwest. I have family in Texas, a lot of more conservative attitudes, so to speak, and a lot of more skepticism to the issue of climate change and related topics, right? These are good people. These are earnest, hardworking people. They happen to come to things from a very different perspective. And the more we can understand each other, the better off political outcomes will be for everyone. Okay, whatever your stance is on the issues at hand. And then very last thing is, we get to do what we love, right? And we make well above the median U.S. income. So like we're good, right? So this is super fun. So thank you so much for this.
Thank you so much for bringing your Legos and your rotating tanks and your extremely positive and contagious energy to the live stream, especially at this hour. It has been just a delight. Is there anything else you would like to leave us with before you go?
No, my caffeine high is probably going to crash and burn momentarily. So,
all right, then let's get you off camera before that happens. Thank you so much. Have a lovely day.
Likewise. Thank you.
All right. We are nearing the middle of hour 66. The clock ticked over during that presentation. Y'all in the chat were just here for it. If you joined partway through, welcome. It was a bit of a different hour that we just spent than we have been. But I love that you can see the range of what people do, the range of what people are passionate about on this live stream. If you were to just go to the YouTube channel and pull up the past segments of this live stream, you could just click at any point. And someone said it earlier, every 30 minutes, I care about something different. And I feel like you would just see such a huge range in emotion, in what people are talking about, in what people do, in how they arrived at this point in life, being on this live stream. So I am just so grateful that we could all share this together. All right, so I have not read our mission statement or our unifying statement in an hour because Spencer took an hour with the tanks. I have not greeted y'all in the chat kind of more personally in the chat for an hour. So let's do a check-in. Where are y'all coming from, and how do you know scientists? Is this your first interaction with us as a group of people, or do you have some personal connection? Good morning. Hi. It's 6:30 for me. I'm on the East Coast while y'all are putting stuff in the chat. I know. Listen, Fish, I realized that your last name is Failurson. And if you don't mind, I don't want to make you like reveal personal information, but I've been laughing about Fish Failurson for the last 24 hours, like you were somehow a fish that didn't make it. Okay, so while you're putting stuff in the chat, I'm going to remind us all what brought us here and why this live stream is happening. Like I said, we're in hour 66. This camera right here, this TV, shows the hour that we're in. It took me until yesterday morning, almost halfway through, to realize that. Let's see. Right, so we're here because we think weather and climate forecasts are important to people in the United States and to people the world over. The United States has long been a world leader in weather and climate prediction. I know I keep saying this, but that's so much more difficult to do than just reporting what's happening outside right now. The US scientists developed the first computerized weather forecasts to help people know what to expect in the coming days and weeks. They made the first computerized models of climate impacts of carbon pollution, so to know what to expect in the years and decades to come. To make forecasts work, they created an unparalleled network of observations using weather stations, satellites, planes, balloons, boats, floats, and much more than that. The resulting forecasting and observation systems are true scientific miracles, and we are so excited to have this live stream so we can share those miracles and the people who are working on them even today with all of you. The miracles were made possible by decades of investment by the US public, not just dollars, but support in terms of building an entire infrastructure that makes science work, support in terms of encouraging people to go into the sciences, that they can have a career path this way, support in terms of just, I don't know, being aware, talking, doing stuff that matters, living science-informed lives. All that stuff is so important. In recent weeks, though, funding cuts in the US have put our scientific systems at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecasts. I mentioned it before. My hometown, where I grew up, no longer has 24/7 National Weather Service coverage, and the staff got cut right before a weather system blew through. They had a bunch of tornadoes. They did bring staff in overnight, but it was not what it should have been with people who were supposed to be there already. So this is really affecting safety and not just the app on your phone that says whether you should have an umbrella for the day. Laboratories dedicated to understanding our climate's future and, again, people's quality of life are being closed or shrunk, and funding for the future of science for students and for our basic understanding of weather and climate is disappearing. But it does not have to be this way. That's why we're doing the live stream. I'm getting some feedback from the organizers that thousands of people have called their representatives because they have seen the live stream, because they have been urged to act. And that is such an incredible number. And I've seen on social media some congressional people talking about how a really low number of contacts, like tens to hundreds, is an unusual volume that will make people pay attention. So if anyone's feeling discouraged out there, the live stream is working, but also your action is working and is powerful. It is making a difference right now. If you would like to contact your representatives, if you're in the US, there's a link in the description to this live stream. It usually appears on screen during this segment of the mission statement. It goes in the chat every now and then, but you do not have to be an expert yourself. You do not have to be a scientist. You don't even have to know how weather and climate science works to call your representatives and tell them that this is important to you and that we as a country should continue funding science federally. You do not have to know everything because the link takes you to a spot that gives you all the information you need to know. So, oh yeah, and if you're everywhere, I've been adding this in every day. If you're anywhere, US or abroad, talking to people, even having the uncomfortable conversations like Spencer was saying earlier, that matters too, because then we all know that we're not alone and societal pressure says support science, which makes it more likely to happen. Okay. Oh, and then you can tell people about joining this live stream. It seems like y'all on Tumblr have been doing a terrific job. I've been seeing people saying they've been posting on social media. I know I've been telling my friends and family about this. I cannot emphasize enough how much I love the community that I'm seeing in the chat. Y'all connecting with each other, connecting with me, connecting with the scientists on the live stream. And what you are doing absolutely is making a difference right now. So please keep it up. I am going to check the chat because we have a minute left before I can bring the next speaker on stage to see where y'all are from right now. I'm seeing, let's see, in y'all's interaction with science, New Zealand, a student, Germany. You've been helping with skeptical science in your spare time since 2010. Your dad was a science teacher. A bunch of people from Tumblr. I see you. People who have family members who are scientists. Oh, this is so great. Watching from China. Georgia, he did research on climate change in Greenland. Oh my gosh. Somebody's on a ridge where two rivers are meeting in Alaska. I know when I first checked in at 5 a.m. my time, someone was listening in from a plane in Michigan, above Michigan, pardon me. I see Switzerland, I see Kentucky, I see Scotland, but from California. It is so great to have y'all here. Thank you so much for joining us. Chat, you all should be pros at this by now. If you've been in this time slot with me before, we need to do a reset because YouTube has a limit on how long we can live stream for, and we're not at 100 hours yet. We're only at 66. So I am going to say goodbye. There will be a link that appears on the screen. If you go to that link, you'll get to the reset live stream. We will all join each other. People have been urging me to say this, so I'm going to say it. If you like and subscribe the new stream when we get there, it might help people find the stream. It might help YouTube like the stream. But we will see you in just a couple minutes. If you get there before us, don't worry. It just takes a little bit to reset. Bye for now. See you soon.